Black holes are among the most misunderstood ideas in modern science. They are often portrayed as cosmic monsters, roaming through space, devouring everything in their path. Light, time, even human reason itself. But the truth is simpler and far stranger. Most of what we think we know about black holes is wrong. They are not holes. They do not possess a special force that pulls everything in. And the universe is not on the brink of being swallowed. What makes black holes truly unsettling is not their power. It is what they reveal about us. They expose the limits of human understanding. In this journey, we will dismantle long-held illusions, follow objects we have never directly seen, reach the edge where physics begins to lose its language, and confront questions larger than any answer we have. This is not a story about cosmic destruction. It is a story about time, energy, and knowledge itself. And the moment science must admit, we do not yet understand the universe we live in. When we think about black holes, most of us do not begin with physics. We begin with images, a region of perfect darkness, a vast cosmic mouth, something that devours everything so completely that even light vanishes. In popular culture, black holes are rarely presented as natural phenomena. They are framed as creatures, as force, as threats with intent. Films and science fiction have created a remarkably consistent image. The black hole as a destructive abyss, an unavoidable endpoint, something that pulls in anything that comes near and tears it apart. We have grown so accustomed to this image that we rarely question its origin. We simply accept it as obvious truth. What is striking is that these images are not built from data. They are built to trigger emotion. Fear, awe, the feeling of insignificance in the face of an uncontrollable power. This is how the human brain works. Our intuition responds more strongly to images than to numbers, to stories rather than equations. When you see a dark region consuming everything, your brain does not wait for physical verification. It immediately concludes that it must be extremely dangerous. So our initial understanding of black holes is not shaped by science, it is shaped by emotion. And when a scientific concept is first encountered through emotion, it leaves a deep imprint. All information that comes later is rarely received neutrally. It is filtered through that initial mental image. This creates an interesting paradox. We feel as though we understood black holes early on, but in reality, what we understood was only a symbol of destruction, a symbol of inescapability, a symbol of cosmic fear. This symbol is so powerful that it shapes the very questions we ask. We do not ask how a black hole works. We ask how to survive encountering one. We do not ask what happens to space and time. We ask whether it will swallow Earth. This is not the viewer's fault. It is the natural outcome of how the story has been told. Popular culture needs clear images. It needs something to fear. It needs conflict to generate drama. Science is different. Science does not care how frightening something looks. It cares about which laws it follows. The problem arises when these two approaches become entangled. When emotional symbols are mistaken for physical concepts, we believe we are discussing the same thing. In reality, they are not the same at all. A black hole in cinema is a character. A black hole in physics is a state of space-time. The two are not contradictory, but they are not interchangeable. When we carry the monster image of black holes into scientific discussion, we quietly lay the wrong foundation. And if the foundation is skewed from the beginning, everything built upon it will tilt as well. This is why so many fears about black holes persist. Even though observational data has existed for decades, not because data is missing, but because the initial image is too powerful. Before we can speak seriously about black holes, we may need to do something simpler. Temporarily set that image aside. Not erase it. Not deny its cultural role. Simply stop using it as the foundation for understanding physics. And then, a natural question emerges. If the image was wrong from the start, then what is our understanding of black holes actually built on? After imagery, the next force shaping how we understand black holes is language. More specifically, the name black hole itself. It is one of the most famous terms in modern physics, and also one of the most misleading. When we hear the word hole, the human brain almost automatically imagines a void, an emptiness, a puncture, a place where structure has been removed. This is not a conscious inference. It is a linguistic reflex. Language does not merely describe the world, it quietly constructs mental models of it. When you call something a hole, you implicitly suggest absence. Absence of matter. Absence of structure. Absence of existence. But a black hole, in physical terms, that is not an absence. On the contrary, it is an extreme state of presence. The name does not reflect this. It simplifies a deeply complex concept into a familiar image. This simplification is useful for communication, but it comes at a cost. That cost is a flawed mental model planted from the very first encounter. When we say black hole, we are not just naming a phenomenon. We are introducing a metaphor. And this metaphor channels thought in a very specific direction. It makes us imagine the universe as having punctures, places where space itself is torn, regions where things fall in and simply vanish. In physics, there is no evidence that space is punctured. There is no empty gap in the fabric of the universe called a black hole. The issue is not that the concept is wrong. It is that the wording misleads. From the very name, we are guided toward a particular interpretation. And once an interpretation is established early, it becomes difficult to replace. New information rarely breaks the old model. It is often forced to fit within it. This is why people can hear that black holes are regions of curved space-time, yet still picture them as holes. Language has won over data. This is not unusual. It happens with many scientific concepts. With black holes, the consequences are particularly significant. Because they sit at the edge of human intuition, our brains did not evolve to understand extremes of space and time. When language reinforces a misleading image, the gap between understanding and misunderstanding widens. In fact, many physicists themselves are dissatisfied with the term. Once a term enters popular culture, it becomes almost impossible to change. So instead of renaming, science must do something more difficult. It must continuously re-explain, continuously dismantle the false models language has created. Before asking what black holes do to matter or light, we may need to pause here and ask a more fundamental question. If even the name itself leads us astray, how far from the truth might our understanding really be? Once we set aside imagery and language, we can begin approaching black holes from a more neutral position. And the first thing to clarify is a simple but crucial statement. There are no holes in the universe called black holes. There is no place where space has been carved out. There is no region where the structure of the universe is missing. This may sound counterintuitive to many, because our intuition is built on the wrong image. In modern physics, a black hole is not described as an empty space. It is described as a structure of space and time themselves. Space is not punctured. It is curved. Time does not disappear. It changes how it flows. When a massive star collapses, what happens is not the erasure of matter. What happens is that its mass causes the surrounding space-time geometry to curve to an extreme degree. This is the key point the whole image fails to convey. A black hole is not a place where nothing exists. It is a place where structure exists in its most extreme form. Space there is not removed. It is compressed. Time does not stop. It becomes different. If we could see space-time geometry, we would not see a gap. You would see a deep curvature, like a fabric pulled downward by an enormous weight. Even that analogy is only illustrative. The reality is far more complex. A black hole is a valid solution to the equations describing space-time. It is not an exception. It does not break the laws. It is a direct consequence of them. This is why physicists do not see black holes as scars in the universe. They see them as a physical state, a state where familiar quantities reach their limits. Density, curvature, temporal distortion. None of this implies nothingness. On the contrary, black holes represent too much. Not too little. Too much mass in too small a region of space. This concentration is what makes space-time geometry extraordinary. By calling it a hole, we unintentionally invert the nature of the problem. We think in terms of absence, when the reality is extreme concentration. This confusion is not merely linguistic. It directly affects how we imagine everything that follows. If you think of a black hole as a void, falling into it sounds like erasure. But if you understand it as extreme curvature, the questions change. It is no longer about falling into nothingness. It becomes about motion within a very different geometry. This is a crucial shift in perspective. A black hole is not a void in the universe. It is a part of the universe's structure, clearly defined by physical laws. Nothing is missing there. Only things far beyond human intuition. And once we accept this, a natural question arises. If a black hole is not a hole, then what is it? Physically. Really? When we talk about black holes, one of the most common ideas is that they possess a special kind of pull, a force different from ordinary gravity. A force that seems to actively seek out and drag everything inward. In physics, no such concept exists. Black holes have no magical pulling force. They do not possess a special mechanism for attracting matter. The only thing present is gravity. And it is the same gravity we already know. No upgraded version. No special mode. Gravity still follows the same laws. It depends on mass and distance. It does not depend on whether the object is a black hole. This surprises many people, because in popular imagination, black holes are seen as more powerful than stars or planets. But gravitationally, an object is defined only by its mass. If you replace the sun with a black hole of the same mass, Earth would continue its motion almost unchanged. The orbit would remain stable. There would be no sudden jerk. No mysterious pull would emerge. This sounds counterintuitive, but it reflects a fundamental truth. Gravity does not care about the nature of the object. It cares only about mass and how that mass is distributed. A black hole does not pull actively. It does not reach out to grab matter. Matter falls into a black hole because it moves within curved geometry, not because an extra force acts upon it. This distinction is crucial. When we say black holes suck everything in, we anthropomorphize a physical phenomenon. We assign intent and behavior. In reality, there is no intent, no active mechanism, no predatory action. There is no effect that pulls the universe inward. A black hole does not control surrounding space by will. Space responds to mass according to established laws. A black hole is simply an extreme case of this. When an object gets very close, what happens is not stronger pulling. It is that the geometry becomes steeper. The natural paths available lead inward. At large distances, a black hole is not special. It behaves exactly like any other object with the same mass. The danger of a black hole does not come from universal suction. It comes from approaching a region of extreme curvature. When we remove the idea of magical attraction, a calmer understanding emerges. Black holes are not cosmic predators. They do not lurk and devour everything nearby. They simply exist. And the universe operates around them according to known laws. Once this is understood, a natural question arises. If a black hole's gravity is not different, what makes it so extraordinary? Once we accept that black holes have no special pulling force, the next step is a direct comparison. Comparing a black hole with something more familiar, a star. More precisely, a star with the same mass. In gravitational physics, this is a very clear comparison. Two objects with the same mass produce the same gravitational field. There is no exception for black holes. At sufficient distances, a black hole and a normal star are indistinguishable by gravity. Planets move the same way. Orbits follow the same laws. There is no indication that something more dangerous is present. This often confuses people, because in popular imagination, black holes are seen as enhanced versions of stars, stronger, more violent. But gravitationally, that is not true. A black hole is not stronger than a star of equal mass. It does not exert greater gravity simply because it is a black hole. The difference is not in the nature of gravity. It lies in the geometry very close to the center, far away. Space-time geometry is nearly flat. The natural paths of objects are stable and familiar. But as you move very close, things begin to change. Not because gravity suddenly increases, but because the geometry becomes extreme. With a normal star, you cannot get arbitrarily close. Its surface imposes a physical boundary. With a black hole, that boundary has a different meaning. It is the event horizon, not a solid surface, but a geometric boundary. Only when you approach this boundary does the difference become apparent. Before that, nothing unusual happens. No sudden pull, no feeling of being dragged. The danger of a black hole does not come from afar. It comes from proximity. The closer you get, the steeper space-time becomes. Stable orbits gradually disappear. But this is not because the black hole is more aggressive. It happens because space-time no longer allows the old paths. The danger, if any, is a consequence of geometry, not of intent, not of mysterious strength. This changes how we should visualize black holes. Not something that emits increasing gravity over time, but a static structure where familiar laws are pushed to their limits. If you are far enough away, a black hole is completely harmless. If you get close enough, things become irreversible. Distance, not nature, is the deciding factor. This is very difficult for intuition to accept, because we tend to associate danger with the object itself. In this case, danger is tied to location. Once this is understood, a new question begins to form. If gravity is the same, what is truly different about motion around a black hole? When we talk about black holes, a very common fear is the idea that everything nearby will eventually be pulled straight in, as if proximity alone causes orbits to collapse. But from a physical perspective, this is not what happens. Objects moving around a black hole still follow the same familiar orbital laws. They do not lose their orbits simply because the center is a black hole. If an object has the right speed and direction, it can orbit a black hole stably for a very long time. There is no mechanism forcing it to plunge inward. This often comes as a surprise, because in popular imagination, a black hole resembles a funnel. Everything that approaches slides inevitably downward. That image does not reflect orbital mechanics. In reality, orbital motion does not change simply because the central object is a black hole. The laws of dynamics remain intact. There is no special clause for black holes. An object is not pulled straight in unless its trajectory allows it. If it has sufficient tangential motion, it will continue to orbit the center, just like planets orbit stars. Just like satellites orbit planets, a black hole does not break this logic. It does not make physics chaotic. It does not cause familiar laws to stop working. In fact, what is surprising is how normal everything remains. Even when the center is a black hole, orbital stability is only disrupted when you get extremely close. And that is not because the black hole pulls harder. It is because space-time geometry no longer supports stable orbits. At larger distances, nothing special happens. The equations of motion are exactly the same. Physics continues to operate consistently. This point is often overlooked in popular descriptions. We are told about objects being torn apart, but rarely are we told that before that. They were moving quite normally. Fear tends to skip over this stable phase. It focuses on the outcome, not the process. Science cares about the process, and this process shows something very clearly. Black holes do not collapse orbital mechanics. They do not destroy the dynamical order of the universe. They are simply cases where familiar laws are pushed to their limits. When this is understood, a natural question arises. If motion around a black hole is not fundamentally different, why does the fear of being pulled in remain so powerful? When fear about black holes is scaled up to the universe, one question almost always appears. If black holes are that powerful, why is Earth still here? That question often points to a specific name: Sagittarius A, the supermassive black hole at the center of the Milky Way. At this point, imagination takes over. A gigantic black hole at the galactic center, with hundreds of billions of stars orbiting around it. This image easily leads to a false conclusion, that the black hole controls the entire galaxy. And if so, Earth being pulled in is only a matter of time. But this is where intuition once again misleads us. Sagittarius A times is indeed massive. Its mass is millions of times that of the Sun. But the distance between it and Earth is equally hard to comprehend. Earth lies about 26,000 light-years from the galactic center. At that distance, the gravitational pull from Sagittarius A times is extremely weak, far weaker than the gravitational pull of the Sun. In Earth's everyday existence, the Sun is the object that governs our motion, not the black hole at the galactic center. There is no such thing as a galactic pulling force dragging everything inward. Stars in the Milky Way move mainly due to the galaxy's total mass, including stars, gas, dust, and dark matter. Sagittarius A times accounts for only a tiny fraction of that total mass. It is not the sole gravitational center. It does not dictate the orbit of every star. Stars very close to the center are more strongly affected. But the farther out you go, the weaker the black hole's influence becomes. Earth is very far away. Our orbit around the Sun is not distorted by Sagittarius A asterisk, and the Sun's orbit around the galaxy is not a straight fall into the center. It is a stable motion lasting hundreds of millions of years. This reveals an important truth. Black holes do not dominate galaxies the way imagination suggests. They are part of a much larger system, a system where mass is distributed on vast scales. Sagittarius A times does not pull everything toward itself. It strongly affects only its immediate neighborhood. Beyond that region, familiar laws dominate. This is why Earth is not being drawn into the galactic center. Not because of luck, but because physics works exactly as it always has. Once this is understood, a new picture begins to form. Black holes are not global controllers. They do not command entire galaxies. They dominate strongly only on very small scales. And that leads to the next question. If a black hole does not control an entire galaxy, what, if anything, does it truly control? When the image of black holes is amplified for long enough, a familiar scenario emerges. The black hole as a wanderer in space, drifting between galaxies, quietly approaching, and then consuming entire star systems or even galaxies. It is a powerful emotional image. But once again, it has no physical foundation. In the universe, there is no mechanism known as cosmic hunting. Black holes do not actively search for prey. They do not select targets. They do not wander with intent to consume. Black holes move like any other object. Their motion follows galactic dynamics. They are bound by the surrounding gravitational field. A black hole within a galaxy does not move freely at will. It is part of that structure. It rotates with the galaxy. It responds to the surrounding mass distribution. If the galaxy is stable, the black hole is stable as well. If galaxies collide, the black hole is carried along with the collective motion. In all cases, a black hole is not an independent agent. It does not act outside the system. It behaves as a component of a much larger system. This is especially true for supermassive black holes. They form and evolve alongside their host galaxies. Their existence is tightly linked to galactic structure. They do not arrive from outside to destroy. They grow within the system. Even when two galaxies merge, the central black holes do not rush around consuming everything. They slowly move toward one another, influenced by the shared gravitational field, and eventually may merge. This process takes millions to billions of years. There is nothing sudden or predatory about it. The idea of black holes devouring galaxies often comes from confusing scales. We take an extreme phenomenon at very small distances and project it onto scales of hundreds of thousands of light years. Physics does not allow that. A black hole's influence drops rapidly with distance. Beyond its immediate neighborhood, it cannot consume large structures. A galaxy is not eaten by a black hole. It is a self-balancing system with mass distributed throughout. A black hole is only one of many components. Not a ruler, not a predator. Just a very special part of the overall picture. When we remove the image of roaming galaxy eaters, a more accurate view begins to emerge. Black holes are not dangerous because they seek victims. If there is danger, it comes from something else. And that leads to the next question. If black holes are not predators, where does their real danger actually lie? Perhaps no description of black holes is more familiar than this one. Black holes swallow light. At first glance, this sounds like a powerful statement, and also a deeply misleading one, because the word swallow implies a biological act, something being consumed, destroyed, removed from existence. But light is not eaten in any such sense. There is no digestion, no act of annihilation, no mechanism that turns light into nothingness. So what actually happens? Light is a form of motion. It always travels at the speed c, not faster, not slower. In almost every environment, this speed is sufficient for light to escape. In the case of a black hole, the issue is not the light. It lies in space-time geometry. As you approach sufficiently close to a black hole, the required escape velocity increases. At a certain point, the escape velocity exceeds the speed of light. This is the familiar boundary known as the event horizon. Inside this boundary, it is not that light becomes weaker. It is not that light is pulled harder. It is that no outward paths exist. Every possible path leads further inward. Light still moves at speed c. It does not change its nature, but the geometry it moves through has changed. This is a subtle but crucial distinction. A black hole does not pull light. It does not exert a special force on photons. Light simply follows space-time geometry, and that geometry does not allow escape. Saying that black holes swallow light is shorthand, convenient but imprecise. A more accurate description is this: light cannot escape because no escape direction exists. Not because it is destroyed, not because it is annihilated. It continues to exist. It continues to move. But that motion is entirely constrained by geometry. This leads to a profound implication. If light is not destroyed, then the information it carries does not simply vanish. It becomes trapped within a particular geometric structure. This is where physics begins to encounter very difficult questions. No longer about forces or motion, but about information. About whether information can be lost. And if it is not lost, where it is. When we discard the image of black holes devouring light, a deeper problem is revealed behind it. Not destruction, but confinement. If light is not destroyed, what does a black hole actually do with information? After removing most of the misleading images, we can return to the question of danger. Are black holes dangerous? The short answer is yes, but the full answer is far more nuanced. Black holes are dangerous under very specific conditions, at very close distances, within a very small region of space. That danger is local. It does not spread outward. It does not extend to galactic scales. Yet, in human imagination, this danger is often inflated into a global threat, something that could affect everything, everywhere, at all scales. This is a very common confusion, but it does not originate from physics. It originates from psychology. The human brain is not good at handling scale, especially scales far beyond direct experience. When confronted with an extreme phenomenon, we unconsciously expand its perceived influence. Something dangerous up close is felt as dangerous everywhere. Physics does not work that way. In physics, danger is always tied to range. It depends on distance. It diminishes with space. Black holes are a clear example. Very close to them, they can destroy material structures. Tidal forces become extreme. Stable orbits vanish. But step back just a little, and all of that disappears. At galactic scales, black holes are no longer a threat. They become one mass among many others. their role is diluted. Human emotion does not follow this dilution. Emotion tends to maintain intensity. A strong fear up close is projected outward, unchanged. And here, emotion begins to replace data. We do not ask what the range of danger is. We only remember that it is dangerous. This leads to a loss of true scale. A local danger becomes a global catastrophe. Science always emphasizes scale. No phenomenon exists independently of its range of influence. When we ignore this, we begin to fear things that do not truly threaten us. Black holes become the perfect symbol of this kind of fear, not because they are common, but because they are difficult to visualize. What is hard to imagine is easy to exaggerate. When data is not intuitive, the brain fills the gaps with imagination. And imagination is rarely neutral. It leans toward worst-case scenarios. This is not an individual failure. It is an evolutionary mechanism. Fear helped our ancestors survive. But in a cosmological context, this mechanism often leads us astray. We fear black holes as universal threats, while in reality, they are dangerous only when you get very close. And getting that close is exceedingly rare. When we recognize the difference between local danger and global imagination, our view of black holes begins to change. They are no longer looming threats over humanity. They become natural laboratories of extreme physics. And from here, a deeper question emerges: why humans consistently exaggerate the danger of what they do not understand. When facing black holes, what frightens us is not the numbers, not the mass, not the radius, not the equations describing them. Fear arises before those data acquire meaning. This is not accidental. The human brain reacts most strongly to what it does not understand. Uncertainty triggers vigilance. Ambiguity triggers fear. This is an ancient reflex. In early evolutionary environments, what could not be clearly seen was often more dangerous than what was familiar. So the brain learned to prioritize emotion over data. When information is lacking, the brain does not wait. It automatically fills the gaps. And the tool it uses is not science, it is imagination. Imagination helps us act quickly, but it does not help us understand accurately. In the case of black holes, the knowledge gap is vast. We cannot see them directly. We cannot experience them firsthand. We approach them only through inference and indirect measurement. For the human brain, this is an ideal condition for fear to grow. The invisible is often more frightening than the visible, not because it is more dangerous, but because it lacks clear boundaries. When we do not know exactly what happens, we assume the worst-case scenario. This is the brain attempting to protect us. But in science, this mechanism becomes an obstacle, because science does not advance from worst-case assumptions. It advances by gradually reducing uncertainty. Data does not generate fear. Data has boundaries. It tells us what happens and what does not happen. It is ambiguity that feeds fear. When we do not know how far a black hole's influence extends, we imagine it affects everything. When we do not understand motion around a black hole, we imagine everything collapses. Emotion overriding reason is not a human weakness. It is because the brain is designed to react before it analyzes. Science demands the opposite. It asks us to pause reaction and replace it with observation. This does not come naturally. It requires practice. When we say fear comes from lack of understanding, we are not denying real danger. We are distinguishing the source of the feeling. With black holes, most fear does not come from observational data. It comes from the gaps in our understanding. And every time science fills one of those gaps, fear recedes slightly. It does not vanish entirely, but it becomes proportionate. When we recognize this, a foundational question emerges. If fear comes from misunderstanding, where should science begin? When we think about science, we often imagine the discovery of new things. In reality, many scientific advances begin not by adding knowledge, but by removing misunderstandings that already exist. Science does not develop on an empty surface. It is always built upon the existing framework of human understanding. And if that foundation is flawed, everything constructed upon it will be affected. Misunderstanding does not only produce wrong answers, it produces wrong questions. When a question is misdirected, even the most accurate answer becomes meaningless. With black holes, this is particularly evident. When we imagine black holes as holes that devour everything, the natural question that arises is not how black holes function, but how to avoid being swallowed. That question is not emotionally wrong, but it is scientifically misplaced. It leads us to search for mechanisms that do not exist, and to overlook the structures that actually operate. This is why science cannot move forward simply by expanding theories. Before expanding, it must examine its foundation. Removing misconceptions is not a secondary step. It is foundational. If flawed models are not dismantled, new models will be distorted from the start. Throughout the history of science, many major revolutions began with the realization that a basic assumption was wrong, not because new data suddenly appeared, but because existing data was re-examined through a different conceptual lens. Science advances not only by answering questions, it advances by reformulating the right questions. But to do that, we must accept that previous questions may have been wrong. This is not easy, because humans tend to defend familiar models. They provide a sense of control, even when they are inaccurate. Removing misconceptions requires humility. It requires acknowledging that intuition can mislead us, and that common understanding is not always correct understanding. With black holes, removing misconceptions does not make them less fascinating. On the contrary, it makes them deeper. When the monster imagery is removed, black holes emerge as subtle consequences of physical equations. When vague fear is removed, they become natural laboratories of space and time. Science cannot build knowledge on a foundation of misunderstanding. It must clear the foundation first. Only then does expanding theory become meaningful. Otherwise, we are simply building higher on a tilted base. If the foundation is wrong from the beginning, where will the entire journey of understanding ultimately lead? As layers of fear and exaggeration are gradually removed, black holes begin to appear in a very different form. No longer monsters, no longer destroyers, but endpoints. In astrophysics, black holes are not anomalies. They are natural outcomes of stellar evolution. When a sufficiently massive star exhausts its fuel, it makes no decision. It does not choose to become a black hole. It simply follows the laws governing matter and energy. Gravity overcomes pressure. Structure collapses. A new state forms. There is no will involved, no intention, no destructive motive. Black holes do not act. They do not want to consume. They exist as inevitable consequences when physics is pushed to its limits. Calling black holes monsters reflects human emotion, not the nature of the universe. We tend to assign intent to what we cannot control. The universe does not operate on intention. It operates on laws, and black holes are among the purest expressions of that fact. They do not arise to destroy the universe. They arise because space and time allow them to exist. If black holes did not exist, that would be surprising, because the equations clearly show that such states are unavoidable. When we understand black holes as natural consequences, fear begins to transform into curiosity. No longer how do we avoid them, but what do they tell us about the universe? Black holes are not signs of chaos. They are signs of order pushed to its ultimate boundary, an order human intuition was never evolved to grasp. And that is precisely what makes them important. Not because they are dangerous, but because they force us to expand our conceptual framework. Black holes are not evil entities. They carry no morality. They are not opposed to life. They are simply indifferent. And that indifference is a defining feature of nature. When we stop seeing black holes as enemies, they become physical landmarks. Places where familiar laws reach their limits. Places that force science to be more humble. And it is here that a new question arises. If black holes are merely natural consequences of physical laws, what makes them so extraordinary? Before science finds answers, it always begins with questions. But those questions do not arise in a vacuum. They emerge from how we initially imagine the world. With black holes, initial perception plays an especially powerful role. How we imagine black holes determines what kinds of questions we believe are reasonable to ask. If black holes are imagined as monsters, the natural questions revolve around avoidance and survival. If black holes are imagined as destructive holes, questions focus on collapse and endings. These questions are not meaningless, but they reflect intuition, not physical structure. When untested, intuition leads the way. It can limit the scope of our curiosity. We fail to ask other questions, not because they are unimportant, but because they do not fit the initial image. This is how initial perception both guides and quietly constrains. In science, progress does not come from clinging to initial frameworks. It comes from repeatedly re-examining them, not to discard all common understanding, but to see whether they remain sufficiently precise. Not every initial perception is wrong, but many are only correct within limited contexts. When they are extended beyond that range, they begin to mislead. This is especially true for extreme phenomena like black holes. Science advances when it realizes that a familiar model is no longer sufficient, and instead of discarding everything, it refines. Adjusting perception is not about becoming instantly right. It is about making questions sharper, less vague, less driven by emotion. When questions are framed properly, answers, even if incomplete, become more meaningful. With black holes, adjusting perception has opened entirely new lines of inquiry. No longer only asking what is destroyed, but asking what is preserved. Not only asking where matter goes, but how information is encoded. These questions do not emerge when the initial framework remains untouched. They appear only after that framework is seriously re-evaluated. This reveals something important. How we ask questions matters as much as the answers. And asking better questions begins with revisiting how we understand the problem. When we recognize this, a foundational question emerges. If the way we frame questions can expand or constrain understanding, where should we begin adjusting? After moving through all the common misconceptions, perhaps the most important step now is not to learn something new, but to pause, a deliberate pause, not to forget what we know, but to observe again with less baggage. Reset here does not mean starting over. It means gently setting aside what no longer serves understanding. The first thing to set aside is the exaggerated imagery from films and popular culture. Not because they are worthless, but because they were designed to tell stories, not to describe physics. When we bring those images into science, they interfere with observation. The second thing to set aside is emotional language. Words like devour, destroy, abyss are not emotionally wrong, but they are imprecise descriptions. Science does not require fear-inducing language. It requires language that clarifies structure. The third thing, perhaps the hardest, is accepting an uncomfortable truth. Human intuition was not evolved to understand cosmic extremes. This is not a failure of humanity. It is simply the natural limit of a brain evolved to survive on Earth. When intuition fails, science does not force it to work. It builds new tools. Equations replace feelings. Observation replaces speculation. Resetting perception also requires openness. Not openness in the sense of believing everything, but readiness to update when new data emerges. Black holes are among the objects where understanding is still evolving. Many questions remain unanswered. And that is not a weakness. It is the normal state of science. It demands care, patience, and willingness to say we do not yet know. When we set aside misleading images, emotional language, and intuitive expectations, black holes do not become less interesting. On the contrary, they become clearer. Not clearer in the sense of being easy, but clearer in the sense of being properly placed. After removing what black holes are not, we face a deeper challenge. How did science learn to trust evidence that no eye could ever observe? This question is not unique to black holes. In fact, it reaches to the core of how science has always worked. From its earliest days, science has rarely depended on direct sight alone. Many of the most important entities in nature were accepted long before they could ever be seen. Atoms were treated as real long before microscopes could resolve them. Neptune was predicted through mathematics before any telescope pointed in its direction. Even electromagnetic waves existed in equations before antennas confirmed them. In each case, science did not wait for an image. It relied on something more subtle and ultimately more powerful. The idea of observation in science is often misunderstood. Observation does not mean direct visual perception. It means detecting patterns, measuring effects, and tracing consequences. The human eye is only one kind of sensor, and it is not a particularly reliable one when it comes to understanding the universe. Our eyes evolved to survive on Earth, not to measure reality at its extremes. They cannot see radio waves, X-rays, neutrinos, or gravitational distortions. If science limited itself to human vision, much of reality would remain invisible forever. Instead, science expanded the very meaning of observation. Instruments became extensions of our senses, not replacements for understanding. A telescope does not simply show us distant objects. It translates invisible signals into measurable data. A detector does not look at reality. It registers interactions and records their imprint. What matters is not whether something can be seen. What matters is whether it leaves consistent, measurable effects. Motion becomes evidence. Disturbance becomes information. Absence itself can carry meaning. When stars move as if something massive is pulling them. Science, pay us attention. When energy appears where no visible source exists, questions begin. These are not guesses. They are measurements connected by logic. This approach requires a different kind of trust. Not trust in images, but trust in consistency. Not trust in intuition, but trust in repeatable results. Telescopes, sensors, and equations form a network of checks rather than a single viewpoint. No single instrument defines reality. Agreement between independent methods does. This is why science can accept entities it has never seen. And it is why black holes entered science not as images, but as consequences. Before they were pictures, they were patterns. Before they were objects, they were influences. This is the foundation of scientific confidence. If science does not require seeing, then what does it require? If science does not rely on seeing, then it must rely on something else to describe reality. That something is mathematics. Mathematics enters science not as an image maker, but as a structure builder, long before instruments are capable of observing a phenomenon. Equations often describe its form. This has happened repeatedly throughout scientific history. Mathematical relationships reveal how quantities must behave if nature is internally consistent. They do not show what something looks like. They show what it is allowed to be. In this sense, mathematics does not invent physical objects. It constrains them. An equation cannot decide whether something exists, but it can tell us whether existence would violate the rules of the system. This distinction is subtle but essential. When mathematics predicts something, it is not making a claim about reality. It is making a statement about consistency. If the laws we believe to be true are correct, then certain outcomes must follow. If they do not, then something in our understanding is incomplete. This is why mathematics is such a powerful guide in science. It allows scientists to explore consequences long before confirmation is possible. But this power comes with limits. A mathematical solution can be internally valid and physically irrelevant at the same time. Nature is not required to realize every possibility that mathematics permits. Some solutions remain abstract forever. Others wait for the right conditions to emerge. This is why prediction is never the final step. A prediction only becomes meaningful when it faces data. Observation tests whether nature chooses to follow the path mathematics allows. Sometimes it does. Sometimes it does not. And sometimes it does so in unexpected ways. This interplay creates a careful balance between confidence and humility. Mathematics gives science direction, but not certainty. It opens doors rather than closing debates. When a mathematical framework points toward a possibility, science does not declare victory. It asks a quieter question. Under what conditions would this possibility leave a trace, and how might those traces be measured? This is where mathematics hands responsibility back to observation. The equations define what to look for, not what must be found. This distinction prevents science from confusing elegance with truth. Some of the most beautiful equations describe universes that do not exist, and some of the most important discoveries began as awkward mathematical results. Mathematics therefore acts as a filter, not a verdict. It narrows the space of what could be real, but it does not decide what is real. That decision belongs to nature, revealed through data. This is especially important when dealing with extreme predictions. The more unfamiliar a prediction is, the more cautiously science must proceed. Mathematical possibility alone is never enough. Evidence must converge from multiple directions. Only then does a prediction begin to resemble reality. And this raises a crucial question. If mathematics can point toward possibilities without confirming them, how do we know when nature has actually chosen one? When mathematics points toward an extreme possibility, science rarely accepts it immediately. Instead, it slows down. It asks whether the result reflects nature or merely the freedom of equations. One of the most striking examples of this hesitation appears early in the history of general relativity. Shortly after the theory was formulated, a solution emerged from its equations. Today, this solution is known as the Schwarzschild solution. At the time, it was nothing more than a mathematical result. It described how space-time would behave around a perfectly spherical mass. Under ordinary conditions, the solution produced familiar results. But when the mass was compressed beyond a certain limit, the equations led somewhere unfamiliar. Space-time itself appeared to collapse inward. A boundary emerged from the mathematics, beyond which no signal could escape. At that boundary, the known laws of physics seemed to break down. This was not a prediction anyone was eager to accept. It felt too extreme, too absolute, too disconnected from experience. Even the creator of general relativity himself was skeptical. Albert Einstein did not believe such an object could exist in reality. To him, the solution seemed like a mathematical artifact rather than a physical prediction. This skepticism was not a weakness. It was a sign of scientific discipline. Science does not treat every mathematical solution as a description of nature, especially when a solution implies infinities or singular behavior. Such results often indicate that a theory is being pushed beyond its domain of validity. For decades, the Schwarzschild solution remained in this uncertain category. It was discussed, debated, and largely set aside. There were no known objects that seemed to require it. No observations demanded such an extreme description of space-time. And without observational pressure, caution prevailed. This restraint reflects an important aspect of scientific method. Predictions are not accepted because they are elegant or profound. They are accepted because they become necessary. At this stage, the Schwarzschild solution was not necessary. It solved a mathematical problem. But no physical puzzle demanded its use. Science, therefore, kept it at a distance, neither rejected nor embraced. This careful posture would define the next chapter of the story. Because the turning point did not come from equations, it came from the sky. Slowly, quietly, observations began to reveal behavior that existing models could not explain. And only then did an old mathematical solution begin to look less abstract. The question was no longer whether the Schwarzschild solution was mathematically valid. It was whether nature itself was pointing in its direction. If even Einstein doubted the physical reality of such an extreme prediction, what convinced later scientists to take it seriously? Mathematics can suggest possibilities, but observation decides whether they matter. For decades, no observation demanded the extreme predictions of general relativity. Then, quietly, something began to change. Astronomers studying the motion of stars noticed behavior that did not fit familiar patterns. Some stars were moving as if influenced by a powerful central mass, yet there was nothing visible at the center of their orbits. No star, no nebula, no detectable source of light at all. What remained was motion. And in physics, motion is never arbitrary. The path an object follows encodes information about the forces acting upon it. By measuring how stars move, scientists can infer the mass that governs their motion. This method does not require seeing the mass itself. It relies on gravity's influence, not on light. When stars orbit rapidly around an unseen center, the equations are unforgiving. The mass must be large, and it must be concentrated in a very small region of space. This was not a philosophical interpretation. It was a numerical requirement imposed by the data. At first, astronomers searched for conventional explanations. Perhaps the object was simply dim. Perhaps dust obscured the light. Perhaps multiple objects were hiding together. Each possibility was tested against observation, and one by one, they failed. The inferred mass was too large for a normal star, the region too compact to host a cluster of stars. No known luminous object fit the constraints. What remained was an uncomfortable conclusion. Something massive was there, but it was not emitting light. This marked an important shift in scientific reasoning. The absence of light was no longer a problem to be solved. It became a clue. Motion replaced image as the primary source of information. The stars themselves became instruments. Their paths traced the invisible landscape of gravity. This was not yet proof of black holes. Science does not move that quickly. But it was the first time nature demanded an unseen mass of extreme density. The mathematical possibility from decades earlier suddenly had a place to stand. Not because it was elegant, but because it was necessary. Still, caution remained. A single line of evidence is never enough. Scientists asked whether the same invisible mass could reveal itself in other ways. Could it leave additional signatures beyond stellar motion? And if motion reveals mass, what exactly is that mass made of? Stellar motion around an invisible center raised the first serious questions. But science needed something more precise, a way to measure mass directly, not infer it loosely. This opportunity came from binary star systems. In a binary system, two objects orbit a common center of mass. Their motion is tightly constrained by gravity, and those constraints can be measured with extraordinary accuracy. By tracking orbital periods and velocities, scientists can calculate mass with little ambiguity. Unlike isolated stars, binary systems leave little room for interpretation. The mathematics is straightforward. If one object moves faster than expected, the mass of its companion must be larger. In several systems, astronomers observed a striking pattern. One component behaved like an ordinary star. The other exerted a powerful gravitational pull. Yet, it emitted no detectable light. Not in visible wavelengths. Not in radio. Not in infrared. What remained was a massive object that was effectively dark. At first, scientists again turned to familiar explanations. Could it be a white dwarf? The mass was too high. Could it be a neutron star? Again, the mass exceeded known physical limits. Neutron stars can only grow so massive before collapsing. These limits are not arbitrary. They emerge from the physics of nuclear matter. When observations crossed those limits, entire categories were ruled out. This process was not dramatic. It was slow, methodical, and cautious. Each alternative was tested and set aside only when it failed repeatedly. No single observation decided the matter. But over time, the space of possibilities narrowed. What remained was not chosen because it was appealing. It remained because nothing else survived the constraints. The idea of a black hole began to shift in status. It was no longer a speculative extreme. It became a candidate, a reluctant candidate. Science did not embrace it with certainty, but it could no longer ignore it. Binary systems had delivered something crucial, a mass that was measured, not imagined, a gravitational influence that could not be explained away. This strengthened confidence, but not enough for a conclusion. One question still remained. If the mass was real and invisible, how else might it reveal itself? And when many possibilities are eliminated, does what remains become more trustworthy? Up to this point, the evidence for black holes had been silent. Mass inferred from motion, gravity detected without light. But science still lacked something familiar, a signal that could be seen. That signal did not come from the black hole itself. It came from what surrounded it. In regions of extreme gravity, matter does not fall straight inward. Instead, it spirals. Gas, dust, and stellar debris begin to orbit as they fall. This motion forms what is known as an accretion disk. The disk is not smooth or calm. Different layers move at different speeds. Inner regions orbit faster than outer ones. This difference creates friction, and friction generates heat. As matter is compressed and heated, temperatures rise dramatically, far beyond what ordinary stars can produce. At these temperatures, matter emits intense radiation, not because it is luminous by nature, but because it is being violently energized by gravity. This radiation can escape, even when the central object itself cannot. The black hole remains dark, but its surroundings become some of the brightest regions in the universe. This was a crucial realization. It meant that invisibility did not imply silence. A black hole could announce its presence indirectly, through the behavior of matter caught in its grip. Astronomers began to search for these signatures, not by looking for black holes, but by looking for accretion disks behaving in extreme ways, disks that were too hot, too energetic, too compact to be powered by known objects. Again, caution was essential. Accretion disks can form around other objects as well. White dwarfs, neutron stars. But these objects impose limits. Limits on temperature, limits on luminosity, limits on how compact the emitting region can be. In some systems, those limits were exceeded. The energy output was simply too high, the emitting region too small. No solid surface could survive such conditions. This ruled out entire classes of objects. What remained was an object without a surface, an object that allowed matter to fall endlessly inward. The light did not come from the object itself. It came from matter on the brink of disappearance. This distinction mattered deeply. Scientists were not claiming to see black holes. They were observing the consequences of their gravity. This was indirect observation at its most powerful. Multiple lines of evidence began to align. Mass from stellar motion, constraints from binary systems, and now, energetic emission from accretion disks. Each alone was suggestive. Together, they formed a coherent picture. Still, one final piece was missing. The radiation was intense. But what kind of radiation was it exactly? And could its properties tell us how extreme these environments truly were? If the light comes from the environment, what exactly are we observing? The black hole itself, or only the consequences of its presence? When accretion disks revealed themselves through intense radiation, science faced a new layer of evidence. But not all radiation carries the same meaning. The spectrum matters, and one part of the spectrum stood out immediately: X-rays. X-rays are not produced casually in the universe. They require extreme conditions, temperatures of millions of degrees, violent acceleration of particles, energies far beyond those found in ordinary stars. When astronomers began detecting intense X-ray sources associated with invisible massive objects, The implications were immediate. These emissions could not be explained by conventional stellar processes. Nuclear fusion alone was insufficient. No known stellar surface could reach such energies without being destroyed. Once again, scientists tested familiar explanations. Could these be neutron stars? In some cases, yes, but in others, the X-ray intensity exceeded even neutron star limits. The emitting region appeared too small, the variability too rapid, the energy output too concentrated. These characteristics pointed toward matter falling into an extraordinarily deep gravitational well. As gas spirals inward, it accelerates to tremendous speeds. Collisions become more violent. Temperatures soar. At these extremes, matter naturally emits X-rays. This behavior matched theoretical models of accretion onto black holes. Not perfectly, but closely enough to demand attention. Importantly, X-rays provided a different kind of evidence. They were not inferred from motion alone. They were directly detected signals, yet they still did not come from the black hole itself. They came from matter under its influence. This reinforced a key idea. Black holes reveal themselves not by shining, but by shaping their surroundings. Each new X-ray detection added weight to this picture, not because it was dramatic, but because it was consistent. Different systems, different environments, the same underlying pattern: extreme gravity. Matter accelerated beyond familiar limits, and X-rays as a natural consequence. This convergence mattered deeply to scientists, because science does not rely on single lines of evidence. It relies on agreement between independent observations. Stellar motion, binary system mass measurements, accretion disk behavior, and now, high-energy X-rays. None of these alone could confirm a black hole. Together, they began to form something stronger, not certainty, but confidence grounded in convergence. This raised an important question. When multiple independent signs all point in the same direction, how much does our confidence truly increase? By the time high-energy X-rays entered the picture, science was no longer dealing with a single hint. It was confronting a pattern. Patterns are where science becomes cautious and confident at the same time. Cautious, because patterns can mislead. Confident, because when independent paths converge, coincidence becomes unlikely. In the case of black holes, the evidence did not arrive from one instrument, one wavelength, or one method. It arrived from many directions at once. Stars moved as if orbiting an unseen mass. Binary systems revealed companions that were heavy but dark. Accretion disks glowed with extreme energy. X-rays emerged from regions impossibly compact. Each observation relied on different physics. Stellar motion depended on gravity and dynamics. X-rays depended on high-energy particle interactions. Radio and infrared observations traced entirely different processes. These methods shared almost nothing in common except the object they described. That is what made the convergence powerful. No single measurement was precise enough to stand alone. Each came with its own uncertainties, assumptions, and sources of error. But their errors were different. Their weaknesses did not align. When independent measurements with different limitations pointed to the same conclusion, confidence grew not from precision, but from agreement. Science values this kind of consistency more than dramatic results. A single spectacular observation can be seductive, but it can also be misleading. Consistency by contrast, is quiet. It builds slowly, and it resists simple explanations. In the study of black holes, no observation demanded belief on its own. Instead, each one asked the same question in a different language. How much mass is present? How compact it must be? How energy is released nearby? When those answers aligned, the picture sharpened. Not sharper because it was more vivid, but because it was more constrained. Every new dataset reduced the space of possible explanations. What survived was not what scientists preferred. It was what remained compatible with everything else. This is the core of scientific trust. Not belief in authority, but reliance on convergence. Data does not persuade by being impressive. It persuades by being consistent across contexts. As observations accumulated, black holes shifted from a theoretical possibility to a practical necessity. Not because science had finally seen them, but because it could no longer explain the universe without them. Even so, restraint remained essential. Convergence does not mean closure. It means readiness to proceed further. Each consistent signal invited a deeper test, a stricter constraint, a more demanding question. When data converges, science does not stop asking questions. It learns which questions are worth asking next. If consistency builds trust, how far can that trust go before it must face its own limits? As evidence converged from multiple directions, science did not immediately declare a winner. Instead, it turned to a quieter and more demanding task. It asked what else could explain the data. This step is often misunderstood. It is tempting to think science advances by choosing the most exciting idea. In reality, it advances by eliminating what does not work. Every alternative to black holes was examined seriously, not dismissed, not ignored, tested. Ordinary stars were the first candidates. Could a faint or obscured star explain the unseen mass? The data said no. The mass was too large, and the region too compact. Clusters of stars were considered next. Perhaps many small objects packed tightly together, but their gravitational stability failed under scrutiny. Such clusters would disperse or collapse in ways that were not observed. White dwarfs were ruled out by mass limits. Their physics simply does not allow such densities. Neutron stars survived longer as candidates. They are dense, compact, and exotic by ordinary standards. But even neutron stars obey strict physical limits. Above a certain mass, they cannot remain stable. Observations repeatedly exceeded those limits. Not once, not twice. Across different systems and environments, other exotic models were proposed. Objects made of unfamiliar states of matter, configurations unlike anything previously known. These ideas were not rejected because they were strange. They were rejected because they failed to match the full set of data. Some explained mass but not radiation. Others explained radiation but not compactness. None explained everything at once. This process took decades. It was slow by design. Each hypothesis was allowed time to succeed or fail on its own terms. Science resisted the urge to converge too quickly, because premature agreement is more dangerous than prolonged uncertainty. Gradually, the landscape changed. The list of viable alternatives grew shorter, not because black holes were compelling, but because other explanations became untenable. This is a critical distinction. Black holes were not selected as the best idea. They remained as the least inconsistent one. In science, survival often matters more than appeal. A hypothesis earns trust not by explaining one observation perfectly, but by failing less often than its competitors. This can feel unsatisfying. It lacks the clarity of proof, but it reflects how knowledge actually grows. By the time black holes became widely accepted, the question was no longer whether they were exotic. It was whether anything else could possibly work. And that question had been answered, slowly and repeatedly, by the data itself, which leads to a deeper reflection. In a discipline built on uncertainty, is being less wrong than all alternatives a strong enough standard for belief? At this stage of the story, it becomes tempting to believe that science has simply guessed correctly. After all, black holes were once invisible, extreme, and difficult to imagine. It is natural to assume that belief preceded evidence, but this assumption misunderstands how scientific thinking works. Science does not avoid speculation. It allows it, but it does not stop there. Speculation begins with intuition, analogy, or mental imagery. It is a necessary starting point, but it is also fragile. Inference, by contrast, is disciplined speculation. It is speculation constrained by logic and evidence. Where speculation asks what might be true, inference asks what must be true if the data are correct. This difference is subtle, but it changes everything. Speculation can multiply endlessly. Inference narrows possibilities. Speculation is driven by imagination. Inference is driven by constraint. In the case of black holes, early ideas were speculative. They emerged from mathematical oddities and extreme solutions. But acceptance did not come from imagination. It came from inference built over time. Each piece of data added a condition. If the mass is this large, then the object cannot be a star. If the region is this compact, then a solid surface cannot exist. If the energy output behaves this way, then familiar processes are insufficient. None of these statements are guesses. They are conditional conclusions, and that condition is always explicit. If the measurements are accurate, if the models describing matter are correct, if no unknown physics intervenes, scientific inference never claims absolute truth. It claims reliability under stated assumptions. This is why scientific conclusions often sound cautious. They are. But that caution is a strength, not a weakness. It keeps science responsive to change. Speculation resists revision because it is personal. Inference invites revision because it is conditional. When new data arrive, the conditions are re-examined. If they change, the conclusion changes with them. This prevents science from hardening into belief. It allows understanding to remain flexible. In the story of black holes, this distinction was essential. Without it, extreme ideas would have become dogma or been dismissed too early. Instead, science held them in suspension, neither belief nor disbelief, waiting for inference to replace imagination. This balance protects science from illusion. It ensures that what is accepted is not what feels right, but what survives scrutiny. Yet this raises an unavoidable tension. If every inference depends on conditions, what happens when those conditions change? If scientific inference is always conditional, then trust must rest on how those conditions are tested. This brings us to a concept that often feels uncomfortable: indirect observation. To many people, indirect observation sounds like a compromise, as if science is settling for less than certainty. But in reality, indirect observation is not an exception. It is the norm. Much of science has always depended on effects rather than appearances. We do not see gravity. We measure acceleration. We do not see magnetic fields. We observe their influence on charged particles. We do not see atoms directly in everyday conditions. We infer them from spectra and reactions. In each case, reliability does not come from direct sight. It comes from consistency across independent measurements. This is the critical point that is often missed. The problem is not whether an observation is direct or indirect. The problem is how many independent ways the same conclusion can be reached. An indirect observation tested once is weak. An indirect observation tested repeatedly, across methods and contexts, becomes robust. This is why black holes could be taken seriously without ever being seen. No single signal carried the burden of proof. Instead, many indirect signals shared the weight. Stellar motion constrained mass. Binary systems refined those constraints. Accretion disks revealed energy release. X-rays confirmed extreme conditions. Each observation could be questioned on its own. Together, they resisted dismissal. This layered structure of evidence is what gives indirect observation its strength. Cross-checking is not an accessory. It is the foundation. When one method fails, another remains. When assumptions differ, agreement becomes meaningful. This is why indirect evidence can outperform direct images in reliability. Images can mislead. They compress complexity into a single frame. Indirect measurements preserve structure. They remain connected to equations, uncertainties, and error bars. This makes them easier to challenge and therefore harder to fool. In the case of black holes, indirect observation was not a fallback. It was the only path available, and science adapted its standards accordingly. Trust was not granted because the idea was compelling. It was earned through repeated survival under scrutiny. This does not mean certainty was achieved. It means uncertainty was constrained. That distinction matters. Science does not promise truth beyond revision. It promises methods that improve reliability over time. Indirect observation fits that promise precisely. So, where is the boundary that makes indirect observation trustworthy enough to accept? At this point, a deeper concern often emerges. If scientific conclusions are always provisional, how can they ever be trusted? This question feels unsettling because it seems to undermine certainty. But it also reveals a misunderstanding of what scientific confidence actually means. In science, virtue is not a virtue. Adaptability is. Every scientific conclusion carries an implicit condition. It holds given the data we have, the instruments we use, and the models we trust. When any of those change, revision is not a failure. It is the expected outcome of a working system. This is where science differs fundamentally from belief systems. Beliefs seek stability. Science seeks responsiveness. When new data arrive, science does not defend old conclusions out of loyalty. It re-examines them. Sometimes the revision is minor. A parameter is refined. An uncertainty range narrows. Other times, the change is more profound. A model is replaced. an assumption is abandoned. This process can look like instability from the outside, but internally, it is a sign of health. A system that never changes is not reliable. It is brittle. Science survives precisely because it allows itself to be wrong, and because it builds mechanisms to detect and correct those errors. The story of black holes unfolded within this framework. Early skepticism did not disappear because of authority or consensus. It diminished because data accumulated. Models were tested repeatedly. Predictions survived. Challenges, where they failed, adjustments were made. Where they succeeded, confidence increased. Acceptance did not come from declaring the question closed. It came from recognizing that further revisions were becoming smaller, not larger. This pattern matters. It signals convergence, not certainty. Black holes were accepted not as final truths, but as the best available explanations under current knowledge. This acceptance remains conditional. If future data were to contradict key predictions, revision would follow. That possibility does not weaken trust. It defines it. Trust in science is not trust that conclusions will never change. It is trust that change will be guided by evidence rather than preference. This is why scientific knowledge can be both tentative and dependable. Tentative in wording, dependable in method. The black hole, once doubted, now stands as an example of this process in action. Not a monument to certainty, but a record of disciplined revision, which brings us back to the original discomfort. If science is always provisional, how do we justify trusting any conclusion at all? The discomfort surrounding provisional knowledge often comes from a deeper assumption that what is real must be visible. This assumption feels intuitive. Human experience is built on sight. But science did not grow by trusting intuition alone. It grew by separating measurement from appearance. Measurement does not depend on vision. It depends on interaction. Anything that interacts with the world leaves traces. And anything that leaves traces can, in principle, be measured. Science is built on this principle. Mass is not seen. It is inferred from motion. Energy is not seen. It is measured through its effects. Force is not visible. Its presence is revealed through acceleration and change. Entire branches of physics rely on quantities that cannot be observed directly. Yet, their predictions work with remarkable precision. This is because science does not ask what something looks like. It asks what it does. Black holes belong to this category. They do not emit light, but they influence mass, energy, and motion in unmistakable ways. Their gravity shapes stellar orbits. Their presence drives accretion disks. Their environment generates radiation across the spectrum. None of these effects require seeing the object itself. Together, they allow precise measurements to be made. This is where scientific certainty resides. Not in image, not in direct observation, but in the reliability of causal chains. When effects follow causes predictably, inference becomes stable. The more independent effects point to the same cause, the stronger the conclusion becomes. This does not eliminate uncertainty. It bounds it. Science accepts that causes may one day be reinterpreted, but it also recognizes when alternatives become implausible. In the case of black holes, measuring consequences became more reliable than seeking images. Image, when they eventually arrived, did not replace inference. They complemented it. Long before that moment, science already had reasons to trust its conclusions. because those conclusions rested on measurement, not imagination. This distinction explains why unseen phenomena can be treated as real. Reality in science is not defined by visibility. It is defined by constraint. When measurements constrain reality tightly enough, belief becomes unnecessary. What remains is confidence grounded in method, which returns us to a new tension. If we only ever measure consequences, where exactly does certainty live? Given the growing body of evidence, it may seem surprising that black holes were accepted so late. After all, the mathematics existed early. Observational hints accumulated steadily. And yet, decades passed before consensus emerged. This delay was not due to ignorance. It was the result of restraint. Early data was simply not strong enough. Measurements carried large uncertainties. Alternative explanations could not yet be ruled out. Under such conditions, caution was the rational response. Technology also imposed hard limits. Instruments lacked the sensitivity needed to probe extreme environments. Entire regions of the electromagnetic spectrum were inaccessible. What could not be measured could not yet persuade. Beyond data and technology, there was a deeper hesitation. Black holes challenged intuition at a fundamental level. Objects from which nothing escapes defied ordinary reasoning. Science has learned to be especially careful with extreme ideas. History is filled with elegant concepts that later failed. Prudence demanded time, and time was used well, decade after decade. New methods emerged. New instruments expanded the reach of observation. Independent lines of evidence began to intersect. Stellar dynamics grew more precise. Binary system measurements tightened constraints. High-energy astronomy opened new windows. Each advance alone was insufficient. Together, they transformed uncertainty into convergence. Acceptance did not arrive with a single discovery. It arrived gradually, almost reluctantly. Scientists did not announce belief. They acknowledged necessity. At a certain point, the cost of denying black holes became higher than the cost of accepting them. The remaining alternatives strained credibility more than the black hole hypothesis itself. This shift was subtle but decisive. It marked the moment when caution gave way to confidence. Not absolute confidence, but confidence earned through endurance. Black holes were accepted not because science became bold. They were accepted because science remained conservative for so long. This long delay tells us something important. Scientific acceptance is not about speed. It is about resilience under scrutiny. Ideas that survive long enough, across changing data and improving tools, earn their place. Black holes passed that test. Slowly, reluctantly, but thoroughly. And when an idea takes so long to be accepted, what does that tell us about science itself? One truth becomes clear. Science did not accept black holes because it finally saw them. It accepted them because it learned to trust something more demanding than images. Images persuade quickly. They appeal directly to intuition. They feel immediate and complete. But they can also deceive. An image freezes complexity into a single moment. It hides uncertainty behind familiarity. Data does the opposite. Data resists instant belief. It demands patience, comparison, analysis, and an acceptance that conclusions may change. Trusting data means living with uncertainty rather than eliminating it. This is why science often feels unsatisfying to the imagination. It rarely provides closure. It replaces certainty with constraint. But this difficulty is precisely its strength. By choosing data over images, science chooses a harder path, a slower path, a less comforting path, but a more reliable one. In the case of black holes, this choice defined the outcome, long before any image existed. Science had already built confidence through motion, mass, radiation, and consistency. The image, when it eventually arrived, was not a revelation. It was a confirmation, and that distinction matters. It shows that scientific understanding does not wait for what feels convincing. It builds quietly beneath the surface. Black holes became part of modern science not because they were dramatic, but because they endured. They endured scrutiny. They endured doubt. They endured changing tools and improving measurements. This endurance is what data makes possible. Trusting data means accepting that knowledge is provisional. But it also means trusting that this provisional state is not weakness. It is the foundation of modern understanding. Science does not promise final answers. It promises a method that improves with time. And if science requires us to trust what cannot be seen, are we ready to go deeper? The methods that revealed black holes also reveal something else, a boundary beyond which our current physics no longer speaks clearly. We often imagine black holes as objects, dense, massive, violent things tearing matter apart. But the most important feature of a black hole is not something you can touch. It is not made of particles. It is not composed of energy or plasma or exotic matter. The defining feature of a black hole is a boundary we call the event horizon. From a geometric perspective, the event horizon is not a surface in the ordinary sense. It has no material structure, no atoms, no thickness, no physical substance that could be scraped, pierced, or detected directly. The event horizon exists only as a feature of space-time geometry. It is defined entirely by how space-time is curved, and that curvature is described by general relativity. In this theory, gravity is not a force pulling objects together. Gravity is geometry. Mass and energy distort space-time. Objects and light simply follow the paths that geometry allows. The event horizon marks a critical change in those allowed paths. Far from a black hole, light can move freely. It can travel outward, inward, sideways. All directions are available. As space-time becomes more curved, that freedom begins to narrow. The paths that light can take slowly tilt inward, near the event horizon. Escaping outward becomes increasingly difficult. At the event horizon itself, something precise occurs. The geometry of space-time reaches a point where all future directed paths point inward. This includes every possible path that light could take. There is no longer a trajectory that leads outward. Not because light slows down or loses energy, but because outward is no longer a meaningful direction. The event horizon is the location where direction itself changes character. This is why it is called a horizon. Like the horizon on Earth, it is not a place you can point to locally. It depends on the global structure of space. An observer falling toward a black hole would not see a wall. They would not feel a sudden force at the horizon. There is no physical marker announcing the crossing. And yet, once crossed, something irreversible has happened. From that moment on, no signal from that observer can ever reach the outside universe. This is not a limitation of technology. It is not a problem of insufficient energy or speed. It is a consequence of geometry alone. The event horizon does not act. It does not exert force. It does not interact with matter. Yet it permanently separates regions of the universe. Inside and outside become causally disconnected. Information that crosses the horizon is no longer part of the observable universe. All of this arises from a boundary that exists only in our equations. A surface with no substance, no physical construction, only mathematical definition. And yet, its consequences are real. Real for matter, real for light, real for information. This creates a deep tension at the heart of physics. Something that is not a physical object still controls physical outcomes. A boundary that exists only in geometry still determines the fate of everything that crosses it. If the event horizon is only a mathematical boundary, why does crossing it permanently change what the universe can ever know about what falls inside? If we remove the imagery we instinctively attach to black holes, the event horizon immediately stops behaving like a surface. In physics, a surface is something that can be interacted with. You can collide with it, reflect off it, or be slowed by it. A surface produces local effects: pressure, resistance, friction, deformation. The event horizon produces none of these. There is no layer where matter accumulates, no shell where particles crash and pile up, no boundary that objects strike as they fall. An observer falling toward a black hole does not encounter a wall of gravity. Gravity does not suddenly intensify at the horizon. There is no sudden jolt or impact, no physical sensation marking the crossing. From the falling observer's perspective, motion remains smooth and continuous. Their instruments behave exactly as expected. The local laws of physics appear unchanged. This alone rules out the event horizon as a material surface. Any real surface must announce itself locally. The event horizon does not. And yet something profound still changes at that boundary. The change is not mechanical. It is not energetic. It is not dynamical in the usual sense. The change occurs in the ability to transmit information. Before crossing the horizon, signals can still, in principle, escape outward. Light may be delayed and redshifted, but escape remains possible. After crossing, that possibility vanishes completely. No signal sent inward can ever reach the outside universe. This is not due to a lack of energy or speed. It is not a technological limitation. It is enforced by the structure of space-time itself. The event horizon is therefore not a barrier in space. It is a boundary in causality. Inside the horizon, events still happen. Physics still operates locally. But those events can no longer influence anything outside. The future of the outside universe becomes inaccessible. This is why nothing special is felt at the crossing. Causality is not something we feel. It is something the universe enforces silently and globally. A surface would interfere with motion. The event horizon interferes with possibility. Specifically, the possibility that information can ever return. That is why it does not need structure. Geometry alone is sufficient. A rule written into space-time quietly redraws what futures are allowed. Matter passes through without resistance. Time continues forward without interruption. But the universe permanently loses access to whatever has crossed. And if there is no surface, no force, and no physical signal at the event horizon, then what exactly changes at the moment something crosses it? We often describe the event horizon as a point of no return. The phrase sounds dramatic, as if something actively prevents escape. But in reality, nothing is blocking the way. There is no force pulling infinitely hard. No sudden increase in gravitational strength. The point of no return is not created by violence. It is created by geometry. Beyond the event horizon, every possible path through space-time leads inward. Not most paths. All of them. This includes paths taken by matter, paths taken by light, and paths taken by information itself. The reason is subtle but precise. Space-time is not flat near a black hole. It is tilted. The closer you move inward, the more severe that tilt becomes. Outside the horizon, future directions still allow escape. Inside the horizon, the future points only one way. Deeper, this is not a choice made by falling objects. It is not a failure of propulsion or control. Even light, moving at the maximum speed allowed by the universe, cannot resist this geometry. Trying to escape is like trying to move north from the North Pole. The direction simply no longer exists. This is what makes the point of no return absolute. Not because motion is restricted, but because the structure of space-time has redefined what motion means. From inside the horizon, moving forward in time inevitably means moving inward in space. There is no physical maneuver that can reverse this. No engine powerful enough. No technology advanced enough. The point of no return is therefore not an event. It is a condition imposed by geometry. And its most important consequence is not destruction. It is isolation. Once inside, nothing that happens can ever influence the outside universe. Signals cannot cross outward. Causes cannot produce external effects. The black hole becomes causally sealed. This is the true meaning of no return. It is not about falling in. It is about losing the ability to be observed. From the outside, the interior effectively disappears from the universe. Whatever crosses the horizon no longer contributes new information. The flow of knowledge stops at that boundary. This transforms the event horizon into more than a geometric feature. It becomes a limit on observation itself, a place where scientific access ends, not because our instruments fail, but because the universe no longer allows information to escape. And if nothing inside the horizon can ever send information outward, what does that mean for the very idea of scientific observation? Beyond the event horizon, our equations continue to function. They still describe motion. They still predict trajectories. But as we follow those equations deeper inward, something strange begins to appear. A solution that does not behave like any physical quantity we know. The equations produce a singularity. In mathematical terms, a singularity is a point where values diverge. Density increases without bound. Curvature of space-time grows toward infinity. Numbers cease to be finite. At first glance, this looks like an extreme physical prediction. Matter crushed into an infinitely small point. Gravity becoming infinitely strong. But physics has a problem with infinity. Infinite values are not just large numbers. They represent a loss of meaning. When a quantity becomes infinite, the theory can no longer compare it to anything else. The equations stop telling us what happens next. Prediction breaks down. Cause and effect can no longer be traced. This is why singularities are not treated as ordinary objects. They are signals that a model has reached its limit. General relativity was never designed to handle infinite curvature. It assumes space-time is smooth and continuous. A singularity violates that assumption completely. At the singularity, space-time itself stops being well-defined. Distances lose meaning. Time loses its role as an ordering parameter. The mathematical language still produces symbols, but those symbols no longer correspond to physical predictions. This creates an uncomfortable ambiguity. Is the singularity a real physical entity, or is it merely a sign that the theory has broken down? We do not know. Both possibilities remain open. In the history of physics, singularities have often signaled the need for new theories. They mark places where existing frameworks fail. Newtonian gravity breaks down at small scales. Classical physics fails at atomic distances. Each failure pointed toward deeper structure. The singularity inside a black hole may play the same role. It may represent physics we have not yet discovered, or it may represent a region that cannot be described physically at all. What is clear is that our equations do not survive intact. They continue formally, but they lose explanatory power. The singularity is where prediction ends, not because nature becomes chaotic, but because our description of nature stops working. In this sense, the singularity is not deep inside the black hole. It also lies at the edge of our knowledge, a point where theory exceeds its own capacity. The equations keep going, but understanding does not. When mathematics produces infinity, it forces us to confront a choice. Either we have discovered something fundamentally real, or we have encountered a warning that our model is incomplete. And when the equations return infinity, are they revealing a discovery or issuing a warning? When we say that density becomes infinite, it sounds like a concrete statement, as if infinity were simply a very large number. But in physics, infinity is not a measurable quantity. You cannot build an instrument that reads infinity. You cannot compare infinity to any experimental scale. Infinity does not behave like a physical value. It behaves like a breakdown. In most areas of physics, infinity appears when a model is pushed too far. It signals that an approximation has failed, or that key physics has been left out. Classical electrodynamics produced infinite self-energy. That infinity was not physical. It was resolved by quantum theory. In the same way, infinite density inside a black hole may not describe a real state of matter. It may describe the point where general relativity stops applying. Our current physics has no mechanism for handling infinite values. Forces, energies, and densities are assumed to remain finite. When those assumptions fail, prediction fails with them. An infinite density cannot evolve in time. It cannot respond to forces. It cannot be placed within a causal chain. That alone suggests it may not correspond to any physical configuration. Instead, infinity often marks missing structure, a deeper description that has not yet been written. General relativity treats space-time as smooth at all scales, but quantum physics suggests nature is discrete at the smallest scales. Combining these two frameworks remains unresolved. The infinite density may be where that unresolved tension becomes unavoidable. It may indicate that space-time itself has a microscopic structure, or that gravity behaves differently at extreme energies, or that our concept of density breaks down entirely. What matters is that infinity does not answer questions. It blocks them. It tells us where our language stops working. Every time physics encounters infinity, progress follows by removing it, not by accepting it as real. In this sense, infinite density is not a conclusion. It is a question left unanswered, a sign that something essential is missing from our theories. The singularity does not explain nature. It exposes the limits of our explanations. When we encounter infinity, we are not seeing the end of reality. We are seeing the edge of our understanding. And if infinity signals missing knowledge rather than physical reality, then what exactly are we missing? When a physical model works, it does more than describe. It predicts, given initial conditions. It tells us what happens next. It allows systems to evolve in time. It connects abstract mathematics to observable outcomes. At a singularity, each of these functions fails. The equations may still exist on paper, but they no longer determine a unique future. Predictions become undefined. Multiple outcomes are mathematically allowed, or no outcome can be defined at all. Time evolution breaks down. The model cannot tell us how the system changes moment to moment. Cause can no longer be linked to effect. The chain of explanation snaps. Even worse, the model loses contact with observation. No signal from inside the horizon can ever reach us. No measurement can probe the singularity directly. The model makes claims about a region that is forever inaccessible. This breaks a core requirement of empirical science. A theory must, at least in principle, be testable. At the singularity, that principle fails. The problem runs deeper than missing data. The foundational assumptions of the model collapse. General relativity assumes space-time can be described everywhere. It assumes smoothness, continuity, and well-defined geometry. A singularity violates all of these. When assumptions fail, conclusions lose meaning. The model no longer explains. It merely extrapolates symbols beyond their domain of validity. This is what it means for a model to collapse. Not that it becomes false everywhere, but that it stops being applicable in a crucial region. Historically, such collapses are not failures of science. They are signals, warnings that our conceptual framework is incomplete. Newtonian gravity collapses at relativistic speeds. Classical mechanics collapses at quantum scales. In each case, progress came not from forcing the old model further, but from replacing the questions being asked. The singularity tells us not just that predictions fail, it tells us that our way of asking questions may be wrong. We ask, what happens at a point where the theory cannot define happening? We ask for dynamics where time itself loses meaning. The collapse of the model forces a choice. Either we attempt to repair the existing framework, or we rethink the questions we believe physics should answer. And when a model collapses so completely, should science focus on fixing the model, or on fixing the way the question is being asked? General relativity is one of the most successful theories ever constructed. It has passed every experimental test we have been able to perform. From planetary motion to gravitational waves, from GPS satellites to black hole shadows, across an enormous range of scales. Its predictions are extraordinarily precise. This success makes its limitations easy to forget. General relativity handles strong gravity remarkably well. As long as space-time remains smooth, as long as curvature, though large, stays finite. In these regimes, the theory remains stable and predictive. Black hole orbits, accretion disks, gravitational lensing near massive objects. All of these are described accurately by general relativity. The breakdown occurs not with strength, but with extremity. When curvature becomes infinite, when space-time can no longer be treated as continuous, at that point, the mathematical structure of the theory collapses. General relativity was never designed to operate at the smallest scales. It does not include quantum effects. It assumes space-time itself is classical, but near a singularity. Quantum behavior cannot be ignored. Energy fluctuations become unavoidable. The uncertainty principle becomes relevant. Yet general relativity has no way to incorporate these effects. This is not a flaw unique to black holes. The same issue appears at the beginning of the universe. Wherever gravity and quantum mechanics collide, general relativity falters. This tells us something important. General relativity is not wrong. It is incomplete. It is a theory with a domain of validity. Within that domain, it performs exceptionally. Beyond it, the theory makes no promise. This is how physical theories usually behave. They are not final truths. They are approximations that work under specific conditions. The mistake is to treat success as universality. General relativity excels at describing gravity as geometry, but it cannot describe geometry itself becoming quantum. That missing piece is not a small correction. It represents a fundamentally different way of thinking, one where space-time may no longer be smooth, where geometry fluctuates, where the classical picture breaks down. In this sense, general relativity points beyond itself. Its greatest success reveals its deepest limitation. It describes the universe beautifully, but not completely. And if general relativity is not the final theory of gravity, then what essential ingredient is missing from our understanding? There is a scale where classical descriptions inevitably fail, not because the mathematics becomes inconvenient, but because the assumptions beneath it no longer hold. That scale is known as the Planck scale. At this scale, distances approach unimaginably small values. Energies become extreme, and quantum effects can no longer be ignored. In everyday physics, quantum fluctuations average out. Their effects are tiny and statistically smooth, near a singularity. This is no longer true. Fluctuations in energy become violent. The uncertainty principle dominates behavior. Any attempt to localize position increases uncertainty elsewhere. The sharper the measurement, the stronger the disturbance. At these scales, space-time itself cannot remain smooth. The classical picture of a continuous geometry breaks down. Distances fluctuate. Curvature becomes uncertain. The notion of a precise point in space loses meaning. Time itself becomes problematic. Quantum theory does not treat time as an operator. General relativity treats time as part of geometry at extreme scales. These views collide. The result is conceptual tension, not agreement. This is when quantum gravity becomes unavoidable, a theory where gravity itself must be quantized, where space-time is no longer a passive stage, but an active, fluctuating participant. Yet despite decades of effort, no complete theory exists. We have candidates, partial frameworks, mathematical constructions that work in limited regimes, but no unified description that recovers both quantum mechanics and general relativity fully. The difficulty is not technical alone. It is conceptual. Quantum theory assumes a background. General relativity makes the background dynamic. Combining the two requires rethinking what space and time are. This is why the singularity cannot yet be resolved. Not because we lack equations, but because we lack the right conceptual foundation. We know where quantum physics must appear. We know classical descriptions fail there. What we do not yet know is how to merge these worlds consistently. The need for quantum gravity is clear. The path toward it is not. And if we already know, quantum physics must enter the picture. Why has it proven so difficult to combine it with gravity? General relativity and quantum mechanics are both extraordinarily successful. Each has been tested repeatedly within its own domain. Each produces predictions of remarkable accuracy. There is no experiment where either theory is simply wrong. And yet, when forced together, they refuse to fit. The reason is not a small technical mismatch. It is a fundamental difference in how reality is described. General relativity is a continuous theory. Space-time is smooth. Geometry can be subdivided indefinitely. Distances and durations vary continuously. Quantum mechanics, by contrast, is inherently discrete. Energy comes in quanta. States are quantized. Measurement outcomes occur in jumps, not flows. This difference alone creates tension, but the deeper conflict lies in time. In general relativity, time is part of geometry. It bends. It flows differently depending on gravity. There is no universal clock. In quantum mechanics, time plays a very different role. It is an external parameter, a background against which systems evolve. Quantum theory does not describe time itself as uncertain. It assumes time exists independently of what is being observed. When gravity becomes quantum, these assumptions collide. There is no agreed-upon way to define time, no clear notion of evolution, no stable framework for prediction. The conflict extends beyond time. Quantum mechanics describes reality in terms of probabilities. States exist as superpositions. Outcomes are not determined until measurement. General relativity, on the other hand, is deterministic. Given a space-time geometry, motion is fixed. The future follows from the present. Merging these views raises unresolved questions. What does it mean to have a probabilistic geometry? How can space-time fluctuate and still define cause and effect? How does measurement work when the measuring device is part of space-time itself? These are not contradictions within either theory. Each remains internally consistent. The problem arises only when they overlap. At black hole singularities, at the beginning of the universe, wherever gravity and quantum effects are equally strong. In these regions, neither theory can be applied alone, but no consistent combination yet exists. This does not mean reality is inconsistent. It means our descriptions are: we have two powerful lenses. Each reveals part of the universe, but they cannot be used at the same time. The gap between them is not a gap in nature. It is a gap in understanding. And when two theories are both correct, yet fundamentally incompatible, it forces a deeper reflection. If our best descriptions cannot be unified, what does that say about the limits of how we understand reality itself, beyond the event horizon? Physics does not fail all at once. It fades, one concept at a time. The first thing we lose is measurement. There is no experiment that can be performed inside and reported back. No signal can cross the boundary outward. Without measurement, numbers lose their anchor. The second thing we lose is observation. Science depends on observation. Direct or indirect, inside the horizon, neither is possible. We cannot see events. We cannot infer them from their effects. The interior is causally sealed. The third thing we lose is modeling. A model must connect assumptions to predictions. Predictions must, in principle, be checkable. Inside the black hole, this chain is broken. We can write equations. We can extrapolate mathematics. But we cannot validate meaning. This is where language itself begins to fail. Physical language is built from operational concepts. Length is what a ruler measures. Time is what clocks record. Energy is what changes detectors. Inside the horizon, these operations are undefined, not because reality disappears, but because our access to it does. The interior may be filled with structure, or it may not. It may follow laws radically different from anything we know, or it may not admit laws in any familiar sense. We have no way to decide. Our current physical language stops at the horizon. Beyond it, words like inside and location become metaphors. We speak, but we no longer describe. This creates a temptation to speculate freely, to imagine interiors filled with strange objects or new universes. Such ideas are not meaningless, but they are not yet science. Science advances by disciplined restraint, by recognizing where language applies and where it does not. The event horizon is not just a physical boundary. It is a linguistic boundary, a place where description gives way to silence, not because there is nothing to say, but because we do not yet know how to say it responsibly. This is not a failure of science. It is a sign of its honesty. Knowing when to stop speaking is part of understanding. And when science reaches a place without language, it faces a choice. Should it remain silent until new concepts emerge? Or should it speculate beyond what it can justify? When science has no language for what lies inside, should it choose silence or speculation? The absence of description is not the absence of reality. Science has learned this lesson repeatedly. Long before atoms were observed, matter still existed. Long before space-time was formalized, gravity still acted. Knowledge lags behind existence. This is why science allows for the unknown, not as a flaw, but as an honest boundary. The interior of a black hole lies beyond that boundary. We cannot describe it. We cannot measure it. But science does not conclude from this that nothing is there. To deny existence solely because of missing description would be premature. At the same time, science also resists the opposite error. It does not assert what it cannot justify. Without data, speculation remains speculation. This creates a delicate balance between ignorance and belief, between silence and imagination. Science occupies a middle ground. It acknowledges what it does not know, without pretending that ignorance is knowledge, and without pretending that lack of access implies non-existence. This restraint is not weakness. It is methodological strength. Silence, in science, can be meaningful. It marks the edge of justified speech. Beyond that edge, language becomes narrative rather than explanation. The challenge is not to fill the silence too quickly, but to hold it without collapsing into denial or fantasy. The interior of a black hole may contain structure. It may obey unknown laws, or it may defy our current categories entirely. We do not yet know. And acknowledging that uncertainty is not a failure, it is a disciplined stance, one that keeps science open to revision, while protecting it from unfounded certainty. This is the space where progress becomes possible, not by claiming answers too soon, but by refining questions carefully. Between knowing and believing lies scientific humility, and it is this humility that allows science to move forward. When faced with the unknown, science neither turns away nor leaps blindly forward. It waits, it questions, and it prepares new tools and concepts. In the face of what we cannot yet describe, how do we maintain that balance between skepticism and openness? There comes a point where physics can no longer proceed by measurement alone, not because reality disappears, but because access to it does. When no experiment can be performed, when no observation can return information, physics reaches the edge of its operational language. At that edge, questions do not vanish. They change character. They move from what can be tested to what can be examined conceptually. This is where physics naturally touches philosophy, not as a replacement, but as a continuation by other means. Philosophy enters when assumptions must be questioned. What is time? What is causality? What does existence mean without observation? These are not experimental questions, but they are not meaningless either. Physics relies on them implicitly. Every equation assumes a notion of reality. Every prediction assumes a notion of time. When those assumptions fail, physics alone cannot repair them. This does not mean physics becomes philosophy, and philosophy does not replace physics. The two serve different roles. Physics tests what can be tested. Philosophy examines what makes testing meaningful. At the event horizon, physics identifies a boundary. Philosophy asks what it means to have such a boundary. At the singularity, physics signals breakdown. Philosophy asks whether the concept itself still applies. This interaction is not a retreat. It is a sign of depth. When a science reaches its limits, reflection becomes necessary. Ignoring those limits leads to confusion. Overstepping them leads to speculation disguised as fact. The discipline lies in knowing where each mode of thinking belongs. Physics defines where reliable knowledge ends. Philosophy explores what remains meaningful beyond that point. Together, they prevent two extremes: blind positivism and unconstrained speculation. The boundary between them is not fixed. It shifts as knowledge grows. What was once philosophy can become physics, but only when new tools emerge. Until then, restraint matters. The interior of a black hole forces us to confront this balance. It is not just a physical mystery. It is a conceptual one, a reminder that understanding is layered, and that not every question is answered in the same way. When physics reaches philosophy, it is not lost. It is pausing, re-examining its foundations, preparing for the next step forward. And when physics touches philosophy at its limits, are we advancing toward deeper understanding, or wandering beyond what knowledge can support? A black hole is often introduced as an astronomical object, something massive, distant, exotic. But its true significance does not lie in where it is. It lies in what it does to our theories. A black hole is not just something we observe. It is something that tests the act of observation itself. Every major framework of physics is forced to confront its limits near a black hole. General relativity performs brilliantly, then breaks. Quantum mechanics explains matter, but loses space-time. Observation reaches a boundary it cannot cross. Measurement becomes impossible. Prediction becomes ambiguous. Explanation becomes conditional. In this sense, the black hole is not merely an object in the universe. It is a mirror held up to our understanding. It reflects the limits of our tools, telescopes, detectors, mathematical formalisms, and more importantly, it reflects the limits of our concepts: space, time, causality, information. These ideas work extraordinarily well almost everywhere else. Near a black hole, they begin to strain. Not all at once, but inevitably. This forces science into an unfamiliar posture. Not expansion, but reflection. A recognition that progress is not always about pushing forward. Sometimes it is about understanding where to stop. The black hole marks such a stopping point. Not permanently, but for now. It tells us where current theories no longer speak clearly, where language loses precision, where questions must be reformulated. This does not diminish science. It deepens it. A theory that knows its limits is stronger than one that pretends to have none. The black hole demands that honesty. It forces science to look back at itself, to examine not just what it knows, but how it knows. In that role, the black hole becomes more than a phenomenon. It becomes a boundary of knowledge, a place where understanding pauses, not because nature ends, but because our current descriptions do. How we respond to that pause matters. We can treat it as a barrier, or as an invitation to rethink assumptions, to refine concepts, and to develop new ways of asking questions. If black holes represent a limit of understanding rather than a failure of it, then how should we approach that limit? Science is often praised for how far it goes, how much it explains, how many mysteries it dissolves. But there is another measure of scientific strength that is rarely emphasized: knowing where to stop. Scientific honesty does not come from having answers to everything. It comes from recognizing when answers are not yet justified. There are moments when the most responsible statement science can make is simple: we do not know. This is not a retreat. It is an act of precision, to speak only where language remains anchored to evidence, and to remain silent where it does not. The temptation to fill gaps is always present. When observation fails, imagination offers itself readily. Stories feel satisfying where equations fall silent. But science is defined by restraint, not creativity alone. Filling a gap with speculation does not advance understanding. It only creates the illusion of closure. True honesty requires resisting that illusion. Another form of dishonesty is more subtle: forcing data to answer questions it was never meant to address, stretching models beyond their domain of validity, treating extrapolation as explanation. This too undermines scientific integrity. A model earns trust by knowing its limits. When those limits are crossed, confidence should decrease, not increase. In the context of black holes, this distinction matters deeply. We can describe what happens outside the horizon with extraordinary accuracy. We can track orbits, measure waves, predict emissions. But when we reach the interior, our tools fall silent. The honest move is not to invent detail. It is to mark the boundary clearly. Here is where our models stop applying. Here is where prediction loses meaning. And here is where further claims require new foundations. Accepting not knowing is not intellectual surrender. It is strategic patience. Every major leap in physics began with clearly identified ignorance. Classical mechanics ended when its limits were exposed. Quantum theory began there. The same pattern holds across scientific history. Progress is not made by pretending the unknown is understood. It is made by protecting the unknown from premature explanation. There is a discipline to stopping at the right point. It requires confidence without overreach, curiosity without compulsion, and humility without paralysis. To say we do not yet know is to leave the question alive. To answer too soon is often to kill it. In this sense, stopping is not the opposite of progress. It is one of its necessary forms. The black hole demands this kind of honesty. It challenges not just our theories, but our scientific character, to speak where we can justify, to remain silent where we cannot, and to leave space for future understanding. In the end, the question is not whether science can always move forward, but whether it can recognize when stopping is the most honest move it can make. And is choosing to stop at the right moment more difficult than offering an answer simply because one is expected? In everyday language, not knowing is often treated as failure, a gap to be closed as quickly as possible, an embarrassment to be corrected. In science, the opposite is often true. Not knowing can be a sign of progress. It means a boundary has been reached, honestly, a point where old tools stop working, and where pretending otherwise would distort understanding. The phrase "we do not yet know" carries weight. It acknowledges ignorance without surrender. It keeps the question open without forcing an answer. This intermediate state is not empty. It is fertile. It creates space for new ideas to form, for new mathematics to be developed, for new concepts to emerge. Historically, every major advance in physics passed through such a phase. Before quantum mechanics, classical physics admitted its breakdown. Before relativity, Newtonian space and time were questioned. In each case, progress began with restraint, with the refusal to explain too much using inadequate tools. The black hole places us in exactly such a position. We know enough to see the limits, but not enough to go beyond them responsibly. Declaring certainty here would be premature. Declaring impossibility would be equally so. The productive stance lies between to say we do not yet know what lies inside, and to mean it seriously. This protects science from illusion, from mistaking elegant speculation for established knowledge, from confusing mathematical extension with physical reality. Saying "not yet" is a safeguard. It prevents conclusions from hardening too early. It keeps theories revisable and science alive. There is courage in this position. It resists pressure to perform certainty. It accepts temporary incompleteness in exchange for long-term depth. Accepting not knowing does not mean stopping inquiry. It means redirecting it, from answering questions prematurely to building better questions, from forcing conclusions to refining the conditions under which conclusions could one day be drawn. In this sense, not knowing is not the absence of understanding. It is understanding in a suspended state, waiting for the right framework to arrive. The black hole teaches this lesson with unusual clarity. It shows us where knowledge ends honestly, and where patience becomes a scientific virtue. To accept we do not yet know is to leave the door open, not to fantasy, but to deeper understanding in the future. Progress does not always mean moving forward immediately. Sometimes it means standing still deliberately, marking the edge clearly, and preparing for the next leap with care. In that light, accepting not knowing is not resignation. It is one of the clearest signs that science is working as it should. And if science is strongest when it knows when to stop, what happens when we choose to step forward into even larger black holes? Reaching the limits of our theories does not mean all black holes challenge us in the same way. Before looking at the most extreme cases, we need to understand that black holes themselves are not a single phenomenon. Stars are often described as long-lived beacons of stability. But this impression hides a deeper truth. A star is not a permanent object. It is a temporary balance, sustained only as long as internal processes can resist its own gravity. From the moment a star is born, its future is already shaped by one defining property: mass. Mass determines how a star lives because it governs the intensity of gravity pulling inward. The greater the mass, the stronger the gravitational force that must be countered. To survive, a massive star must generate enormous internal pressure, achieved by burning its nuclear fuel at an extraordinary rate. This makes such stars intensely bright, but it also seals their fate. Contrary to intuition, massive stars do not live longer. They live faster. Their immense energy output comes at a cost. Nuclear fuel is consumed rapidly, sometimes in only a few million years, on cosmic timescales. This is a fleeting existence. The brighter and heavier the star, the sooner it approaches the end of its life. Nuclear fusion is not merely a source of light. It is the mechanism that holds the star up against gravitational collapse. As long as fusion continues in the core, the outward pressure it produces balances gravity's inward pull. But nuclear fuel is finite, and when it begins to run out, that balance starts to weaken. For stars with modest mass, this transition is relatively gentle. But for the most massive stars, the loss of nuclear support is far more dramatic. Gravity does not slowly reclaim control, it surges inward. The star's internal structure can no longer maintain equilibrium, and the long-standing tension between pressure and gravity finally breaks. At this stage, the star has reached the end of its evolutionary path. There is no replenishment of fuel, no mechanism left to restore the balance that once sustained it. What follows is not random, and it is not the same for all stars. The outcome depends entirely on how massive the star was at birth. This is why black holes are not the inevitable destiny of all stars. Only those born with enough mass even approach that possibility. Most stars simply never cross that threshold. Their endings are written within different limits, governed by different physical constraints. And so, at the moment when nuclear fuel is exhausted and gravity begins to dominate, the story does not end. In fact, it reaches a turning point. When a star can no longer hold itself up, what happens next? When a massive star exhausts its nuclear fuel, gravity does not immediately create a black hole. What begins instead is a rapid and profound restructuring of the star's core. Fusion reactions that once produced outward pressure fade away, and with them disappears the only force capable of resisting gravitational collapse. For the first time since the star was born, gravity acts without opposition. As the core begins to collapse, matter is driven inward at extraordinary speeds. Atoms are crushed, electrons are forced into protons, and the internal structure of matter itself changes. This is not a gentle contraction, but a runaway process. Each moment of collapse increases density, and greater density strengthens gravity even further. The inward pull feeds on itself. For a brief time, physics attempts to halt this collapse. In some stars, new forms of pressure emerge as matter is compressed to extreme densities. These pressures can, under certain conditions, establish a new equilibrium and stop the collapse. But this outcome is not guaranteed. There is no universal safety net written into the laws of nature. When the mass of the collapsing core is sufficiently large, no stable configuration remains available. Gravity overwhelms every known source of internal pressure. The collapse does not pause, does not reverse, and does not settle into a long-lived remnant. Instead, it continues inward without a stopping point that physics can currently describe. As collapse proceeds, matter is compressed into an ever smaller region of space. Distances lose their familiar meaning. Densities rise beyond anything that can exist in ordinary environments. Eventually, the collapsing core crosses a critical threshold, a boundary beyond which escape is no longer possible. From that moment on, the object has become what we call a stellar mass black hole. In this sense, stellar black holes are not exotic anomalies. They are the natural outcome when gravity is allowed to complete its work without interruption. No new physics needs to be invoked at the moment of formation. The same gravitational laws that shape stars and planets continue to operate, simply pushed to their most extreme limit. Yet it is crucial to recognize that not every collapsing star follows this path. Many stars reach the end of their lives without ever forming a black hole. Their collapse is halted earlier, stabilized by pressures that remain sufficient to counter gravity. These stars leave behind dense remnants. But gravity never gains absolute control. This distinction matters because it reveals that black hole formation is not a binary switch that flips on at the end of every massive star's life. It is a threshold phenomenon. Cross the threshold, and collapse becomes unstoppable. Remain below it, and an entirely different kind of object is left behind. Stellar mass black holes then represent one branch of stellar death, not the endpoint of all stellar evolution. They mark the cases where gravity wins completely, where no stable balance can be restored. But understanding where that line is drawn remains one of the most important questions in astrophysics. What determines whether a star becomes a black hole or not? To understand where the line is drawn between collapse and survival, we need to examine one of the most extreme objects that can still resist gravity, the neutron star. A neutron star is not a transitional phase. It is a final, stable configuration, at least under the right conditions. It represents the last known state in which matter can oppose gravitational collapse without disappearing behind an event horizon. Neutron stars are born from the same catastrophic collapses that can create black holes, but in these cases, the inward fall of matter is halted at an extraordinary density. The core is compressed until protons and electrons merge, forming a sea of neutrons packed together more tightly than atomic nuclei. What remains is an object only tens of kilometers across, yet more massive than the Sun. The force that halts collapse at this stage is not ordinary pressure. It arises from the fundamental rules of quantum physics. Neutrons, like all fermions, obey a principle that forbids them from occupying the same quantum state. As they are squeezed closer and closer together, this restriction generates an immense resistance known as neutron degeneracy pressure. For a time, this pressure is enough. It establishes a new balance, one far more extreme than anything seen in ordinary stars. Gravity continues to pull inward, but neutron degeneracy pressure pushes back with equal intensity. The result is a neutron star stable, compact, and incredibly dense. But this resistance is not unlimited. Neutron degeneracy pressure has a ceiling. As mass increases, gravity strengthens faster than the pressure can respond. Beyond a certain point, squeezing neutrons closer together no longer produces enough resistance to counter the inward pull. The balance that once held now begins to fail. This limit is not determined by astronomy alone. It is set by the behavior of matter at densities far beyond those we can reproduce on Earth. It depends on the properties of neutrons, the interactions between particles, and the equations that describe matter under extreme compression. In other words, it is a boundary written into particle physics itself. When a collapsing stellar core exceeds this maximum allowable mass, there is no known force left to intervene. Thermal pressure has long since vanished. Neutron degeneracy pressure can no longer keep pace. Gravity, once again, becomes unstoppable. At that point, the outcome is no longer ambiguous. The collapse does not search for another stable state. There is no next layer of resistance waiting beneath. The only remaining path allowed by physics is continued collapse, leading inevitably to the formation of a black hole. In this way, black holes emerge not as exotic alternatives, but as the consequence of exceeding nature's final line of defense. They are what happens when even the most extreme known form of matter can no longer resist gravity's pull. Yet this raises a subtle and intriguing possibility. If there is a precise limit separating neutron stars from black holes, then the universe may contain objects that exist right on the edge so close to the boundary that the distinction becomes blurred. If such a limit exists, could there be black holes that sit right at its edge? If black holes formed only at the scale of dying stars, and if supermassive black holes existed only at the centers of galaxies, the cosmic picture would be relatively simple. But observations suggest a far more complex reality. Between stellar mass black holes and supermassive black holes lies a vast gap in mass, one that theory says should not be empty. This intermediate range spans black holes hundreds to hundreds of thousands of times more massive than the Sun. In many models of cosmic evolution, such objects play a crucial role. They could act as stepping stones, linking the deaths of massive stars to the growth of the giant black holes that anchor entire galaxies. From a theoretical standpoint, their existence seems almost unavoidable. If black holes can merge, and if mass can accumulate over time, then intermediate mass black holes should naturally arise. They could form from repeated mergers of stellar mass black holes, or from the direct collapse of unusually massive stars in the early universe. On paper, the pathways are clear. Yet when astronomers look to the sky, the picture becomes far less certain. Stellar mass black holes are routinely detected through their interactions with nearby matter. Supermassive black holes reveal themselves through the dramatic activity at galactic centers. But intermediate mass black holes remain elusive, appearing only as hints rather than definitive detections. This absence is not easily dismissed. If intermediate mass black holes truly exist in large numbers, we would expect to see them more clearly. Their apparent scarcity raises uncomfortable questions. Are they genuinely rare, forming only under exceptional circumstances, or are our instruments and methods simply not well suited to finding them? Part of the difficulty lies in their ambiguous nature. Intermediate mass black holes are too massive to behave like ordinary stellar remnants, yet too small to dominate entire galaxies. They do not easily announce their presence. Without abundant surrounding matter to feed on, they remain dark and quiet, blending into their environments. Their uncertain origins add another layer to the puzzle. If they form from direct collapse, they may appear suddenly and without dramatic signatures. If they grow through mergers, their history becomes fragmented, leaving behind subtle clues that are difficult to reconstruct. In either case, distinguishing an intermediate mass black hole from other compact objects is a formidable challenge. And yet, these objects matter deeply. Without them, the rapid growth of supermassive black holes in the early universe becomes harder to explain. They may represent the missing link in a chain that connects stellar death to galactic architecture. Ignoring them risks leaving a gap in our understanding of how structure emerges on the largest scales. For now, the problem remains unresolved. Intermediate mass black holes occupy a space where theory is confident, but evidence is fragile. They exist comfortably in equations, yet uneasily in observations. This tension marks them as one of the most intriguing open questions in modern astrophysics. If intermediate mass black holes do exist, why are they so difficult to see? If intermediate mass black holes are as important as theory suggests, their absence from clear observations demands an explanation. The difficulty does not stem from a single limitation, but from a combination of factors that place these objects in an observational blind spot. They sit in a regime where none of our usual detection strategies work especially well. On the largest scales, supermassive black holes reveal themselves by shaping entire galaxies. Their gravity organizes stars, gas, and dust, and their energetic output can be seen across vast cosmic distances. Intermediate mass black holes lack this influence. They are simply not massive enough to leave an unmistakable imprint on galactic structure. At the opposite end of the spectrum, stellar mass black holes often betray their presence through close interactions. When they pull matter from a companion star, that material heats up and emits strong X-ray signals. Intermediate mass black holes, however, rarely sit in such convenient configurations. They are too massive to behave like typical stellar remnants, yet too isolated to generate dramatic emissions. As a result, many intermediate mass black holes are expected to be quiet, without a steady supply of infalling matter. They emit little or no radiation. In astronomical terms, they are effectively invisible. Detecting them requires indirect methods, looking not for light, but for subtle gravitational effects on their surroundings. These indirect signals are difficult to interpret. A cluster of stars moving slightly faster than expected, a brief flare of radiation, or an unusual pattern in gravitational waves can all hint at the presence of an intermediate mass black hole. But none of these clues are definitive on their own. Each can often be explained by alternative scenarios that do not involve a black hole at all. The environments where intermediate mass black holes are expected to reside further complicate matters. Denser star clusters, galactic outskirts, and chaotic regions of gas all introduce noise into observations. Signals overlap, backgrounds fluctuate, and separating cause from coincidence becomes extraordinarily challenging. This is why the field is filled with candidates rather than confirmations. Over the years, astronomers have identified numerous objects that could be intermediate mass black holes. Each candidate satisfies some criteria, yet falls short of absolute proof. The evidence accumulates slowly, never quite crossing the threshold of certainty. This situation creates a subtle tension in science. When theory predicts something strongly, but observations remain ambiguous. The problem may lie in nature or in our tools. History offers examples of both. Some predicted objects were later confirmed with better instruments. Others faded away as models were refined. With intermediate mass black holes, we stand precisely at this crossroads. The signals are suggestive. The implications are significant, yet the evidence remains incomplete. The question is no longer purely about what exists in the universe, but about how we choose to interpret what we see. When an object is difficult to observe, should we doubt its existence? Or should we question our methods? When astronomers first began to detect supermassive black holes in the distant universe, the surprise was not their size, but their timing. These objects were not found in a mature, ancient cosmos. They appeared when the universe itself was still remarkably young, only a fraction of its current age. Some of these black holes already contained billions of times the mass of the Sun, less than 1 billion years after the Big Bang. On human timescales, that interval feels immense. On cosmic timescales, it is extraordinarily short. The existence of such massive objects so early poses an immediate problem. According to the simplest models, black holes grow gradually. They begin as smaller remnants, then gain mass by accreting surrounding matter or merging with other black holes. But this process is limited. There is only so much material available, and there are physical limits on how fast matter can fall inward. When these constraints are applied, the timeline no longer works. Starting from stellar mass black holes, there simply is not enough time for them to grow into billion solar mass giants so early in cosmic history. The numbers refuse to align. Something does not fit. This mismatch suggests that the formation of supermassive black holes may not follow a single, slow pathway. Instead, their origins may involve more dramatic beginnings. Rather than growing patiently from small seeds, some black holes may have started life already massive. One idea is that enormous clouds of primordial gas collapse directly, bypassing the normal stages of star formation. In such a scenario, gravity would act on a scale far larger than that of individual stars, creating a massive black hole seed in a single event. This would dramatically shorten the growth timeline. Another possibility involves unusually massive early stars, far larger than those commonly seen today. If such stars formed in the dense, metal-poor environment of the early universe, their collapse could produce black holes much heavier than typical stellar remnants. These, in turn, would have a head start in the race towards supermassive scales. None of these ideas has yet emerged as the definitive answer. Each comes with uncertainties, assumptions, and unresolved questions. What they share, however, is an acknowledgement that something unusual must have occurred in the early universe. The standard picture is incomplete. The early appearance of supermassive black holes does more than challenge models of black hole growth. It reaches into the foundations of cosmology itself. It forces us to reconsider how structure formed, how matter behaved, and how quickly complexity emerged after the universe began. These objects act like time capsules from the universe's youth. They preserve clues about conditions that no longer exist and processes that may no longer operate in the same way. Understanding them is not just about black holes, but about the earliest chapters of cosmic history. And so the question becomes unavoidable. If supermassive black holes were already in place when the universe was young, then their origin must lie in mechanisms that go beyond slow, incremental growth. If supermassive black holes appeared so early, where did they come from? As observations of galaxies became more precise, astronomers began to notice a striking pattern. The mass of a galaxy's central black hole was not arbitrary. Instead, it appeared closely linked to properties of the galaxy itself, particularly the mass and motion of stars in its central region. This correlation emerged across many different types of galaxies, suggesting an underlying connection rather than coincidence. The implication was difficult to ignore. If black holes and galaxies were entirely independent, Such a consistent relationship would be unlikely. Yet the data repeatedly pointed in the same direction. Larger galaxies tended to host more massive black holes, while smaller galaxies housed comparatively lighter ones. The growth of one seemed to track the growth of the other. This realization shifted how scientists thought about black holes. Rather than being passive objects buried in galactic centers, black holes began to look like active participants in galactic history. Their growth appeared intertwined with the assembly of stars, gas, and structure on much larger scales. One interpretation is that galaxies and black holes evolve together. As galaxies gather mass through mergers and accretion, their central black holes grow as well. At the same time, processes near the galactic center may influence how stars form and how gas is distributed, subtly shaping the galaxy's future. However, correlation alone does not reveal causation. The observed relationships tell us that black holes and galaxies are connected, but not how that connection works. It remains unclear whether black holes drive galactic evolution, whether galaxies regulate black hole growth, or whether both are shaped by deeper, shared processes. In some galaxies, black hole activity appears intense, coinciding with periods of rapid star formation or violent mergers. In others, the central black hole remains comparatively quiet, even as the galaxy continues to evolve. These differences hint that the relationship is not fixed, but dependent on environment, history, and timing. This uncertainty has become one of the central questions in modern astrophysics. Understanding how black holes and galaxies influence each other is essential for explaining why the universe looks the way it does today. Without that understanding, our picture of cosmic evolution remains incomplete. The challenge lies in disentangling cause from effect across billions of years. Observations capture only snapshots in time, while the processes involved unfold slowly and unevenly. Reconstructing that history requires not only better data, but also careful interpretation. What is clear is that black holes and galaxies cannot be treated as separate stories. Their histories are intertwined, even if the direction of influence remains uncertain. To move forward, we must ask a more fundamental question about who is shaping whom. Do black holes shape galaxies? Or do galaxies feed black holes? At first glance, the relationship between a black hole and its host galaxy appears straightforward. Galaxies contain vast reservoirs of gas and dust, and gravity naturally draws some of this material inward. Over time, a fraction of it spirals toward the galactic center, where it can be captured by the central black hole. In this picture, galaxies seem to act as suppliers, steadily feeding their black holes. Observations confirm that this inward flow does occur. Gas clouds lose angular momentum, stars are disrupted, and matter falls toward the black hole, forming a hot, rapidly rotating disk. As material sinks deeper into the gravitational well, the black hole gains mass and grows. Without the surrounding galaxy, this growth would not be possible. But this is only half of the story. As matter falls inward, it does not simply disappear quietly. The process of accretion releases enormous amounts of energy. Some of this energy emerges as intense radiation, while some is carried away by powerful jets and outflows that can extend far beyond the central region of the galaxy. This outward energy flow means that black holes do not merely consume their environment, they also influence it. Radiation can heat surrounding gas, preventing it from cooling and forming new stars. Jets can push material away, reshaping the distribution of gas on galactic scales. In extreme cases, black hole activity can slow or even suppress star formation across large regions. This creates a feedback loop. The galaxy feeds the black hole. The black hole releases energy, and that energy alters the galaxy's future. The process is inherently two-way. Growth on one side modifies conditions on the other, often in subtle and delayed ways. Because of this, there is no single, universal answer to the question of dominance. In some environments, especially during periods of intense accretion, black holes appear to exert a strong influence, regulating how much gas remains available for star formation. In other situations, the galaxy's large-scale structure and gas supply seem to dictate how much the black hole can grow. Timing also matters. A black hole may be relatively quiet for most of a galaxy's life, exerting little influence, only to become briefly active during mergers or inflows of gas. During those episodes, its impact can be profound, even if short-lived. This complexity makes the relationship difficult to disentangle. Cause and effect are intertwined across vast spans of time and space. What appears to be control in one snapshot may look like dependence in another. The balance shifts as conditions change. Rather than asking which side dominates in all cases, astronomers are increasingly focusing on how this interaction operates under different circumstances. The answer appears to depend on mass, environment, cosmic epoch, and the availability of matter. This two-way relationship reframes the problem. Black holes are neither simple parasites nor absolute rulers. They are participants in a complex exchange, shaped by their surroundings even as they shape them in return. If the relationship runs both ways, how do we determine which side is in control? For a long time, black holes were described primarily as consumers. They pull matter inward, strip it of energy, and lock it away behind an event horizon. In this view, black holes appear as endpoints, cosmic sinks where matter and information vanish from the visible universe. But this picture captures only part of what actually happens. Before matter crosses the point of no return, it must pass through an environment of extreme gravity and motion. As gas spirals inward, it heats up, accelerates, and releases vast amounts of energy. This energy does not disappear. It escapes into the surrounding galaxy, sometimes with enough force to rival the combined output of billions of stars. This outward flow of energy is known as feedback. It can take many forms: intense radiation, fast-moving winds, or narrow jets that punch through interstellar gas. Regardless of its form, feedback represents a channel through which black holes communicate with their environment. One of the most significant consequences of feedback is its impact on star formation. By heating surrounding gas or pushing it away from dense regions, black hole activity can slow the collapse of gas clouds that would otherwise form new stars. In some galaxies, periods of intense black hole activity coincide with a sharp decline in star formation. Feedback does not only affect how many stars form, but also where and when they form. By redistributing gas on large scales, it can reshape the internal structure of a galaxy. Regions once rich in star-forming material may be depleted, while other regions are stirred or compressed. Over time, this process alters the evolutionary path of the entire system. Importantly, feedback introduces regulation into cosmic growth. Without it, galaxies might convert gas into stars too quickly, becoming far more massive and compact than we observe. Black hole feedback provides a braking mechanism, preventing runaway growth and helping to produce the diversity of galaxies seen today. This realization has reshaped theoretical models. Feedback is no longer treated as a secondary detail, but as a central ingredient in simulations of galaxy formation. Models that ignore it fail to reproduce the universe we see. Those that include it come closer to matching observations. At the same time, feedback complicates the narrative of black holes as mere endpoints, an object capable of influencing star formation. Gas dynamics and galactic structure cannot be viewed as passive. Its effects propagate outward, long after matter has fallen inward. In this light, black holes appear less like cosmic graves and more like active agents. They participate in shaping their surroundings, sometimes gently, sometimes violently, but always in ways that leave lasting marks on their host galaxies. Understanding feedback is therefore essential. It connects the small-scale physics of accretion near a black hole to the large-scale evolution of galaxies. It is the bridge between the extreme and the familiar, between collapse and structure. And this reframing leads to a deeper question. If black holes actively shape their environment through feedback, then their role in the universe may be far broader than that of a final state. If feedback is so important, are black holes really just an ending? For much of the 20th century, black holes were treated as cosmic endpoints. They marked the end of a star's life, the final outcome of gravitational collapse, after which nothing of significance seemed to happen. Once formed, a black hole appeared to simply exist unchanging, isolated, and largely irrelevant to the broader evolution of the universe. That perspective is now steadily giving way to a different understanding. Observations and models increasingly suggest that black holes do not simply mark the end of a process. They can initiate new ones. Their presence can influence environments over vast distances and over timescales far longer than the lives of the stars that created them. Once a black hole forms, it becomes a long-lived feature of the cosmic landscape, unlike stars, which exhaust their fuel and fade. Black holes can persist for billions of years. During that time, they continue to interact with their surroundings, responding to changes in their environment and, in turn, shaping it. This influence is not limited to dramatic outbursts of energy. Even in quieter phases, the gravitational presence of a black hole affects how matter moves nearby. Gas flows, stellar orbits, and the stability of surrounding structures all feel its pull. Over long periods, these subtle effects accumulate. On larger scales, the role of black holes becomes even more significant. Through feedback processes, they can regulate the growth of galaxies, influence when and where stars form, and help establish the large-scale properties that distinguish one galaxy from another. In this context, black holes act less like remnants and more like regulators. This shift in perspective reframes black holes as participants in cosmic evolution. They are shaped by the conditions that create them, but they also feed back into those conditions, altering the trajectory of matter and energy around them. Cause and effect blur across time. In this sense, black holes are no longer just the outcome of stellar evolution. They are agents within a larger system, capable of influencing structures far beyond their immediate vicinity. Their effects can ripple outward, shaping environments that span thousands or even millions of light years. This does not mean that black holes dominate the universe. Their influence is conditional, dependent on mass, environment, and timing. But it does mean that treating them as passive endpoints misses a crucial part of the story. By recognizing black holes as active components, we gain a more dynamic picture of the cosmos. Evolution becomes not a one-way march from birth to death, but a network of interactions in which even the most extreme objects play ongoing roles. This expanded role invites us to reconsider how far the influence of black holes might reach. If they are not merely consequences, but participants, then their significance may extend well beyond the places where they formed. When black holes become agents rather than endpoints, how far does their role extend? When black holes are viewed only as isolated objects, their significance seems limited to their immediate surroundings. But once we step back and examine the universe as a connected system, a broader picture emerges. Black holes influence not just local environments, but the way matter is arranged and reorganized across cosmic scales. At the heart of galaxies, black holes help shape the distribution of gas and stars. Through gravity and energy release, they influence where matter settles, where it is displaced, and how it circulates over time. These effects leave imprints on galactic structure that persist long after individual events have faded. This influence extends into the cycle of star formation. By regulating the availability and temperature of gas, black holes indirectly determine when stars can form and when that process is suppressed. Over billions of years, these small adjustments accumulate, shaping the stellar population of entire galaxies. Beyond individual galaxies, black holes may also contribute to larger-scale patterns. By influencing how galaxies grow and evolve, they indirectly affect how matter is distributed across galaxy groups and clusters. Their role becomes part of a cascading chain, linking small-scale physics to large-scale cosmic architecture. Importantly, these effects operate across very different scales of space and time. Near a black hole, processes unfold over distances comparable to the size of a solar system. At the level of galaxies, the consequences stretch across tens of thousands of light-years. On cosmic scales, the influence can persist for billions of years. This multi-scale role makes black holes difficult to categorize. They are not merely small-scale phenomena, nor are they dominant architects acting alone. Instead, they operate as connectors, translating extreme physics into gradual, large-scale change. Because of this, black holes cannot be cleanly separated from the broader story of structure formation. Their effects are woven into the same processes that shape galaxies, clusters, and the cosmic web itself. To remove them from that narrative would leave critical gaps. This realization encourages a more integrated view of the universe. Instead of treating black holes as special cases, we begin to see them as components embedded within a continuous hierarchy of structures, each influencing the others. In that context, the question shifts. If black holes participate in structure formation across so many scales, then grouping them under a single, simplified description may obscure more than it reveals. If their roles span so many scales, can we really treat all black holes as one category? As our view of black holes has expanded, it has become increasingly clear that treating them as a single phenomenon is no longer sufficient. Objects that share the same name can arise from fundamentally different physical processes, operate on vastly different scales, and pose entirely different scientific questions. The similarities that once united them now sit alongside deep and consequential differences. Stellar mass black holes are the most direct to interpret. Their origin is closely tied to stellar evolution. They represent the endpoint of massive stars that exhaust their fuel and collapse under their own gravity. In this case, black holes are the predictable outcome of well-understood processes, governed by the balance between gravity and known forms of pressure. Intermediate mass black holes occupy a more ambiguous position. They appear to bridge the gap between stellar remnants and galactic giants. Yet their formation pathways remain uncertain. They could grow through mergers, form through unusual collapses, or arise through combinations of processes we have not yet fully traced. Each possibility carries different implications for cosmic history. Supermassive black holes, by contrast, raise questions that reach beyond stellar physics altogether. Their sheer size and early appearance challenge simple growth models and point toward conditions that may have existed only in the universe's earliest epochs. Here, the problem is not how stars die, but how structure begins. Each category, then, carries its own set of puzzles. Stellar black holes test our understanding of extreme matter and collapse. Intermediate mass black holes probe the missing links of cosmic evolution. Supermassive black holes confront us with questions about the origins of galaxies and the early universe itself. Attempting to explain all black holes with a single mechanism risks flattening these distinctions. A model that works well for one class may fail entirely for another. What appears as a natural outcome in one context can become a profound mystery in another. This realization changes how questions are framed. Instead of asking what black holes are in general, scientists increasingly ask which black holes formed how and under what conditions. Precision replaces generalization. Context becomes as important as classification. In this light, classification is not a matter of labels. It is a way of preserving information about origin, evolution, and influence. By distinguishing between types, we avoid forcing fundamentally different objects into the same conceptual box. The diversity of black holes reflects the diversity of the universe itself. Different conditions give rise to different outcomes, each revealing a different facet of how gravity, matter, and time interact. Understanding this diversity is essential for building a coherent picture of cosmic evolution. And yet, this raises a final, more reflective question. If each type of black hole represents a distinct mechanism and a distinct mystery, then the act of grouping them together becomes less straightforward. If each type carries its own questions, does classification still help us understand black holes at all? As our understanding of black holes deepens, one lesson becomes increasingly difficult to ignore. No single model can capture the full range of phenomena that fall under the name black hole. What works well in one context often breaks down in another. Not because the theory is flawed, but because the objects themselves are fundamentally different. A model designed to describe the collapse of massive stars cannot automatically explain the origin of billion solar mass black holes in the early universe. Likewise, assumptions that hold for quiet stellar remnants may fail entirely when applied to actively accreting galactic centers. Each scenario imposes its own conditions and constraints. When these differences are overlooked, simplification becomes a liability. By forcing diverse phenomena into a single framework, we risk erasing the very features that carry the most information. Important clues about formation, evolution, and interaction can be lost in the process. This kind of overgeneralization can also lead to misunderstanding. Conclusions drawn from one class of black holes may be mistakenly applied to another, creating apparent contradictions where none actually exist. What looks like a failure of theory may instead be a failure of categorization. History shows that progress in science often comes from recognizing when distinctions matter. Stars were once treated as broadly similar objects until classification revealed profound differences in mass, composition, and life cycle. That shift unlocked a deeper understanding of stellar evolution. Black holes appear to demand a similar shift. Treating them as a single category may be useful at the most basic level, but it quickly becomes limiting as questions grow more precise. To move forward, we must allow our descriptions to reflect the diversity we observe. This does not mean abandoning simplification altogether. Models are essential tools, and abstraction is necessary for understanding complex systems. The challenge lies in knowing when a simplification clarifies reality, and when it begins to distort it. In the case of black holes, the cost of excessive simplicity is particularly high. These are extreme objects, shaped by conditions that push physics to its limits. Small differences in origin or environment can lead to radically different outcomes. Recognizing these distinctions is not a complication for its own sake. It is a way of preserving accuracy and avoiding false certainty. By keeping categories separate where necessary, we maintain the flexibility to refine our theories as new data emerges. Ultimately, understanding black holes requires a balance between unity and diversity. We seek common principles, but we must remain alert to meaningful differences. Losing either side of that balance risks oversimplifying one of the universe's most complex phenomena. When does simplification help us understand? And when does it begin to cause harm? Generalization is one of science's most powerful tools. By identifying patterns and shared principles, it allows us to compress complexity into understanding. Without it, the universe would be an overwhelming collection of disconnected facts. But like all powerful tools, generalization carries risk, especially when it is applied beyond its useful range. The danger arises when generalization begins to erase meaningful detail. In extreme systems, small differences can matter enormously. When those differences are smoothed over, conclusions may appear elegant and simple, yet quietly drift away from reality. Black holes illustrate this risk with particular clarity. They are governed by the same fundamental laws of gravity, yet their origins, environments, and consequences differ radically. Treating all black holes as equivalent can lead to statements that sound universally true, but fail in specific and important cases. When such overgeneralization occurs, it can distort interpretation. Observations that do not fit the simplified picture may be dismissed as anomalies rather than signals that the model itself needs refinement. In this way, simplification can slow progress instead of accelerating it. There is also a subtler cost. Broad, sweeping descriptions can impoverish the questions we ask. If all black holes are treated as fundamentally the same, then many lines of inquiry never arise. Distinctions that could lead to new insights are never explored, because the framework does not invite them. This problem becomes especially acute in extreme regimes. Near black holes, physics operates at the edge of what we understand. Assumptions that work well under ordinary conditions can fail dramatically. Applying generalized intuition to such environments can produce confident conclusions that are deeply misleading. This does not mean that generalization should be avoided. Science depends on it. The challenge is recognizing its limits. A general statement is useful only within the domain where its assumptions hold. Outside that domain, the same statement can become a source of error. In the study of black holes, caution is therefore essential. Claims that apply to all black holes must be treated carefully. examined for hidden assumptions about mass, environment, and formation history. Without that scrutiny, even well-established ideas can be stretched beyond validity. The lesson is not to abandon simplicity, but to use it deliberately. Simplification should clarify relationships, not obscure distinctions. It should open paths for deeper questions, not close them off prematurely. In a universe shaped by extreme objects and processes, humility becomes a methodological necessity. Generalization must be paired with a willingness to revise, refine, and sometimes abandon models when reality proves more complex than expected. Seen this way, generalization becomes a tool that demands judgment, used carefully. It illuminates, used carelessly. It conceals. The difference lies not in the tool itself, but in how and when we choose to apply it. If generalization is a double-edged sword, how do we know when to wield it and when to set it aside? Throughout our exploration, so far, a pattern has slowly emerged. The more carefully we examine black holes, the more exceptions we encounter. Objects that sit near boundaries, that form under unusual conditions, or that evolve along unexpected paths begin to strain the frameworks we rely on. These are not outliers to be ignored. They are signals that our understanding is incomplete. Some black holes do not fit neatly into established categories. Their masses fall between expected ranges. Their environments defy typical assumptions, or their behavior contradicts simplified predictions. When viewed through conventional models, these objects appear puzzling or even problematic. Yet it is precisely these cases that often drive scientific progress. Extreme objects probe the limits of theory. They expose assumptions that were never fully tested and highlight regimes where known physics may be stretched or incomplete. In this sense, anomalies are not failures of understanding, but opportunities to deepen it. Preparing for such extremes requires a shift in mindset. Instead of expecting every new observation to conform to established models, we must remain open to the possibility that those models describe only part of the picture. Flexibility becomes as important as precision. This does not mean abandoning structure or rigor. On the contrary, it means strengthening them by acknowledging their limits. A framework that can adapt to exceptions is more robust than one that breaks when confronted with them. In the study of black holes, preparing for extremes also means recognizing that the most revealing cases may not be the most common ones. Rare objects, fleeting events, and borderline systems can illuminate physics that remains hidden in more typical settings. As observational capabilities improve, these extreme cases are likely to appear more frequently. New instruments will push deeper into the universe and further back in time, revealing black holes that formed earlier, grew faster, or behaved more violently than expected. Encountering such objects will test not only our theories, but also our interpretive habits. The temptation will be to force them into existing categories. Resisting that temptation may be essential for genuine progress. In this way, the study of black holes becomes a lesson in scientific readiness. We are not only learning about the universe as it is, but training ourselves to respond when reality turns out to be more complex than expected. What lies ahead, then, is not a neat conclusion, but a frontier. The most extreme black holes do not simply extend known patterns. They challenge us to rethink the rules themselves. If some black holes do not follow the general rules, what happens when we confront the most extreme cases of all? Among the many ways black holes form and evolve, A few stand out not because of their size, but because of their impact. One of the most striking examples lies at the heart of the Phoenix cluster. From a distance, the Phoenix cluster appears as just another massive congregation of galaxies, bound together by gravity across millions of light years. But when observed in detail, it reveals itself as one of the most extreme environments ever studied in modern astrophysics. This is not simply a collection of galaxies drifting quietly through space. It is a region saturated with energy, heat, and motion, where matter exists under conditions far removed from anything we experience in our local cosmic neighborhood. The Phoenix cluster ranks among the largest and hottest galaxy clusters ever observed. With temperatures so high that the space between galaxies glows brightly in X-rays. These X-rays do not come from stars or planets, but from vast reservoirs of superheated gas that fill the cluster, known as the intracluster medium. In fact, this gas contains far more mass than all the stars in all the galaxies combined, making it the dominant visible component of the cluster. Hundreds of galaxies move within this environment, each one bound not only to the cluster as a whole, but also to this immense sea of hot plasma. At temperatures of tens of millions of degrees, the gas cannot form stars, cannot collapse easily, and cannot cool quickly. According to classical models of galaxy cluster evolution, this gas should gradually lose energy over time, slowly cooling and flowing inward toward the cluster's center. There, it would be expected to condense, trigger bursts of star formation, and reshape the central galaxy. For decades, this slow cooling process was thought to be inevitable, an almost passive consequence of gravity and time. The Phoenix cluster challenges that assumption at nearly every level. Observations show that while cooling does occur, it does not proceed unchecked. The cluster remains extraordinarily hot, far hotter than classical theories would predict given its age and size. This tells us that something within the cluster is actively injecting energy back into the environment, counteracting the natural tendency toward cooling. In this sense, the Phoenix cluster functions as a natural laboratory, a place where extreme physics plays out on scales large enough to be measured, but complex enough to expose the limits of our understanding. It allows scientists to study how energy moves through cosmic structures, how matter responds under prolonged stress, and how balance can emerge from forces that seem, at first glance, incompatibly. The environment of the Phoenix cluster is not calm, not static, and not slowly fading away. It is dynamic, self-regulating, and profoundly influenced by processes that originate at its very center. And it is precisely this extreme, high-energy setting that makes the Phoenix cluster so important, because in an environment this harsh, this hot, and this massive, the question naturally arises: what, if anything, can truly dominate the system as a whole? At the very center of the Phoenix cluster lies its most massive galaxy, often referred to as the brightest cluster galaxy. These central galaxies are not simply larger versions of ordinary galaxies. They are structural anchors, shaped by billions of years of mergers, accretion, and gravitational dominance. Embedded deep within the core of this central galaxy is Phoenix A*, a supermassive black hole whose position is not accidental, but inevitable. It sits precisely at the gravitational center of the cluster, the point toward which matter has been drifting for cosmic timescales. This location is more than a matter of geometry. In galaxy clusters, Gravity organizes structure on every level, and the deepest gravitational well defines where mass, energy, and motion ultimately converge. Phoenix A times occupies that well. It is not an isolated object floating within the cluster, but the nucleus of a much larger system, inseparable from the galaxy and the cluster that surround it. Every large-scale flow of matter within the Phoenix cluster, from cooling gas to infalling material from the outskirts, is ultimately connected to this central region. Gas does not simply wander randomly through the cluster. It responds to pressure gradients, temperature differences, and gravitational forces, all of which guide it inward. Over time, enormous quantities of matter pass through the vicinity of Phoenix A*, not necessarily to be consumed, but to interact, to be heated, redirected, or expelled. In this sense, the center of the cluster is not only a spatial reference point, but a crossroads of physical processes. It is where the history of the cluster accumulates and where its future is continually reshaped. To describe Phoenix A times as merely a black hole at the center of a galaxy would miss this deeper role. It functions as the energetic heart of the system, a region where gravitational dominance and energy output overlap. The distinction matters, because a central position grants influence. When energy is released near the gravitational center of a massive system, it does not remain localized. It propagates outward, interacting with gas on scales far larger than the black hole itself. This is why central black holes are uniquely capable of affecting entire clusters, while identical black holes placed elsewhere would have far more limited reach. The Phoenix cluster makes this principle visible. Its structure funnels matter inward, while its center returns energy outward, creating a feedback loop that links the smallest scales of space-time curvature to the largest scales of cosmic structure. In such a configuration, the black hole can no longer be thought of as a passive endpoint where matter disappears. Its position alone ensures that it participates in the regulation of the entire system. The question, then, is unavoidable. When a black hole occupies the very center of a galaxy cluster, aligned with its deepest gravitational well and embedded within its largest galaxy, can its role truly remain passive, or does the geometry of the system itself demand that the black hole become an active participant in shaping its environment? When we speak of jets emerging from black holes, it is tempting to imagine violent streams of matter being forcibly expelled, as if the black hole were somehow throwing material outward. In reality, astrophysical jets are far more subtle and far more revealing. A jet is a highly collimated flow of energy and matter launched along the rotational axis of a black hole, extending far beyond the boundaries of its host galaxy. These structures can stretch for tens, even hundreds of thousands of light years, maintaining remarkable coherence across distances that dwarf the scale of the black hole itself. Yet not every black hole produces such jets. Many supermassive black holes remain relatively quiet, surrounded by swirling disks of gas, but showing little evidence of large-scale outflows. This immediately tells us that jets are not an automatic consequence of a black hole's existence, nor of its mass alone. Instead, they arise only under specific physical conditions. At the heart of jet formation lies the accretion disk, a rotating structure of gas and plasma spiraling toward the black hole. As this material accelerates and heats up, it becomes electrically charged, transforming the disk into a dynamic electromagnetic system. Threaded through this disk are powerful magnetic fields. twisted and amplified by the intense rotation of both the disk and the black hole itself. These magnetic fields do not merely trace the motion of matter, they actively shape it. Under the right conditions, they channel energy away from the disk and the black hole, launching it outward along the axis of rotation in the form of a relativistic jet. Crucially, the energy carried by the jet does not come primarily from matter being swallowed, while accretion supplies the raw material and the conditions needed for jet formation. The dominant energy source lies elsewhere. The rotational energy of the black hole, combined with the stored energy of the magnetic fields, is converted into directed motion. In effect, the black hole's spin acts as a reservoir, and the magnetic field serves as the mechanism that taps into it. This process allows enormous amounts of energy to be extracted without requiring equally enormous amounts of mass to disappear beyond the event horizon. The distinction matters because it explains how a black hole can exert influence far beyond its immediate surroundings without rapidly growing in size. Jets are not waste products of feeding, they are organized channels of energy transfer. Once launched, they interact with everything they encounter, compressing gas, driving shock waves, and redistributing heat across vast regions of space. In the context of a galaxy cluster, this interaction becomes especially important. A jet originating near the cluster's center can carry energy outward into the surrounding medium, counteracting cooling, stirring turbulence, and reshaping the thermal structure of the entire system. What makes jets so powerful is not just their speed or their length, but their efficiency. They translate rotational and magnetic energy into large-scale environmental change. This reframes our understanding of black holes entirely. Instead of viewing them solely as cosmic sinks, we begin to see them as engines, capable of converting invisible motion into visible consequence. And this leads naturally to a deeper question. If the immense energy of a jet does not come directly from the mass falling inward, then where exactly does that energy originate? Measuring the power of a black hole jet presents a fundamental challenge. Unlike stars, which radiate energy directly in visible light, jets do not announce their strength in an obvious or immediate way. Their energy is not something we can point a detector at and simply record. Instead, it must be inferred indirectly, through the changes they imprint on their surroundings. In the case of Phoenix A*, scientists do not measure the jet itself so much as they measure what the jet does. Observations of the Phoenix cluster reveal vast cavities carved into the surrounding hot gas, enormous bubbles where X-ray emission is dramatically reduced. These cavities are not empty by chance. They are the scars left behind by repeated episodes of energy injection, where jets have pushed aside the intracluster medium with enough force to displace gas on scales of tens of thousands of light-years. By analyzing the size of these cavities, the pressure of the surrounding gas, and the time required to inflate them, researchers can estimate the total energy involved. The numbers that emerge are staggering. The mechanical power required to create and maintain these structures reaches levels on the order of 10 to the 46 ergs per second, placing Phoenix A times among the most energetic black hole systems ever observed. To put this in perspective, this output rivals or exceeds the combined luminosity of hundreds of billions of stars. It is not merely comparable to a galaxy's starlight, it competes with the energy budget of an entire galaxy cluster. What makes this even more remarkable is that this energy is not released in a brief, explosive event. It is delivered steadily over tens or even hundreds of millions of years. Such sustained power fundamentally alters the thermal history of the cluster. Classical models of cluster evolution assume that, over time, hot gas radiates away its energy and cools. Yet in the Phoenix cluster, the inferred jet power is sufficient to offset this cooling almost continuously. The cluster exists in a state that should not persist according to older theories. Its temperature remains high. Its gas remains turbulent. And its evolution is forced onto a different path, because the jet power is inferred rather than directly observed. The confidence in these conclusions comes from consistency. Multiple independent measurements, using different assumptions and methods, converge on the same result. The cavities, the shock fronts, the disturbed gas distribution, and the suppressed cooling all point toward an energy source of extraordinary magnitude. In this way, the Phoenix cluster becomes a case study in how astrophysics measures the unobservable. By reading the environment as a record of past events, scientists can reconstruct energies that would otherwise remain hidden. And this reconstruction leads to an unavoidable realization. The power associated with Phoenix A times lies well outside the range that cluster evolution models were originally designed to accommodate. It forces a re-evaluation of what black holes are capable of, not in isolation, but as long-term drivers of cosmic structure. When the only thing we can measure is the aftermath, the question becomes sharper. How can we be certain that the energy involved is truly this immense? And what does it mean when the consequences alone already exceed our expectations? Describing a black hole as violent can easily be misleading if the word is taken at face value. In astrophysics, violence is not measured by spectacle, nor by sudden destruction. It is measured by how rapidly and how persistently energy is transferred into an environment. By this definition, Phoenix A times stands apart. Its significance does not lie in being the largest black hole ever found, nor in producing the most dramatic single outburst. Instead, its violence emerges from the rate and intensity at which it releases energy, and from the scale over which that energy acts. The jets associated with Phoenix A times do not simply flare and fade. They operate over extended periods, injecting power into the surrounding cluster for tens to hundreds of millions of years. This sustained output means that the environment never has the opportunity to return to a quiet, equilibrium state. Energy is continuously added faster than it can be dissipated, keeping the intracluster medium in a state of agitation. What makes this especially striking is the scale involved. The effects are not confined to the immediate vicinity of the black hole or even to the host galaxy. They extend across the entire galaxy cluster, influencing regions separated by hundreds of thousands of light years. Gas is displaced, heated, and stirred on scales that dwarf the size of any individual galaxy. Over time, these changes accumulate. The temperature distribution of the cluster is altered, pressure gradients are reshaped, and the natural cooling processes that would otherwise dominate are persistently interrupted. This is not the aftermath of a single catastrophic event, but the signature of a continuous governing process. In many astrophysical contexts, extreme events are brief. Supernovae explode and fade. Gamma-ray bursts flash and vanish. Their violence is intense but fleeting. Phoenix A times represents a different category entirely. Its impact is long-lived, cumulative, and structural. The black hole does not overwhelm the cluster in a moment. It gradually but decisively redirects its evolution. This is why the term violent applies so precisely. It captures not chaos, but dominance. The dominance of an energy source capable of shaping an environment over cosmological timescales. The longer this process continues, the more pronounced its consequences become. What we observe today is not just a snapshot of activity, but the integrated result of millions of years of energetic influence. Seen this way, the true violence of Phoenix A times lies in its persistence. It continually modifies the balance between heating and cooling, between collapse and support. And this forces us to confront a deeper implication. If such long-term energetic dominance is the defining feature of its violence, then what aspects of the cluster's evolution are being rewritten as a result? The influence of Phoenix A times becomes most visible not through the jet itself, but through the way the surrounding hot gas responds. When astronomers observe the Phoenix cluster in X-rays, they see vast cavities embedded within the intracluster medium, regions where the normally bright X-ray glow is conspicuously absent. These cavities are not voids created by chance, nor are they the result of gas simply drifting away. They are sculpted by the mechanical force of the jet, which pushes into the hot plasma and displaces it, carving out enormous bubbles that can span tens of thousands of light years. The formation of these cavities marks the first stage of interaction, but it is far from the last. As the jet expands and evolves, it does not simply clear a path and move on. It stirs the surrounding gas, generating turbulence and shock waves that ripple outward through the cluster. This agitation redistributes energy across the intracluster medium, preventing heat from remaining confined to a small region near the black hole. Instead, energy is spread over a much larger volume, altering the thermal structure of the entire cluster core. One of the most significant consequences of this process is the change in temperature distribution. In a cluster without strong feedback, cooler gas would gradually sink toward the center, where higher densities would accelerate cooling and promote star formation. In the Phoenix cluster, this sequence is disrupted. The jet-driven mixing continually reheats gas that would otherwise cool, flattening temperature gradients and breaking the steady inward flow. Gas that might have condensed instead remains suspended, hot and turbulent. This prevents large amounts of material from settling into the central galaxy. Importantly, these effects are not confined to the immediate vicinity of Phoenix A*. The cavities, shocks, and stirred regions extend far beyond the black hole's gravitational sphere of influence. They propagate through the cluster core and into surrounding regions, demonstrating that the reach of the jet vastly exceeds the scale of its source. Over time, repeated episodes of jet activity reinforce this pattern, maintaining a dynamic environment in which cooling is continually delayed. The result is a cluster atmosphere that behaves very differently from what simple cooling models would predict. Rather than collapsing inward and forming stars efficiently, the gas remains in a precarious balance, constantly energized and perpetually unsettled. This balance is neither accidental nor temporary. It is sustained by the ongoing interaction between the jet and the hot gas. In this way, the jet does more than heat the environment. It reorganizes it. It reshapes the flow of matter, alters the timing of physical processes, and imposes a form of order through continuous disruption. And this leads to a critical realization. When the environment is persistently stirred and prevented from settling, certain outcomes are no longer possible. The question, then, is not simply what the jet is doing, but what it is actively stopping from happening. In galaxy clusters, cooling is not a minor detail. It is one of the fundamental processes that determines how structure evolves over billions of years. Hot gas radiates energy away, primarily in X-rays. And as it cools, it becomes denser. Denser gas sinks toward the cluster's center, where it can collapse and form new stars at extraordinary rates. In classical models, massive clusters like Phoenix should eventually experience intense bursts of star formation driven by this cooling flow. Yet, when astronomers examine the Phoenix cluster, they encounter a contradiction. The gas is hot enough, dense enough, and old enough that large-scale cooling should already have taken place. And yet, the expected flood of star formation is largely absent. The cluster is not forming stars at the rate its conditions seem to demand. This discrepancy points to an active counter-process. Phoenix A times injects energy back into the intracluster medium, effectively reversing the direction of thermal evolution. Instead of allowing gas to lose energy and settle inward, the black hole's jets reheat it, steer it, and keep it suspended. Cooling still occurs, but it is slowed, interrupted, and repeatedly reset. The result is not the elimination of cooling, but its regulation. This regulation is crucial. By preventing gas from cooling too efficiently, Phoenix A times stops the cluster from rapidly converting its gas reservoir into stars. Without this intervention, the central galaxy would grow far more quickly, altering the mass distribution and gravitational balance of the entire cluster over long timescales. This feedback stabilizes the structure. The cluster does not collapse inward, nor does it exhaust its gas supply prematurely. Instead, it remains in a prolonged state of controlled tension, balanced between heating and cooling. This behavior stands in stark contrast to the idea of passive evolution, where clusters simply age, cool, and fade. The Phoenix cluster is not fading. It is being actively maintained. Its long-term stability is not the result of inertia, but of continuous energy input. This changes how we think about time in cosmic systems. Evolution is no longer a one-way process driven solely by gravity and radiation. It becomes a dialogue between opposing forces. In this dialogue, the black hole plays a decisive role, not by creating stars, but by preventing them. This raises a profound implication. If a black hole can delay or suppress star formation across an entire cluster, then it is not merely influencing local conditions. It is intervening in the evolutionary path of one of the largest structures in the universe. The question that follows is unavoidable. When a black hole regulates when and where stars can form, how deeply is it reshaping the history of the cosmos itself? For much of modern astrophysics, the evolution of galaxy clusters was described as a largely passive process. Gravity assembled matter. Gas heated up during collapse. And over time, that gas radiated energy away, slowly cooling as the cluster aged. In this classical picture, clusters followed a one-way path from hot and chaotic to cooler and more settled. The role of black holes, if considered at all, was secondary, confined to the immediate surroundings of their host galaxies. The Phoenix cluster does not fit this narrative. Observations show a system that remains extraordinarily hot despite conditions that should favor cooling. Instead of progressing steadily toward thermal exhaustion, the cluster appears locked in a state of prolonged activity. This mismatch between theory and observation forces a reassessment of the assumptions underlying cluster evolution. The discrepancy cannot be explained by minor adjustments or overlooked details. It requires a fundamentally new ingredient. That ingredient is energy feedback from the central black hole. When the influence of Phoenix A times is accounted for, The behavior of the cluster begins to make sense. Energy injected by the jets offsets radiative cooling, reshapes gas flows, and alters the timing of star formation. But introducing this feedback changes more than just the outcome. It changes the structure of the model itself. Evolution is no longer a simple progression driven by gravity and radiation alone. It becomes a coupled system, where cause and effect loop back on each other. Heating triggers changes that modify cooling, which in turn affect accretion, feeding back into heating once again. In this framework, the cluster is not aging passively. It is actively regulated. This realization transforms galaxy clusters from static end products into dynamic systems. Their properties at any given time reflect an ongoing negotiation between opposing processes rather than a fixed stage along a predetermined path. The Phoenix cluster exemplifies this shift. Its current state cannot be understood as a snapshot along a one-directional timeline. It is the result of sustained interaction between gas, gravity, and black hole energy output. As a consequence, long-held ideas about cluster life cycles must be revised. Predictions based on passive cooling no longer hold when feedback is strong. Timescales stretch. Outcomes diversify. And stability emerges not from inertia, but from balance. The cluster becomes resilient, capable of maintaining its structure far longer than classical models would allow. This shift has implications beyond a single object. If feedback-driven regulation operates in Phoenix, it likely operates elsewhere as well, reshaping our understanding of how the largest bound structures in the universe evolve. The question, then, is no longer whether old models are incomplete. It is how they must change to accommodate a universe where evolution is not a straight line, but a continuously adjusted process. For much of the 20th century, black holes were defined almost entirely by what they removed from the universe. They were described as endpoints, regions where matter and light vanished from view, leaving behind little more than gravitational influence. In this picture, black holes were passive by nature. They responded to their surroundings, but did not shape them in any deliberate or sustained way. The Phoenix cluster forces a fundamental revision of that view. Phoenix A times does not behave like a silent sink. It acts as an active source of energy, capable of influencing conditions far beyond its immediate vicinity. The black hole does not simply wait for matter to fall in. Through its jets and feedback mechanisms, it redistributes energy outward, interacting continuously with the surrounding environment. This shift is more than semantic. It represents a change in causality. Instead of being a consequence of galactic evolution, the black hole becomes one of its drivers. The environment responds to the black hole, rather than the other way around. Gas flows are redirected, temperatures are regulated, and star formation is delayed or suppressed. These are not secondary side effects. They are primary outcomes of the black hole's activity. The implication is profound. If black holes can actively regulate their surroundings, then they must be treated as agents within cosmic systems, not merely as byproducts. Their influence is not confined to extreme, rare moments. It operates continuously, shaping evolution over cosmological timescales. This challenges the traditional definition of a black hole as an object characterized solely by mass, spin, and event horizon. Those properties remain fundamental, but they are no longer sufficient. What matters just as much is how a black hole couples to its environment, how efficiently it converts stored energy into large-scale change. In the case of Phoenix, A*, That coupling is strong enough to alter the fate of an entire galaxy cluster. This realization forces astrophysics to broaden its perspective. Black holes must be understood not only as solutions to Einstein's equations, but as dynamic participants in cosmic ecosystems. Their role is not limited to absorbing matter. They regulate flows, maintain balances, and, in some cases, prevent processes that would otherwise dominate. When framed this way, the black hole is no longer a passive endpoint of evolution. It becomes a controlling factor within it. And this reframing naturally leads to a deeper question. If a black hole can act as a sustained source of influence rather than a silent absorber, then where does its power truly come from? And what ultimately sets its limits? Not all supermassive black holes behave like Phoenix A*. In fact, many of the black holes found at the centers of large galaxies are remarkably quiet. They possess enormous mass, comparable in scale to the most active systems. Yet they produce little or no evidence of powerful jets. Their surrounding environments evolve in a markedly different way. Gas cools more predictably. Star formation proceeds with fewer interruptions, and the host galaxy follows a calmer evolutionary path. This contrast is crucial, because it reveals that extreme behavior is not an inherent property of black holes themselves. If mass alone determined activity, then the universe would be filled with violently active cluster cores. Instead, the majority remain relatively subdued. The difference lies not in what a black hole is, but in how it interacts with its surroundings. Two factors appear especially important. The first is the rate at which matter is supplied to the black hole. Accretion governs how much energy becomes available for extraction. But more importantly, it sets the conditions for magnetic fields to organize and intensify. The second factor is the structure of those magnetic fields themselves. Only when they are arranged in the right configuration can they efficiently tap into the black hole's rotational energy and launch large-scale jets. In many systems, accretion is too weak, too chaotic, or too intermittent to sustain this process. As a result, the black hole remains quiet, exerting influence primarily through gravity alone. Phoenix A* represents the opposite extreme. Its environment provides both a steady supply of material and the conditions necessary for strong, coherent magnetic fields to form. This combination allows it to enter a state of sustained activity, where energy extraction becomes highly efficient. The black hole is not fundamentally different from its quieter counterparts. It obeys the same physical laws and is governed by the same parameters. What differs is the regime in which it operates. In this regime, small changes in accretion or magnetic structure lead to disproportionately large consequences for the surrounding environment. This comparison reframes how we think about black hole diversity. Rather than categorizing black holes by type, it becomes more useful to think in terms of states. Quiet and violent are not separate classes, but different expressions of the same underlying object under different conditions. Phoenix A* occupies one end of this spectrum, illustrating what happens when circumstances align in the most extreme way. And this realization sharpens the central question. If black holes share the same fundamental nature, why do only a few, like Phoenix A*, cross the threshold into such dramatically different behavior? For a long time, mass dominated how black holes were ranked and understood. The more massive the black hole, the more important it was assumed to be. This intuition feels natural, because gravity scales directly with mass. and gravity is the most obvious influence black holes exert. Yet the Phoenix cluster reveals the limits of this perspective. Phoenix A times is undeniably massive, but its significance does not stem from size alone. What truly defines its role is how much energy it releases, how efficiently it releases it, and how far that energy reaches. In other words, impact outweighs mass. A less massive black hole, under the right conditions, can influence its environment more profoundly than a heavier one that remains inactive. This forces a shift in emphasis. Instead of asking how large a black hole is, we must ask what it is doing. Energy output becomes the dominant factor. It determines whether gas cools or remains hot, whether stars form or are delayed, whether a cluster evolves quietly or remains dynamically regulated. Mass sets the stage, but energy directs the performance. This distinction matters because mass is largely static on human timescales, while energy release is dynamic. It can rise, fall, switch modes, and reorganize entire systems without requiring significant changes in mass. Phoenix A times demonstrates this clearly. Its ability to channel rotational and magnetic energy into jets allows it to affect regions vastly larger than its own gravitational sphere of influence. The black hole's reach is therefore not limited by its size, but by the processes that convert stored energy into action. This reframing represents a critical change in thinking. It moves black holes from a category defined by scale to one defined by function. In doing so, it aligns them more closely with other astrophysical engines, such as stars and galaxies, which are also judged by what they emit, not just by what they contain. The implication is subtle but powerful. Two black holes of similar mass may play radically different roles in cosmic evolution, depending on how effectively they release energy. Conversely, a smaller black hole may punch far above its weight if conditions allow it to operate in a highly efficient regime. Phoenix A times sits at the extreme end of this spectrum, illustrating what happens when energy output, not mass, becomes the controlling parameter. This perspective does not diminish the importance of mass, but it reorders priorities. Mass defines potential. Energy defines consequence. And once consequence becomes the focus, our entire framework for evaluating black holes begins to change. The natural question that follows is inevitable. If size is no longer the primary measure of importance, then what metric truly captures the power of a black hole? In physics, power is rarely about size alone. It is about influence, the capacity to alter conditions, redirect processes, and impose structure on an environment. When viewed through this lens, the true authority of a black hole does not lie in its mass, but in its ability to shape what surrounds it. Phoenix A times makes this distinction unmistakably clear. Its mass places it among the giants, but mass by itself would mean little if it remained dormant. What grants Phoenix A times its exceptional status is the way it controls the physical state of an entire galaxy cluster. It acts as a central engine, a concentrated source of energy whose effects propagate outward, coupling the smallest scales of relativistic physics to the largest scales of cosmic structure. This form of power is not static. It is exercised through continuous interaction. By injecting energy into the surrounding gas, the black hole determines how that gas behaves, whether it cools, whether it collapses, whether it forms stars, or whether it remains suspended and turbulent. These outcomes are not side effects. They are the defining features of the cluster's evolution. In this sense, the black hole's power is environmental. It is measured not in solar masses, but in consequences. A central energy source capable of influencing temperature, pressure, and motion across hundreds of thousands of light years holds a kind of authority that far exceeds its physical size. Phoenix A times demonstrates that a relatively compact region of spacetime can govern a structure millions of times larger than itself. This realization reshapes how we think about dominance in the universe. Power is no longer proportional to scale in a simple way. Instead, it depends on leverage, how effectively energy is coupled into the surrounding medium. A black hole that can efficiently transfer energy outward can dominate a system even if its mass is modest by cosmic standards. Conversely, a far more massive black hole may exert little influence if it fails to engage its environment. This reframing places black holes alongside other regulatory agents in nature, systems whose importance arises from control rather than bulk. It also introduces a more nuanced metric of power. Influence is assessed by the magnitude and persistence of change produced, not by the intrinsic properties of the source alone. Phoenix A times sits near the extreme end of this spectrum, illustrating how far environmental control can extend. Yet this naturally raises a limit question. If power is defined by impact, and impact depends on energy coupling, then there must be boundaries beyond which even the most energetic black holes can no longer dominate. The challenge is not only to identify how black holes exert control, but to understand where that control ultimately breaks down, when black holes are framed as regulators rather than destroyers. Their role in the universe takes on a very different meaning. Regulation implies balance, timing, and restraint. In the context of galaxy clusters, it means participating directly in the control of energy flow. Phoenix A times exemplifies this role with unusual clarity. Instead of allowing processes to unfold unchecked, it intervenes through feedback, injecting energy precisely where and when it matters most. This feedback does not halt cosmic evolution, nor does it reverse it entirely. Instead, it slows certain processes down, preventing them from running to extremes. Gas that would otherwise cool too rapidly is reheated. Star formation that would proceed explosively is delayed. Structural collapse that could destabilize the cluster is postponed. In this way, the black hole acts not as a disruptive force, but as a moderating one. The concept of feedback is central here. Energy output from the black hole responds to conditions in the surrounding environment. When cooling intensifies, accretion increases, strengthening jet activity. That activity then heats the gas, reducing cooling and limiting further accretion. This self-regulating loop creates a dynamic equilibrium. The system oscillates around balance rather than diverging toward runaway behavior. Importantly, this regulation does not impose order by erasing complexity. On the contrary, it sustains complexity by preventing any single process from dominating completely. The cluster remains active, structured, and long-lived. Its order emerges not from stillness, but from continuous adjustment. Phoenix A times thus becomes part of a larger, stabilizing mechanism, one that operates across immense scales of space and time. The black hole does not sit outside the system it influences. It is embedded within it, responding to changes and shaping responses in return. This perspective alters how we think about cosmic stability. Stability is no longer synonymous with inactivity. It becomes a balance maintained through ongoing interaction. Black holes, once seen as symbols of finality, emerge as participants in this balance. Yet regulation implies limits. Every stabilizing mechanism has a threshold beyond which it can no longer compensate. If energy input becomes too strong, structure can be disrupted. If it becomes too weak, collapse resumes. Phoenix A times appears to operate near this delicate boundary. And that observation raises a critical question. If black holes truly act as regulators of cosmic systems, what happens when the regulating mechanism itself is pushed beyond its limits? Every physical system has limits. No environment, no matter how vast, can absorb energy indefinitely without consequence. In galaxy clusters, this principle defines a narrow corridor between stability and disruption. Too little energy input, and gas cools rapidly, collapsing inward and triggering runaway star formation. Too much energy, and the structure of the cluster itself begins to fracture, with gas expelled. Pressure, balance lost, and coherence broken. The Phoenix cluster appears to reside within this narrow corridor. Its environment is neither collapsing nor being torn apart. Instead, it exists in a finely tuned state where energy injection from the central black hole nearly balances radiative losses. This balance is not exact, and it is not static. It fluctuates over time, responding to changes in accretion, jet activity, and gas dynamics. What makes Phoenix A times so scientifically valuable is that it operates close to this boundary. The cavities, shocks, and temperature distributions observed in the cluster suggest that the system is being pushed hard, but not beyond its breaking point. The gas is displaced, heated, and stirred, yet it remains gravitationally bound. Cooling is delayed, but not entirely suppressed. This indicates that the energy output is approaching the maximum that the environment can tolerate without destabilizing. Observations, therefore, provide more than a description of an extreme object. They offer a way to measure the tolerance of cosmic structures. By studying how the intracluster medium responds to sustained energy input, scientists can infer where the threshold lies between regulation and destruction. This threshold is not defined by a single number. It depends on gas density, cluster mass, geometry, and the history of energy injection. Phoenix cluster allows these variables to be examined in concert. It serves as a stress test for our models, revealing how close a real system can come to instability while remaining intact. The implications extend beyond this single cluster. If Phoenix A times is indeed operating near the upper limit of environmental tolerance, then systems pushed even slightly harder may behave very differently. Gas could be expelled from the core. Star formation could be quenched permanently. The cluster might transition into a new evolutionary regime. Understanding where this boundary lies is therefore essential for predicting the long-term fate of massive cosmic structures. And it sharpens the central question. If Phoenix A times sits near the edge of what its environment can endure, what happens when that edge is crossed? And how would we recognize the moment it occurs? The story of Phoenix A times is at its core, a story about control. Control over energy, control over matter, control over the structure of space on the largest scales we can observe. By regulating heat, suppressing collapse, and reshaping the environment of an entire galaxy cluster. Phoenix A times challenges our understanding of how space itself evolves. Yet for all of its influence, there is one domain it has not directly confronted: time. Everything we have described so far unfolds within the familiar flow of cosmic time. The black hole alters outcomes, delays processes, and stretches evolutionary pathways. But it does so without breaking the fundamental direction of time. Cooling is slowed, not reversed. Star formation is postponed, not undone. The cluster's history is redirected, but it still moves forward. This distinction matters. It tells us that even the most powerful black holes, when acting through energy feedback alone, remain bound by temporal progression. However, the universe contains other black holes that hint at a deeper challenge. Objects whose behavior forces us to question not just how fast processes occur, but how time itself is experienced. Near event horizons, time dilates. Near singularities, our equations break down entirely. In these regimes, time ceases to behave as a simple background parameter and becomes part of the problem. Phoenix A times prepares us for this transition. It shows us that black holes are capable of controlling space and energy on unimaginable scales. Once that lesson is absorbed, the next question becomes unavoidable. If energy is not the final constraint, then what is the frontier shifts from power to temporality? From how much energy can be injected to how time itself responds to extreme gravity. This is where feedback models reach their limits, and deeper paradoxes emerge. Black holes do not merely influence when things happen. In certain conditions, they redefine what when even means. Phoenix A times does not cross that boundary, but it brings us to its edge. It demonstrates that the universe is already more regulated, more interactive, and more dynamic than classical pictures allowed. And standing at this threshold, the focus must now turn away from energy alone, toward time, toward causality, toward the question that lingers beyond all others. If a black hole can control space and energy on the scale of a galaxy cluster, what happens when time itself becomes the variable under pressure? If Phoenix A reveals the limits of energy, another black hole forces us to confront something more restrictive. Not power, not size, but time itself. Asterisk. The object now known as TON 618 did not enter astronomy as a black hole at all. It was first noticed as something far more familiar to observational astronomers, an extraordinarily bright quasar. In early surveys, its defining feature was not mass, gravity, or relativistic effects, but sheer luminosity. It shone so intensely that it dominated its surroundings, overwhelming any attempt to see what lay at its core. At the time, there was no intention to search for a record-breaking black hole. Astronomers were simply cataloging unusual sources of radiation, trying to understand why certain points in the sky emitted far more energy than expected. TON 618 stood out because it did not behave like ordinary galaxies. Its light output was extreme, persistent, and difficult to reconcile with known stellar processes. That brightness, however, was also a veil. The very radiation that made TON 618 visible across vast cosmic distances concealed the nature of the engine producing it. The central region could not be observed directly. Instead, its presence had to be inferred indirectly, through spectral lines, emission widths, and the dynamics of the surrounding material. Only gradually did a picture begin to form. The quasar's luminosity implied an energy source far beyond nuclear fusion. The velocities of gas near the center suggested gravitational forces of extraordinary strength. Piece by piece, Astronomers realized that the simplest explanation involved a supermassive black hole accreting matter at an extreme rate. Even then, the identification was cautious. TON 618 was not discovered by pointing a telescope and declaring, "Here is a black hole." It was uncovered through a chain of inference, built from anomalies and inconsistencies. Each observation narrowed the possibilities, until the black hole interpretation became unavoidable. This indirect path matters. It reminds us that some of the most extreme objects in the universe do not announce themselves clearly. They emerge from the data only after careful analysis, long after the initial observations are made. TON 618 was revealed not because we knew what we were looking for, but because something refused to fit. Its discovery was not a triumph of prediction, but of attention. An object that was never meant to be a black hole candidate slowly transformed into one of the most challenging black holes ever studied. And this origin story sets the tone for everything that follows. If TON 618 was not found by searching for the limits of black holes, but by stumbling upon a source that defied explanation, then the real question becomes unavoidable. If it was not discovered as a black hole, what was it about TON 618 that forced astronomers to look deeper? Once, TON 618 was recognized as something extraordinary. Its distance immediately became impossible to ignore. This object does not reside in the nearby universe, nor even within the relatively local cosmic neighborhood. It lies at such an extreme distance that the light reaching our telescopes today began its journey billions of years ago. Every photon we collect left TON 618 long before the Earth existed in its current form. In practical terms, this means that nothing we observe represents the black hole as it is now. Every spectrum, every brightness measurement, every inferred property belongs to a remote past. Distance, in this context, ceases to be a simple geometric separation. It becomes a physical barrier imposed by time itself. The farther an object lies, the deeper into the past we are forced to look. Observing TON 618 is therefore not just an act of measurement, but an act of historical reconstruction. We are not watching an object evolve in real time. We are examining a frozen record of how it behaved when the universe was far younger. This has profound implications. When astronomers speak about the mass, luminosity, or activity of TON 618, they are always speaking in the past tense, even if the language does not make that explicit. The present state of the black hole is fundamentally inaccessible. Its now is separated from us by billions of years of cosmic expansion. No improvement in telescope technology can overcome this delay. Faster detectors, sharper resolution, or more sensitive instruments can refine what we see, but they cannot close the temporal gap. The universe enforces that limit. As a result, distance becomes a physical parameter with causal consequences. It determines not only how faint an object appears, but how incomplete our knowledge must remain. This inversion of intuition is subtle but crucial. In everyday experience, distance merely separates locations. In cosmology, distance separates epochs. To look far away is to look backward. For TON 618, this backward gaze is extreme. The object we describe exists for us only as a memory carried by light. This reframes the act of observation itself. Astronomy becomes less like surveillance and more like archaeology. We uncover evidence, not current states. We infer processes, not ongoing actions. And this leads to an unsettling realization. If all available data describe a version of TON 618 that no longer exists, then our understanding is always temporally displaced. We build models, draw conclusions, and test theories against an object that may have already changed beyond recognition. The black hole we discuss is, in a very real sense, no longer there. It has moved on, evolved, and possibly transformed entirely. The light simply has not caught up. This raises a question that cuts to the core of scientific meaning. When observation itself is inseparable from looking into the past, what does it mean to speak about the present state of a cosmic object at all, once distance and time delay are taken into account? The next shock comes from mass. Estimates of TON 618's mass place it far beyond the scale of black holes we consider familiar. Even among supermassive black holes, it occupies an extreme position. The numbers involved are so large that they resist intuitive comparison. They are not simply bigger by a factor of 2 or 3. They exceed typical values by orders of magnitude. What makes these estimates especially compelling is that they do not come from a single technique. Astronomers approach the problem from multiple directions, using independent methods that rely on different physical assumptions. They analyze the width of emission lines produced by fast-moving gas near the center. They infer gravitational influence from luminosity and accretion behavior. They compare results across models and datasets collected over decades. While each method carries uncertainty, they converge on the same unsettling conclusion. Even when conservative assumptions are applied, the mass remains extraordinarily large. The error bars do not rescue the situation. They shift the value, but they do not bring it back into a comfortable range. This is a crucial distinction. TON 618 is not controversial because it might be slightly larger than expected. It is controversial because it sits well outside the regime that existing formation and growth models were designed to handle. In that sense, it is not simply the largest black hole. It is a black hole whose mass exceeds what the models comfortably allow. This transforms mass from an answer into a problem. Instead of clarifying our understanding, the number raises new questions. How could such a mass be assembled? Under what conditions and within what time frame? The issue is not whether the measurements are perfect. Science rarely demands perfection. The issue is that multiple imperfect methods point in the same direction. They collectively insist that TON 618 belongs to an extreme category that theory struggles to explain. When mass becomes this large, it stops functioning as a descriptive parameter and becomes a diagnostic one. It reveals the limits of our assumptions about growth, accretion, and cosmic history. In this context, asking whether TON 618 is the single largest black hole misses the deeper point. The real significance lies in how far it pushes beyond expectation. It forces us to question whether the frameworks we use to interpret such numbers are still adequate. The measurement itself is not the end of the inquiry. It is the beginning. Because once a value grows beyond what theory can absorb, the focus must shift. The problem may not lie with the object alone. It may lie with the way we understand what such objects are allowed to become. When a number refuses to fit, we must decide whether to doubt the object or to reconsider the model that gives the number meaning. Extreme mass alone does not create a paradox. Time does. In astrophysics, black holes do not simply appear at their final size. They grow. This growth follows physical rules, governed by how matter falls inward, how radiation pushes back, and how efficiently mass can be converted into gravitational weight. Accretion is not instantaneous, even under ideal conditions. it proceeds at a limited rate. Radiation pressure generated by infalling matter imposes a natural ceiling on how fast a black hole can gain mass. This means that growth is gradual, cumulative, and time-dependent. Standard formation models reflect this reality. They assume that black holes begin as smaller seeds and increase in mass over hundreds of millions to billions of years. There is no known mechanism that allows a black hole to become extraordinarily massive in a cosmic instant without violating well-tested physical principles. This is where TON 618 creates tension. When its estimated mass is combined with the epoch at which we observe it, the numbers begin to conflict. The universe at that time was simply too young. There does not appear to be enough available time for a black hole to grow from a plausible initial seed to the mass inferred for TON 618 using conventional growth rates, even assuming near-continuous accretion at the upper physical limit. The clock runs out. The math does not close. This is not a matter of fine-tuning or unlikely efficiency. It is a fundamental timing problem. Growth models demand billions of years. The observed light suggests far less. The discrepancy does not disappear when uncertainties are expanded. Adjusting parameters can ease the tension slightly, but it cannot eliminate it. At some point, time itself becomes the bottleneck. The paradox sharpens because the individual steps make sense. Accretion physics is well understood. Radiation pressure has been tested in multiple contexts. The early universe timeline is independently constrained by cosmology. Each component, taken alone, appears reasonable. Yet, when combined, they refuse to align. TON 618 seems to have reached a size that it should not have had enough time to achieve. This shifts the nature of the problem. The question is no longer whether black holes grow. They clearly do. The question becomes how growth proceeded fast enough, early enough, to produce such an object. Either the initial conditions were radically different from what we assume, or growth mechanisms operated in regimes we do not yet fully understand. In either case, time is the limiting factor, not energy, not space, time. And when time is insufficient, explanations must stretch or break. This is why TON 618 is not merely large. It is temporally inconvenient. It exists where it should not, when it should not, according to current models. And that leads to the unavoidable question. If the universe did not grant enough time for this black hole to form in the usual way, then by what path did it arrive here at all? The tension surrounding TON 618 intensifies when its mass and growth requirements are placed within the broader timeline of the universe itself. This object is not observed in the modern cosmos. After billions of years of quiet evolution, it is seen at a time when the universe was still young, when structures were only beginning to assemble and cosmic order was far from settled. Cosmological models tightly constrain the age of the universe at that epoch. There is only so much time available, and that time must accommodate everything: the formation of galaxies, the build-up of large-scale structure, and the growth of the earliest black holes. Within this framework, TON 618 appears uncomfortably early. The conflict that emerges is subtle but profound. It is not a disagreement between measurements. Astronomers do not argue over when the light was emitted, nor over how old the universe was at that redshift. Those values are independently supported by multiple lines of evidence. The contradiction arises instead between timing and scale, between when TON 618 is observed and how massive it already appears to be. In simple terms, the universe does not seem to have had enough time to produce something like this through known evolutionary pathways. This is why the problem cannot be dismissed as an observational anomaly. The data are internally consistent. The redshift places TON 618 firmly in a young universe. The inferred mass is large by any standard. The issue lies in connecting these two facts within a single coherent narrative. Evolutionary models describe how complexity builds gradually. They rely on sequential processes unfolding over time. But TON 618 seems to compress those processes into an interval that is too short. Time becomes a stressed variable. It is stretched to its limit, asked to accommodate more growth than it should reasonably allow. The paradox deepens because there is no obvious escape route. One cannot simply extend the age of the universe at that epoch without breaking cosmology. Nor can one easily reduce the inferred mass without contradicting multiple observations. The system appears cornered by its own consistency. Everything agrees, except the story we tell about how it all fits together. This reveals the true nature of the conflict. It is not a crisis of data, but a crisis of evolution. The sequence of events that our models rely on may be incomplete, or ordered incorrectly, or missing an early phase entirely. Time itself becomes the battleground where assumptions collide. When astrophysicists confront TON 618, they are forced to ask not whether the universe is old enough, but whether their picture of how structures grow within that age is sufficient. The black hole exposes a gap between what the universe permits chronologically and what our models predict evolutionarily. And in that gap, uncertainty expands. The question is no longer confined to TON 618 alone. If such an object can exist so early, then either rare exceptions occurred, or the rules of early growth were different from what we currently assume. In either case, time is no longer a passive backdrop. It becomes an active constraint, shaping what can and cannot exist. And this brings us to the unavoidable question. When time itself seems insufficient, is it the model that must bend? Or the assumptions that must be rebuilt from the ground up? At the heart of the time problem lies a physical speed limit. Black holes cannot grow arbitrarily fast, no matter how much matter surrounds them. The act of accretion itself generates radiation, and that radiation pushes back. As matter spirals inward, it heats up, emits energy, and creates outward pressure that resists further infall. This balance establishes what is known as the Eddington limit, a threshold where the inward pull of gravity is matched by the outward force of radiation. Beyond this point, adding more material does not significantly increase growth. Instead, excess matter is blown away. This limit is not a theoretical curiosity. It is a well-tested consequence of basic physics, observed across a wide range of astrophysical systems. It defines a maximum sustainable growth rate, setting a hard ceiling on how quickly mass can be accumulated over time. For most black holes, growth proceeds well below this ceiling. Even when accretion is efficient, it rarely remains at the limit for long periods. Variability, feedback, and environmental changes intervene. This makes sustained, near maximal growth exceptionally difficult. When this framework is applied to TON 618, the tension sharpens. To reach its inferred mass within the available cosmic time, the black hole would need to accrete at or above the Eddington limit for an extended duration. Not briefly, not episodically, but continuously, over a timespan that strains plausibility. Exceeding the Eddington limit is not forbidden in principle, but it requires special conditions. Radiation must escape without coupling strongly to infalling gas. or accretion must occur through geometries that reduce feedback. Such states are thought to be unstable or short-lived. It remains unclear whether they can be maintained long enough to account for the mass of Ton 618. And even if super-Eddington phases occur, their efficiency and longevity remain uncertain. This uncertainty is not a small detail. It sits at the core of the paradox. The growth rate required appears to collide directly with a fundamental physical barrier. The Eddington limit does not bend easily. It is rooted in the interaction between light and matter. To bypass it without breaking, physics demands mechanisms that are either rare, transient, or not yet fully understood. As a result, the problem shifts again. It is no longer just about how early the black hole appears, or how massive it is. It becomes about whether the universe can plausibly sustain growth at the required pace without violating known laws. The limit transforms time into a rigid constraint. Even infinite fuel would not help if it cannot be absorbed fast enough. This is why the Eddington limit matters so deeply in the case of Ton 618. It turns the question of growth into a question of feasibility. The clock is ticking. The mass is enormous, and the growth rate seems capped. Something must give. Either the black hole found a way to operate near the edge of physics for an exceptionally long time, or our understanding of accretion limits is incomplete. And that leads directly to the next question. If growth truly has a ceiling, how can that ceiling be crossed without forcing physics itself to break, faced with the problem of insufficient time? One possibility naturally shifts attention away from growth speed and toward initial conditions. Perhaps Ton 618 did not begin small at all. The seed black hole hypothesis proposes that some black holes may have formed with unusually large initial masses, bypassing the need for prolonged, gradual growth. Among these ideas, direct collapse stands out. In this scenario, vast clouds of primordial gas collapse directly into a black hole without first fragmenting into stars. If such a process occurs, it could produce a seed thousands or even hundreds of thousands of times more massive than those formed from stellar remnants. This would dramatically reduce the amount of growth required later, easing the time tension. On paper, the idea is elegant. It preserves known accretion limits while altering the starting point. However, elegance does not guarantee reality. Direct collapse demands highly specific conditions. The gas must remain hot enough to avoid fragmentation, yet dense enough to collapse. Cooling must be suppressed, star formation delayed, and turbulence controlled. These requirements are not impossible, but they are extreme. They are expected to occur only in rare environments during the earliest phases of cosmic history. Even then, such conditions may persist only briefly. The rarity of these circumstances limits how often direct collapse could realistically occur. More importantly, there is currently no direct observational evidence that such massive seeds ever formed. Astronomers have not yet observed an unambiguous example of a direct collapse black hole in its infancy. What exists instead are indirect hints and theoretical models that remain difficult to test. The early universe is observationally opaque, and the signatures of such events may be subtle or short-lived. As a result, the seed hypothesis occupies an uncertain position. It is neither ruled out nor confirmed. It offers a possible escape from the time problem, but only by invoking conditions that stretch plausibility. This places the burden of persuasion on probability rather than possibility. Could such rare conditions explain one object? Perhaps. Could they explain a population that is less clear? For Ton 618, The hypothesis remains tempting because it addresses the core difficulty without violating known physical laws. Yet it does so by leaning heavily on events we cannot yet observe. In this sense, the seed black hole hypothesis highlights a recurring tension in astrophysics. When direct evidence is inaccessible, theory must operate in the space between what is allowed and what is likely. TON 618 sits squarely in that space. Its existence does not demand the seed hypothesis, but it keeps it alive. And that leaves us with an uncomfortable balance. The hypothesis exists. It is mathematically consistent, and it may be physically possible, but without observational confirmation, its explanatory power remains provisional. This forces a deeper question. When a hypothesis requires conditions so specific and so rare, where should its credibility truly rest? By this stage, the difficulty surrounding TON 618 can no longer be reduced to observational delay or incomplete data. The problem runs deeper. It is not simply that we are seeing the object in the past. It is that, even within that past, there appears to be too little physical time available for the black hole to become what it already is. Every individual mechanism involved in black hole evolution appears sound. Accretion operates as expected. Radiation pressure imposes its limits. Seed formation scenarios remain within the bounds of known physics. None of these steps are inherently contradictory. Yet, when they are combined into a single evolutionary timeline, the total duration falls short. The sum of reasonable processes does not add up to the observed outcome. This is what transforms the issue into a true paradox. It is not a matter of small discrepancies or adjustable parameters. Tweaking efficiencies or extending uncertainties cannot resolve it. Even optimistic assumptions strain against the clock. The difficulty lies in aggregation. Each process consumes time, and time is finite. When those requirements are added together, the available cosmic window closes too soon. This is why the problem must be framed as a shortage of physical time, not merely observational time. Observational limitations affect what we can see. Physical time limits what can happen at all. TON 618 confronts us with the latter. It exists in a regime where the universe has not granted enough duration for conventional evolution to unfold. This creates a sharp conceptual tension. Our models describe how black holes grow step by step. But TON 618 appears as though several steps have been compressed or bypassed. The paradox is not that any single rule is broken. It is that all the rules, obeyed together, still fail to produce the result. Time becomes the central variable under stress. It is no longer a neutral backdrop against which processes play out. It becomes the bottleneck that constrains possibility. This reframing changes the nature of the inquiry. The question is no longer whether we understand accretion, feedback, or collapse. The question becomes whether our timeline itself is missing something essential. Perhaps an early phase proceeds faster than we expect. Perhaps growth is episodic in a way that collapses timescales. Or perhaps the initial conditions of the universe allowed pathways that are no longer accessible. These are not refinements at the margins. They are structural gaps in how we connect physics to chronology. TON 618 therefore occupies a unique role. It does not simply challenge a parameter. It challenges the coherence of an entire evolutionary sequence. When every component appears valid, yet the whole remains impossible, the problem can no longer be localized. It becomes systemic. And this is why time emerges as the true centerpiece of Act 6. Not because it is mysterious in itself, but because it refuses to accommodate what we observe. The black hole forces us to confront the possibility that something fundamental about early cosmic timing remains misunderstood. When mechanisms are correct but the total still does not fit, the implication is unavoidable. Something is missing. The question that follows is not whether we can adjust existing explanations, but whether we have yet identified the process that makes the timeline whole at a fundamental level. Everything we know about TON 618 arrives encoded in light. That light is not instantaneous information. It is a messenger from the past, traveling across an expanding universe for billions of years before reaching us. By the time it enters our telescopes, it carries a story that is already ancient. There is no channel through which we can access the black hole's present state. No signal moves faster than light. No observation can leap across the temporal gap imposed by distance. The now of TON 618 is therefore permanently inaccessible. It exists, but not for us. This creates a profound fracture in intuition. In everyday experience, observation feels immediate. We look, and we see what is happening. In cosmology, this intuition collapses. Observation becomes retrospective by necessity. Every property we infer mass. Luminosity. Accretion rate belongs to a version of the object that existed billions of years ago. Our models are calibrated against that past, not against an evolving present. This does not merely complicate interpretation, it transforms the meaning of description itself. When we speak about TON 618, we are not describing what it is. We are describing what it was. The distinction is subtle, but it matters. The black hole may have changed dramatically since the light we observe was emitted. It may have grown further, quieted, merged, or altered its environment in ways we cannot yet know. All such possibilities lie hidden behind a temporal wall. No future instrument can remove this limitation. Technology can sharpen the image of the past, but it cannot pull the present into view. Time enforces an absolute asymmetry. This forces science into an unusual posture. We must reason about processes whose current outcomes are unknown, using evidence that is permanently delayed. Theories are tested not against reality as it is, but against reality as it once was. For nearby objects, the delay is negligible. For TON 618, it is dominant. Billions of years separate cause from observation. This delay breaks the intuitive link between explanation and existence. We explain an object whose current state we will never directly observe. And yet, science proceeds. It constructs narratives constrained by physics that bridge the gap between past evidence and present inference. But those narratives always carry an asterisk. They describe a history, not a state. This realization deepens the time paradox rather than resolving it. The difficulty with TON 618 is not only that it seems to have formed too quickly, it is that we cannot even verify what it has become. The object confronts us with a limit that is not technological, but temporal. Our knowledge is bounded by when the light left, not by how carefully we analyze it. This reframes the central problem of Act 6. If the present is unreachable, then scientific understanding becomes an exercise in reconstruction rather than observation. And that raises a deeply unsettling question. When we cannot know the present of an object, what exactly is science claiming to describe? Once we accept that all information about TON 618 comes from the distant past, a new layer of uncertainty emerges. The black hole we describe may no longer resemble the one that exists today, over billions of years. Dramatic change is not just possible, it is expected. Accretion may have continued, allowing the black hole to grow even more massive. Alternatively, fuel may have been exhausted, causing the once blazing quasar to fade into relative quiet. Mergers could have occurred. Jets could have weakened or shut down. The surrounding environment could have transformed completely. All of these scenarios are physically plausible. None can be confirmed. This is the uncomfortable reality imposed by cosmic time delay. The present state of TON 618 is not unknown because we lack data, but because the universe does not permit access to it. The information simply has not arrived, and will not arrive for billions of years. As a result, the current TON 618 exists as a conceptual gap. It is not an object we can describe, only one we can imagine within physical bounds. This gap matters deeply for interpretation. When scientists discuss the implications of TON 618 for black hole growth, they are necessarily extrapolating from a snapshot frozen in deep time. Conclusions are drawn with the understanding that the object may have evolved beyond recognition since that snapshot was taken. This does not invalidate scientific reasoning, but it changes its nature. Certainty becomes conditional. Statements are framed probabilistically, bounded by what physics allows rather than what observation confirms. In this sense, TON 618 exposes a fundamental asymmetry in knowledge. We can reconstruct histories with increasing precision, yet remain blind to outcomes. The past becomes increasingly detailed, while the present remains opaque. This inversion challenges our intuitive sense of scientific progress. We often associate better instruments with greater immediacy and clarity. Here, progress sharpens the image of what was, not what is. The black hole's present becomes an absence rather than a target. And within that absence, questions accumulate. If TON 618 has changed substantially, do our conclusions still apply? If it has quieted, does that alter its role in cosmic evolution? If it has grown even larger, does the paradox deepen further? There is no way to know. The uncertainty is not temporary. It is structural. It cannot be eliminated by patience or precision. It is written into the geometry of space-time itself. This forces a sober reassessment of what scientific certainty means in cosmology. Knowledge is not defined by direct verification, but by coherence, consistency, and constraint. We know what TON 618 could not have done, what it could not violate, and what pathways are forbidden by physics. Within those boundaries, multiple presents remain possible. The black hole today exists as a range of allowed realities rather than a single confirmed state. And that leads to a final tension. When the present cannot be checked, certainty shifts away from observation and towards structure. The question becomes not what is it now, but what must it be consistent with? In confronting TON 618, science is forced to operate without the anchor of the present. And that raises a critical issue. When the present itself cannot be verified, where does scientific certainty truly reside? At this point, the nature of astronomical science must be redefined. Observing objects like TON 618 is not analogous to watching a process unfold. It is closer to excavation. Astronomers do not witness events as they happen. They uncover remnants left behind by light that departed long ago. In this sense, light functions as a fossil record. Each photon carries encoded information about conditions at the moment of its emission, preserved across cosmic time. When we collect that light, We are not observing reality in motion, but interpreting traces. This makes astronomy fundamentally historical. Like archaeologists reconstructing ancient civilizations from fragments, scientists rebuild cosmic narratives from incomplete evidence. Spectral lines become tools. Brightness variations become clues. And models serve as hypotheses about how the past must have unfolded. There is no direct access to the full sequence of events. The process itself is never observed. Only its outcome frozen in radiation. This perspective reshapes expectations. Archaeology does not promise total certainty. It works within constraints, cross-checks evidence, and accepts ambiguity where records are missing. Astronomical science operates in the same way, but on a far grander scale. The universe does not preserve everything. It leaves behind partial imprints, eroded by distance, noise, and time. From these, we infer histories that are consistent, not complete. Ton 618 exemplifie this limitation. The light we analyze tells us about extreme mass, intense accretion, and early existence. It does not tell us every step that led there. Entire phases may be invisible, compressed into epochs we cannot resolve. The fossil record is sparse, and yet, reconstruction proceeds. This is not a weakness of science, but its operating mode. Knowledge is assembled through coherence rather than direct replay. Competing scenarios are evaluated not by observation of the event itself, but by how well they account for the surviving traces. In this framework, certainty is replaced by plausibility. The goal is not to reproduce the past exactly, but to identify the narrow range of histories that could have produced the evidence we see. This approach has limits. Just as archaeology cannot recover every detail of a vanished society, cosmology cannot retrieve every moment of early cosmic evolution. Some information is permanently lost. Light carries only what it carried at emission. Everything else is gone. Recognizing this forces a shift in how we judge explanations. The question becomes not whether a model is provable in the traditional sense, but whether it is the most consistent reconstruction available. Ton 618 challenges us precisely because its fossil record is so extreme. It stretches reconstruction to its breaking point. And that leads to a deeper reflection. If astronomy is, at its core, the archaeology of light, then understanding the universe means accepting that some chapters will always be inferred, never observed. The boundary between knowledge and speculation is not fixed by technology, but by time itself, and that raises the final tension of this act. If science reconstructs history from fragments of light, where exactly does reconstruction end and irreducible uncertainty begin? At this stage, the paradox surrounding Ton 618 can no longer be dismissed as a problem of poor measurement. The observational data are internally consistent. Independent instruments, different surveys, and separate analytical techniques converge on the same picture. The redshift is well constrained. The luminosity is extreme but stable. The inferred mass remains enormous across methods. The uncertainties are real, but they are not large enough to dissolve the contradiction. Expanding error bars does not restore comfort. The numbers may shift, but the tension survives. This is a critical moment in scientific reasoning. When data persist and disagreement remains, attention must turn elsewhere. The most likely candidate is not the observation, but the framework used to interpret it. Models of black hole growth rely on assumptions about early cosmic conditions, accretion behavior, feedback efficiency, and timescales. These assumptions work remarkably well in most contexts. But TON 618 occupies an edge case where small cracks become visible. The question is not whether the models are wrong in general. It is whether they are incomplete when pushed to extremes. Perhaps growth in the early universe followed pathways that are no longer accessible today. Perhaps accretion behaved differently under primordial conditions. Or perhaps the initial state of the universe itself allowed structures to form faster than current models anticipate. None of these possibilities require the data to be false. They require the framework to be flexible. This is how science typically advances. Observations do not collapse theory outright. They expose its boundaries. When an object consistently refuses to fit, the response is not to discard the data, but to re-examine the assumptions that make the data meaningful. TON 618 may represent such a boundary case. It highlights where a successful model begins to strain. This does not signal failure. It signals opportunity. Adjusting a framework does not mean abandoning rigor. It means refining the map to include previously unexplored terrain. The discomfort arises because frameworks feel stable until they are challenged. Here, the challenge is explicit. Either the early universe permitted more rapid structural assembly than expected, or our understanding of black hole growth is missing a crucial phase. In both cases, the data remain intact. What wavers is interpretation. This distinction matters deeply. Science rests on trust in measurement, but it progresses through revision of explanation. TON 618 forces that distinction into the open. It asks us to choose carefully. When observation stands firm, but models begin to wobble, the rational response is not to doubt reality, but to expand understanding. And that leads directly to the core question of this section. When the data hold and the framework trembles, where should scientific confidence truly be placed? By now, a pattern has become unmistakable. Many limits in astrophysics can be stretched. Space can expand, accommodating ever larger structures. Energy output can increase, reaching scales once thought impossible. Even mass, under the right conditions, can grow far beyond familiar bounds. But time behaves differently. It does not stretch in response to demand. It cannot be borrowed, accelerated, or stockpiled. Time advances at its own pace, indifferent to the needs of any physical process. This is what makes the paradox of TON 618 uniquely severe. Every proposed solution eventually collides with the same wall. Growth requires duration. Assembly requires sequence. Evolution requires order. And all of these are constrained by time in a way that cannot be negotiated. In most astrophysical problems, time acts as a background parameter. It sets a scale, but rarely becomes the central obstacle. Here, it does. No matter how extreme the assumptions about accretion efficiency, seed mass, or environmental conditions, the clock remains unforgiving. One can imagine more fuel, denser gas, or stronger gravity, but one cannot imagine more time than the universe has already provided. This transforms time from a passive coordinate into an active physical constraint. TON 618 forces us to confront time not as a bookkeeping device, but as a limiting factor that shapes what can exist. In this sense, the black hole does something subtle but profound. It turns chronology into physics. The question is no longer simply how black holes grow, but when growth is even possible. This reframing exposes a hierarchy of limits. Space yields, energy adapts, mass accumulates. Time does not. It sets an absolute boundary that cannot be bypassed without revising fundamental assumptions. That is why the discomfort surrounding TON 618 persists. The data do not ask for minor adjustments. They press against a boundary that feels final. Either something allowed growth to occur faster than we currently believe possible, or our understanding of early cosmic time itself is incomplete. Both options are unsettling. Both imply that time, not matter or energy, is the true bottleneck. In confronting this, science reaches a moment of humility. There are limits that cannot be engineered around. Some constraints are written into the structure of reality. TON 618 exposes one of them. It demonstrates that even in a universe of immense freedom, where extremes abound, time remains the ultimate arbiter. And this realization sharpens the question at the heart of Act 6. If time truly represents a hard boundary, one that cannot be stretched or circumvented, what escape routes, if any, remain for our current models? At this point, TON 618 no longer behaves like a problem waiting to be solved. It behaves like a boundary being revealed. The volume of observational data is not small, nor is it fragmentary. Measurements are consistent across methods, wavelengths, and independent analyses. The difficulty does not arise from missing information, but from what the information implies. Each confirmed detail opens more explanatory gaps than it closes. The mass raises questions about formation. The timing raises questions about evolution. The distance raises questions about what it even means to observe. None of these tensions come from error. They come from excess. The object does not contradict data, it exceeds interpretation. The frameworks used to describe black hole growth were built to handle gradual assembly, sequential causality, and sufficient time. TON 618 sits beyond the comfortable reach of those ideas. As a result, explanation fragments, multiple scenarios remain possible, none decisive, none dominant. This is not because science lacks rigor, but because the phenomenon has moved ahead of the language designed to describe it. In such cases, progress no longer looks like resolution. It looks like exposure. The role of the object is not to be neatly explained, but to mark where explanation stops working. The certainty of numbers contrasts with the instability of meaning. What remains solid is not an answer, but a question, one that persists precisely because the data are sound. When an object forces inquiry without yielding closure, questioning itself becomes the outcome. And that leaves only one thing unresolved. When the question is the result, how should science move forward? There comes a moment in every long inquiry when progress no longer means moving forward. It means stopping, not because the path is exhausted, but because continuing with the same assumptions would distort what has already been learned. TON 618 marks such a moment. It does not deliver a conclusion, and it does not resolve the questions it raises. Instead, it forces a pause. The data remain valid. The methods remain sound. The scientific structure does not collapse. What changes is confidence in the sufficiency of current understanding. TON 618 does not break science. It reveals where science, as it currently stands, reaches its edge. Beyond this point, familiar intuitions no longer scale. Growth, time, causality, and observation all begin to behave in ways that strain existing frameworks. This is not failure. It is a boundary condition, a recognition that certain questions cannot yet be pushed further without first re-examining the ground they stand on. The object demands intellectual restraint. It asks for slower thinking, not faster answers. It reminds us that some discoveries do not advance knowledge by adding facts, but by exposing limits. After this point, questions are no longer framed the same way. What seemed like problems to solve become assumptions to question. What once felt solid becomes provisional. Ton 618 stands not as an endpoint, but as a mandatory stopping place, a moment where understanding must catch up to observation. And standing here, with no resolution offered and no shortcut available, only one question remains. If there exists a black hole that forces science to slow down and become more humble, is this the place where we need to stop and look back at the entire journey? After confronting a case that challenges time itself, it becomes important to return to the black holes whose existence rests on solid, repeatable data. In science, naming is never a cosmetic act. A name is not given to help memory, nor to create familiarity. It is assigned to establish distinction. To name an object is to declare that it can be reliably separated from noise, speculation, and ambiguity. In astronomy, this distinction carries exceptional weight. A named black hole is not simply an idea or a hypothesis. It is an object anchored to a specific body of evidence, repeated observations, consistent signals, and converging measurements. Each name functions as a label for a dataset, not for a story. Without sufficient evidence, no name is granted. Objects may be suspected, modeled, or discussed for years without crossing that threshold. The absence of a name is not an oversight. It is an intentional restraint. It signals that the evidence has not yet stabilized into something that can be independently verified. In this way, naming becomes a reflection of confidence, not curiosity. When a black hole receives a designation, it marks a transition from doubt to confirmation. This transition is procedural, not emotional. It does not depend on how striking the object appears, or how dramatic its implications may be. It depends on whether its existence can be tested, challenged, and reproduced across instruments and teams. The scientific name therefore encodes a judgment that the object is no longer provisional. It has crossed from possibility into record. This practice protects the integrity of the field. Without it, extraordinary claims would accumulate faster than verification. Naming enforces discipline. It draws a boundary between what is suspected and what is established. Each named black hole represents a case where data have outpaced doubt. The criteria are demanding by design. Signals must persist over time. Alternative explanations must be ruled out. Independent methods must agree. Only then does the community accept the responsibility of naming. This responsibility matters because names endure. Once assigned, they anchor future research, comparisons, and conclusions. A premature name would fossilize uncertainty. A delayed name preserves rigor. In this sense, scientific naming is conservative by necessity. It favors reliability over novelty. The act of naming does not end inquiry, but it stabilizes it. It creates a reference point from which deeper questions can safely be asked. This is why the return to named black holes matters after extreme cases. It reminds us that science advances not only by pushing boundaries, but by carefully marking where solid ground begins. And that brings the decision into focus. If naming is a scientific commitment rather than a label, then the essential question follows naturally. If giving a name is a scientific decision, what standard must be met before that decision is justified? In science, assigning a name is inseparable from accepting responsibility. A named object is no longer shielded by ambiguity. It becomes accountable to the entire community. Once a black hole is given a designation, the data behind that decision are no longer private or provisional. They are placed into a shared space where anyone with the appropriate tools can test them. This is not a symbolic gesture. It is an operational commitment. Naming signals that the evidence is robust enough to withstand independent scrutiny. Other researchers must be able to reproduce the measurements, challenge the interpretations, and verify the conclusions using different instruments and methods. If discrepancies appear, they are not dismissed. They are traced back through the data pipeline, calibration choices, assumptions, noise handling, and modeling steps can all be re-examined. A name invites this process. It does not protect against error. It exposes the possibility of error openly. This exposure is intentional. Scientific credibility is not built on being correct forever, but on being correctable. To name an object is to accept that future data may refine, adjust, or even overturn parts of the original interpretation. The name remains, but its meaning can evolve as understanding deepens. This is why naming is conservative. It is not an act of triumph, but an act of accountability. The community does not ask whether the object is impressive. It asks whether the evidence is traceable. Can every claim be followed back to a measurement? Can every inference be challenged without collapsing the case? If the answer is yes, naming becomes appropriate. If not, restraint is maintained. In this way, naming functions as a built-in error correction mechanism. It creates a stable reference point while leaving room for revision. The object is fixed in the record, but its interpretation is not frozen. This balance is essential. Without names, knowledge cannot accumulate coherently. Without accountability, names would harden speculation into dogma. The practice of naming holds these two forces in tension. It allows science to move forward while remaining open to self-correction. That is why a scientific name carries weight. It represents a willingness to be checked, questioned, and, if necessary, corrected in public. And that leads to a deeper boundary question. When responsibility is placed on data rather than authority, where exactly does the line fall between what is considered certain and what remains provisional in scientific practice? A clear boundary separates hypothesis from confirmation. A hypothesis proposes that something could exist. It is an invitation to investigate, not a declaration of reality. Confirmation demands more. It requires converging data that persist across time. Instruments and methods. In astronomy, this distinction is especially strict. Many candidates appear promising at first glance. Signals emerge. Patterns suggest presence. Models align with expectation. But possibility alone is never enough. Not every candidate becomes an accepted object. Many remain suspended in a provisional state for years, sometimes decades. This is not due to neglect, but design. Time itself acts as a filter. A real object will continue to announce itself. Its signals will reappear. Its effects will remain measurable as technology improves and perspectives change. A false positive, by contrast, tends to fade, fragment, or collapse under closer inspection. This is why confirmation cannot be rushed. Data must accumulate independently. Measurements must agree without coordination. Alternative explanations must be systematically excluded. Only when evidence converges from multiple directions does a hypothesis cross the threshold into confirmation. Even then, the process is cautious. Science advances slowly here because the cost of error is high. Misclassification can mislead entire research programs, distort statistics, and propagate assumptions that take years to undo. Slowness is therefore a feature, not a flaw. It is a protective mechanism against confusion. Hypotheses are allowed to exist in an open state, precisely because science does not demand immediate resolution. Some hypotheses strengthen with time, accumulating support until recognition becomes unavoidable. Others weaken, not through dramatic refutation, but through quiet inconsistency. The passage of time reveals which is which. This temporal dimension is essential. A claim that cannot survive repeated scrutiny eventually loses standing, regardless of how compelling it once appeared. In this way, science resists premature closure. It tolerates uncertainty longer than intuition might prefer, because certainty earned too quickly is often fragile. The distinction between hypothesis and confirmation is therefore not philosophical. It is procedural. It is enforced by patience, repetition, and restraint. And that leads to the decisive question. When a hypothesis persists without resolution for an extended time, what ultimately determines its fate? Among all known categories of black holes, stellar mass black holes are the easiest to confirm. Their discovery does not rely on indirect inference across cosmic distances, but on local, repeatable dynamics. Most are identified within binary star systems, where a visible star orbits an unseen companion. The key evidence comes from motion. By measuring the orbital period, velocity, and geometry of the system, astronomers can calculate the mass of the invisible object using well-tested gravitational laws. When that mass exceeds the maximum possible for a neutron star, the conclusion becomes unavoidable. The object cannot be anything other than a black hole. This method is powerful because it is grounded in classical dynamics rather than exotic assumptions. The measurements are repeatable. The orbits can be tracked over time. Independent teams can analyze the same system and arrive at the same mass estimate. These black holes also fit cleanly into existing models of stellar evolution. Massive stars exhaust their fuel, their cores collapse, and under the right conditions, a black hole forms. There is no need to invoke unfamiliar physics or extreme environments. The process is violent, but well understood. As a result, stellar mass black holes were among the first to be accepted as real physical objects rather than theoretical curiosities. The data supporting them are comparatively robust. Uncertainties exist, but they are bounded. Errors can be quantified. Assumptions can be tested. This does not mean every individual case is trivial, but the overall framework is stable. These objects anchor black hole science to measurable reality. They demonstrate what confirmation looks like when nature cooperates with observation. Their relative accessibility explains why they form the foundation of black hole catalogs. They provide a baseline against which more distant and massive candidates are judged. And yet, this very clarity highlights a contrast. If stellar mass black holes are confirmed so directly, using nearby systems and straightforward physics, then the question naturally arises. If this group is the easiest to verify, what is it that makes other classes of black holes so much harder to confirm? Binary star systems provide one of the most reliable laboratories for confirming black holes. Their strength lies in dynamics rather than appearance. In these systems, two objects are gravitationally bound, orbiting a common center of mass. Often, only one component emits visible light. The other remains dark, revealing itself solely through its gravitational influence. This asymmetry is crucial. By tracking the motion of the visible star, its speed, orbital shape, and period, astronomers can reconstruct the mass of its unseen partner with high precision. When that inferred mass exceeds the theoretical upper limit for a neutron star, the interpretation becomes constrained. No known form of stable matter can account for such a mass without collapsing further. The unseen object must therefore be a black hole. What makes these systems especially powerful is not a single dramatic example, but repetition. Similar configurations appear in many regions of the galaxy. Different stars, different environments, different orbital parameters, yet the same pattern emerges. A luminous companion, an invisible partner, and a mass that defies alternatives. This repetition matters. Science does not rely on isolated coincidences. When the same dynamical signature appears again and again, confidence increases not through belief, but through statistics. Each new system reinforces the framework. Independent observations, carried out by different teams using different instruments, converge on the same conclusion. The model does not need to be reinvented each time. It is stress-tested. Minor variations exist, but the core inference remains stable. This is how certainty accumulates, not from a single perfect measurement, but from consistent outcomes across diverse cases. Binary systems therefore play a foundational role in black hole science. They transform abstract prediction into empirical pattern. They show that black holes are not rare anomalies, but repeatable outcomes of stellar evolution. The invisible component is not guessed, it is required by the data. And because these systems can be observed over long periods, uncertainties shrink rather than grow. Orbits refine. Masses converge. And alternative explanations lose viability. The reliability comes from patience and multiplicity. Each confirmed system adds weight, not by novelty, but by familiarity. This is a different kind of excitement, one rooted in confirmation rather than surprise, and it raises a subtle shift in perspective. When a model reproduces itself across many independent systems, the question changes. It is no longer about whether the phenomenon exists, but about how confidently it can be generalized. When a pattern repeats often enough, certainty is no longer binary. It deepens gradually. And that leads to the central question of this section. When a model repeats itself across many systems, how does that repetition change the level of certainty we assign to it? Our own galaxy provides a unique anchor point in black hole science. At the center of the Milky Way lies a supermassive black hole whose existence is no longer inferred from distant echoes, but traced through direct, long-term observation. Unlike external galaxies, where signals arrive faint and delayed, the galactic center is close enough to allow continuous monitoring. This proximity changes everything. Individual stars can be tracked as they orbit an unseen central mass. Their paths are mapped year after year, decade after decade. The result is not a snapshot, but a time lapse. These stellar orbits reveal a compact object with millions of solar masses confined within an extraordinarily small region. No alternative explanation remains viable. A dense star cluster cannot persist under such conditions. Exotic matter offers no stable solution. The gravitational evidence points unambiguously to a black hole. This object, known as Sagittarius A*, occupies a privileged position in astrophysics. It is not the most massive, nor the most energetic. Its importance lies elsewhere. It is the black hole we can watch evolve. Observations span multiple generations of instruments, improving in precision over time. Each technological advance refines earlier measurements rather than replacing them. The data accumulate rather than reset. This continuity allows uncertainties to shrink and models to be tested repeatedly against reality. Long-term observation also exposes variability. Flares, accretion changes, and subtle shifts become measurable only when viewed across extended timescales. Short surveys would miss these patterns entirely. Here, time becomes an ally rather than an obstacle. The Milky Way's central black hole therefore serves as a calibration point. It grounds theoretical models in a system where assumptions can be checked directly. It provides a benchmark against which more distant, less accessible, black holes are compared. While not every galaxy hosts an identical central object, this one offers something irreplaceable: depth of data. Decades of observation transform inference into confidence. They reveal not just that the black hole exists, but how it behaves. This is why it holds such weight in scientific reasoning. When questions arise about growth, stability, or dynamics, this nearby example acts as a reference. It does not answer every question, but it constrains them, and that highlights a crucial advantage. When observation extends over long periods rather than brief detections, the nature of certainty changes, which brings the focus to the central issue. What does long-term observation give us that distant discoveries, no matter how dramatic, cannot? The confirmation of Sagittarius A times does not depend on seeing the black hole itself. It depends on watching how everything around it moves. At the center of the Milky Way, dense clouds of stars orbit an invisible focus. These stars act as test particles, tracing the gravitational field of an object they never touch and never illuminate. By tracking their motion with extreme precision, astronomers can reconstruct the mass, location, and compactness of the central object. The key lies in orbital mechanics. The paths are not random. They follow predictable trajectories governed by gravity. Some stars complete full orbits in just a few decades, allowing repeated measurements within a human lifetime. As instruments improved, uncertainties shrank. Positions were refined. Velocities became clearer. Over time, the orbits converged on a single conclusion. Millions of solar masses are confined within a region no larger than our solar system. No cluster of ordinary objects can remain stable under such conditions. The gravitational field is too intense, too compact. A black hole is not inferred by assumption, but demanded by the data. This method is powerful precisely because it avoids indirect proxies. There is no reliance on brightness, jets, or high-energy emissions. Even if the black hole were completely quiet, its presence would still be revealed through motion. This makes the case unusually robust. Decades of continuous observation form a coherent narrative. Early measurements predicted future positions. Later observations confirmed them. The system behaves exactly as expected if a supermassive black hole sits at the center. Deviations are small, explainable, and do not accumulate. This long-term consistency is rare in astrophysics. Many distant objects offer only fleeting glimpses. Sagittarius A times offers continuity. It allows hypotheses to be tested against time itself. Incorrect models do not survive repeated orbital cycles. Only those aligned with reality persist. That is why this object stands among the most securely confirmed black holes known. It is not spectacular because of energy output or dramatic visuals. It is convincing because of patience. Motion, measured carefully and repeatedly, becomes decisive evidence. And yet, this raises an important question about confirmation itself. If gravitational motion alone is sufficient to establish the existence of a black hole with such confidence, what additional information do we still seek? And why? For the first time in history, a black hole was not only inferred, but imaged. The object at the center of the galaxy M87 became the first black hole whose presence was confirmed through a direct visual reconstruction. This achievement did not come from a single telescope, but from a planet-scale instrument. By synchronizing radio observatories across the Earth, astronomers created an effective aperture the size of our planet. The result was not a photograph in the everyday sense, but a resolved image of a shadow. This distinction matters. What was captured was not a surface, because a black hole has none. It was the silhouette cast by the event horizon against a glowing background of infalling plasma. The dark region corresponds to light paths bent and captured by extreme gravity, exactly as predicted by general relativity. The size and shape of this shadow matched theoretical expectations with remarkable precision. This was not merely a visual milestone. It was a geometric test of space-time itself. The image of M87 times confirmed that gravity behaves as Einstein's theory predicts. Even in the most extreme regime accessible to observation, deviations would have signaled new physics. None were required. The shadow's symmetry, scale, and stability aligned with models derived decades earlier. This elevated confidence in the framework that underpins modern astrophysics, yet the limits of the image are as important as its success. The picture does not show the interior of the black hole. It does not reveal what happens beyond the event horizon. It offers no information about singularities, quantum effects, or internal structure. The image is a boundary marker, not a window. It confirms where space-time closes off to observation, but nothing beyond that closure. In this sense, the image answers one class of questions while leaving others untouched. It verifies existence and geometry, but not content. It transforms a theoretical boundary into an observed one, without dissolving the mystery behind it. The achievement is therefore both decisive and restrained. It strengthens confidence in established physics, while clearly delineating what observation cannot penetrate. The black hole is seen, but only as an outline, and this contrast sharpens the remaining uncertainty. When the first image of a black hole becomes possible, what questions does that image still leave unanswered? Beyond the Milky Way, the nearest large laboratory for comparison lies in our neighboring galaxy, Andromeda. At its center resides another supermassive black hole, commonly referred to as Andromeda A*. Its proximity makes it uniquely valuable. While still distant on human scales, it is close enough to allow meaningful comparison with the black hole at the heart of our own galaxy. This comparison immediately reveals an important fact. Similarity in location does not imply similarity in behavior. Andromeda A times is more massive than the Milky Way's central black hole, yet it is far less active. Its surroundings show weaker signs of accretion and lower energetic output. This contrast challenges any assumption that central black holes follow a single evolutionary script. Both galaxies are large spirals. Both host supermassive black holes. Yet their central engines operate differently. The difference cannot be explained by mass alone, nor can it be reduced to age or environment in a simple way. Instead, it points to a more complex interplay between galaxy structure, gas supply, merger history, and feedback processes. Comparing these two systems highlights the limits of generalization. There is no universal template that dictates how a galactic center must behave. The black hole does not act independently. Its state reflects the broader history of its host galaxy. Periods of activity in quiescence are shaped by past interactions, inflows of matter, and internal dynamics. Andromeda A times demonstrates that even with a larger mass, a black hole can remain comparatively quiet. This quietness is not a failure of theory, but a reminder of diversity. The comparison shifts the scientific question. Instead of asking what a typical supermassive black hole does, we must ask under what conditions different behaviors emerge. By placing the Milky Way alongside Andromeda, patterns begin to loosen rather than tighten. The range of possibilities expands. Central black holes appear not as standardized components, but as responsive elements embedded within unique galactic ecosystems. This comparative approach strengthens science by resisting oversimplification. It prevents single-case reasoning from hardening into rule. Each additional galaxy adds context, revealing variance rather than conformity. Andromeda A times, therefore, plays a critical role. It shows that proximity alone does not guarantee similarity, and that mass alone does not dictate activity. Diversity becomes the signal, and with that diversity comes a deeper question. When galaxies differ so fundamentally in structure and history, do their central black holes obey a shared set of rules, or only broad constraints? Within the growing catalogue of confirmed black holes, a small number stand far outside familiar scales. These objects do not merely extend known ranges, they occupy regimes that strain expectation. Their inferred masses exceed billions of solar masses, pushing well beyond what early models of black hole growth were designed to accommodate. What makes these cases credible is not a single dramatic estimate, but convergence. Their masses are derived through multiple, independent methods: stellar dynamics, gas motion, luminosity modeling, and gravitational influence on surrounding structures. Each approach carries uncertainty, but the uncertainties overlap rather than diverge. Error margins may shift the exact value, yet they do not erase the extremity. Even under conservative assumptions, these black holes remain extraordinary. They are not statistical noise. They are rare, but persistent. Observationally, such objects are difficult. They are distant, often embedded in complex environments, and their signals are faint or indirect. Years of data accumulation are required to isolate their influence from background processes. This difficulty explains their scarcity. But scarcity does not imply insignificance. In science, rare cases often carry disproportionate weight. They test the outer limits of theory. These extreme black holes function as stress tests for existing models. Most frameworks are built to explain typical behavior, They perform well across the majority of observations. But when confronted with outliers, assumptions are exposed. Growth rates, accretion, histories, merger, pathways, processes that appear adequate in average cases begin to look insufficient. Importantly, these extreme objects do not invalidate the broader model. They reveal its boundaries. They show where extrapolation becomes unreliable. As exceptions, they force refinement. Either additional mechanisms must be incorporated, or constraints must be clarified. The presence of such black holes therefore shifts emphasis. The question is no longer whether the model works in general, but how it handles its edges. Extreme cases act as anchors for revision. They demand explanation without allowing wholesale dismissal of established understanding. This is the productive role of an exception. It sharpens theory rather than dissolving it. The challenge lies in response. When confronted with objects that clearly exist but sit uncomfortably within current frameworks, science faces a choice. Should the model be stretched to include them, or reshaped to accommodate them more naturally? Phoenix A times occupies a distinctive position in black hole catalogues because it is recognized not primarily by mass, but by consequence. Its identification is anchored in the extraordinary energy it injects into its environment rather than in a direct, dynamical mass measurement. In the heart of the Phoenix cluster, vast cavities carved into the hot intracluster gas reveal a sustained and violent energy output. These structures cannot be explained by stellar processes or galaxy-scale phenomena. Their size, symmetry, and persistence point to a central engine operating far beyond ordinary astrophysical sources. The black hole's presence is inferred through feedback through what it does, not merely through what it weighs. This represents a different pathway to confirmation. Instead of tracing orbital motion or imaging a shadow, astronomers analyze the response of the surrounding medium. Shock fronts, displaced gas, temperature gradients, and suppressed cooling flows collectively form a coherent signature. Each piece of evidence alone might be ambiguous. Together, they converge. The energy budget required to produce these effects exceeds any plausible alternative. The catalog entry for Phoenix A times, therefore, rests on environmental causality. The black hole is necessary to explain the observed state of the cluster. This approach underscores an important expansion in how confirmation operates. Mass remains relevant, but it is no longer the sole organizing principle. In extreme systems, impact becomes measurable, where mass becomes inaccessible. Direct measurements are impossible at such distances and scales. But the imprint left on the environment is unmistakable. By accepting Phoenix A times into catalogues, science acknowledges that confirmation can proceed through consequence as well as through direct measurement. This does not weaken standards. It adapts them to context. The data are still repeatable. The interpretations still testable. Independent observations of the cluster reproduce the same features. Alternative explanations fail consistently. The black hole's role as an energy regulator becomes the dominant line of evidence. Phoenix A times thus exemplifies indirect confirmation at its most rigorous. It shows that when an object reshapes its surroundings on cluster-wide scales, the requirement for proof shifts from direct detection to explanatory necessity. This has implications beyond a single case. It suggests that in certain regimes, the environment itself becomes the detector. The catalogue does not merely list objects by intrinsic properties, but by their measurable influence. And this reframes the criteria of centrality. If a black hole's defining signature is its feedback rather than its mass, then the hierarchy of evidence changes. which leads directly to the unresolved question. If environmental impact is sufficiently strong and unambiguous, does mass still deserve its place? As the central criterion of confirmation, TON 618 appears in black hole catalogues under a special kind of acknowledgement. It is not listed as an ordinary entry, nor treated as a routine data point. Instead, it is marked as an extreme case, one that is accepted, but accompanied by caution. The observational data supporting TON 618 are internally consistent. Independent measurements of luminosity, emission lines, and dynamical indicators converge on an object of extraordinary mass. The debate does not center on whether the signals are real. It centers on how they should be interpreted. Unlike speculative candidates, TON 618 is not excluded because of poor data. It remains in the catalog precisely because the data are robust, even if their implications are unsettling. The tension arises not from a violation of physical laws, but from a strain on existing growth models. TON 618 does not break physics. It stretches the frameworks built to describe typical evolution. For this reason, its catalog entry carries qualifiers. Uncertainty is not hidden, it is explicitly attached. This is a deliberate choice. Science does not remove an object simply because it is difficult, nor does it elevate it without reservation. Instead, it records the object along with the limits of current understanding. The catalog becomes a layered document. Some entries represent well-settled cases. Others, like TON 618, signal active boundaries of interpretation. The warning is not a dismissal. It is a signal to future work. It tells researchers where assumptions are most vulnerable and where new data would have the greatest impact. By keeping TON 618 inches the catalog, science acknowledges two things at once. First, that the object is real within the limits of observation. Second, that the theoretical context is incomplete. This dual stance preserves integrity. Removing the object would deny evidence. Treating it as fully understood would overstate confidence. The compromise is transparency. The catalog entry communicates not certainty alone, but condition. It reflects a mature posture acceptance without closure. TON 618 thus functions as a reference point for uncertainty itself. It shows that cataloging is not merely an act of classification, but an act of communication. Each entry conveys how much is known and how much remains unresolved. In this way, uncertainty is not a flaw in the record, but part of the record, and that brings the question into focus. When an object is officially recorded together with explicit uncertainty, what is science really saying about its state of knowledge? No scientific catalog is ever complete. This is not a temporary limitation, but a structural reality. Black hole catalogs, like all observational records, are snapshots taken under specific technological and conceptual conditions. They reflect what can be seen, measured, and interpreted at a given moment, not what exists in total. As instruments improve, sensitivity increases, resolution sharpens, and new windows open. Objects once invisible begin to emerge. Others are reclassified, refined, or reinterpreted. The list changes not because reality changes, but because access does. Each generation of observation carries its own constraints: detection thresholds, wavelength coverage, temporal baselines, all impose limits. What falls below those limits remains absent, not because it is rare or non-existent, but because it is inaccessible. This absence is expected. It is built into the practice. Catalogues are therefore provisional by design. They are living documents, continuously revised as technology advances and understanding deepens. The absence of completeness is not a weakness. It is a safeguard. Claiming a finished list would imply that observation has reached its final form. That discovery has an endpoint. Science resists that implication. Instead, it treats catalogues as tools rather than verdicts. They organize what is known without pretending to exhaust what is possible. The gaps are as informative as the entries. They mark regions where sensitivity is insufficient, where methods struggle, or where theory has yet to guide observation effectively. In this way, incompleteness becomes informative. It directs future effort. Each update redraws the boundary between the known and the unknown. Older catalogues are not discarded, they are contextualized. They show how knowledge expands unevenly, shaped by capability rather than intention. Understanding this prevents misinterpretation. A catalogue is not a census of the universe. It is a record of contact points between observation and reality. What is listed reflects where that contact has occurred. What is missing reflects where it has not yet reached. Accepting this reframes how catalogues should be read. They are not claims of totality, but maps of progress. And that perspective raises the central question. If scientific catalogues are always incomplete by necessity, how should we understand what they truly represent? Despite the growing catalogues and increasingly sophisticated instruments, most black holes remain unknown. This is not surprising. By their nature, black holes do not emit light, unless they interact with their surroundings in a detectable way. They leave no obvious signal. Many exist in isolation, drifting through space without accreting gas, without producing jets, without disturbing nearby matter. In such cases, there is nothing to see. Others reside in environments too quiet or too sparse to generate measurable effects. Even within galaxies, only a fraction of black holes announce themselves through radiation or dynamics that exceed detection thresholds. The rest remain silent. This silence is not an anomaly. It is the default state. Observational astronomy is biased toward activity. What shines, moves dramatically, or reshapes its environment becomes visible. What does not fades into statistical inference. As a result, the black holes we know are not a random sample. They are the detectable minority. They represent cases where conditions happen to amplify an otherwise invisible object. The majority do not benefit from such amplification. Population models suggest that galaxies should host vast numbers of stellar mass black holes formed over cosmic time. Yet only a small subset has been identified. The discrepancy is not a failure of theory, but a limitation of access. Detection requires interaction. Without it, existence must be inferred indirectly or not at all. This means that current knowledge captures only a thin slice of reality. It is a cross-section defined by observational convenience rather than completeness. What we call the black hole population is therefore highly filtered. It reflects where physics intersects with observability, not where black holes are most common. This has important consequences. Generalizations drawn from known cases must be treated cautiously. Trends may be real, but they are sampled from a biased set. The quiet majority could behave differently, evolve differently, or dominate statistics in ways we cannot yet measure. Acknowledging this hidden population is essential for intellectual honesty. It reminds us that absence of evidence is not evidence of absence. The universe likely contains far more black holes than those listed in any catalogue. What we know is shaped by what reveals itself, not by what exists in total. This perspective reframes confidence. Knowledge becomes conditional. Conclusions become provisional. Understanding expands not by filling in a complete picture, but by gradually widening the window through which we look. And that brings the final tension into focus. When most black holes remain hidden, how representative can our current understanding truly be? The black holes that carry names represent only a small fraction of what likely exists. They are the visible edge of a much larger population, revealed not because they are typical, but because circumstances make them observable. These named objects are invaluable. They allow theories to be tested, equations to be constrained, and predictions to be checked against reality. Without them, black hole physics would remain abstract. Yet, their usefulness should not be mistaken for completeness. What is confirmed is not synonymous with what is common. The majority of black holes do not announce themselves with bright emissions, dramatic jets, or measurable environmental impact. They persist quietly, embedded in regions where detection is difficult or impossible with current tools. As a result, the objects that dominate our discussions are those that cooperate with observation. They shape theory not because they are representative, but because they are accessible. This creates an asymmetry in understanding. Models are calibrated on the minority we can see, then extended carefully toward the majority we cannot. This extension is provisional by necessity. It reflects a field still in an early phase of exploration. In many respects, black hole science today resembles early stellar astronomy, when only the brightest stars were catalogued and entire populations remained unseen. Progress came not from finishing the list, but from deepening sensitivity. The same is true here. Each improvement in instrumentation reveals layers previously hidden. Each new method exposes behaviors that challenge assumptions built on limited samples. This means that current confidence must remain conditional. The named black holes are anchors, not endpoints. They stabilize theory, but they do not close it. They tell us how gravity behaves under extreme conditions we can access, not how it behaves everywhere. Recognizing this prevents overreach. It keeps interpretation aligned with evidence rather than extrapolation. The journey toward understanding black holes is therefore not nearing completion. It is still unfolding. What we have learned so far is foundational, but incomplete. The surface has been touched, not penetrated. And as history suggests, deeper observation rarely simplifies the picture. It complicates it, which leads naturally to the final question of this arc. If what we know today is only the visible surface, what happens when we begin to observe far deeper than we ever have before? Even the black holes we can confidently name and measure are not permanent. Over enough time, they too must follow the deeper laws of thermodynamics. In physics, permanence is not a default property. It must be justified, and it rarely is. Most structures that appear stable do so only within a limited frame, limited in scale, in energy, or in time. Atoms decay, stars exhaust fuel, galaxies merge and disperse. Stability, when observed, is almost always conditional. Black holes were once treated as an exception. Their defining feature the event horizon, seem to seal them off from change. Nothing escapes. Nothing erodes them from the outside. For decades, this led to an implicit assumption: black holes, once formed, are forever. Not eternal in a poetic sense, but permanent in a physical one. They could grow, they could merge, but they would not fade. Thermodynamics challenges this assumption at its foundation. The laws governing energy, entropy, and irreversibility apply universally. They do not exempt extreme objects. They do not pause at horizons. If black holes are physical systems, and all evidence says they are, then they must participate in the same accounting as everything else. This reframes the concept of death. In physics, death is not an event. It is not a moment. It is a trajectory, a slow redistribution of energy, a drift toward equilibrium, a loss of structure rather than a sudden collapse. When applied to black holes, this idea feels counterintuitive. These objects represent maximum compression, maximum gravity, maximum isolation. If anything should resist change, it should be them. And yet, thermodynamics is indifferent to intuition. It does not ask what feels stable. It asks what configurations can persist without violating entropy over sufficiently long timescales. Even the most compact systems are subject to subtle processes that alter them. These processes are not violent. They do not announce themselves with explosions or transitions. They operate quietly, relentlessly, governed by probability and statistics rather than force. The implication is unsettling. If black holes are not exempt from thermodynamic evolution, then their apparent permanence is an illusion of scale. They last longer than stars, longer than galaxies, longer than almost any structure we know. But longer is not the same as forever. The universe does not grant absolutes. It grants durations. From this perspective, black holes are not endpoints. They are long-lived phases, extremely stable, extremely slow to change, but still embedded in time. Their death, if that word even applies, is not a catastrophic disappearance. It is a gradual unwinding, a process so slow that it dwarfs all familiar cosmic timescales, yet inevitable all the same. This shift in understanding matters. It transforms black holes from final sinks into participants in a broader thermodynamic story. They no longer sit outside the arrow of time. They are carried by it. The question is not whether they will change, but why change is unavoidable. If even black holes are not eternal, what is it that forces them to evolve? Hawking radiation does not arise from violence or instability. It emerges from the quiet rules of quantum physics operating near a black hole's boundary. Contrary to common intuition, this radiation does not originate from inside the black hole. Nothing escapes from within the event horizon. Instead, the effect appears just outside it, in a region where gravity is extreme, but space still allows physical processes to unfold. At the quantum level, empty space is not truly empty. The vacuum constantly fluctuates, producing pairs of virtual particles that briefly appear and annihilate each other. Under normal conditions, this process leaves no trace. Near a black hole, however, the balance can be disturbed. The intense gravitational gradient at the edge of the event horizon can separate these particle pairs. One falls inward, beyond the point of no return. The other escapes outward, becoming real radiation. To an outside observer, This looks as though the black hole is emitting particles, yet nothing has come from inside. The radiation is born from the vacuum itself. This distinction is crucial. Hawking radiation is not a leak. It is not erosion from within. It is a boundary effect, produced by quantum mechanics acting in curved spacetime. The black hole does not explode or flare. It does not glow brightly. The process is extraordinarily weak. For stellar mass and supermassive black holes, the radiation is so faint that it is completely drowned out by the cosmic background. There is no detectable signal, no dramatic signature. And yet, the theoretical implication is profound, because the escaping particle carries energy, and because energy must be conserved. The system as a whole changes. The black hole loses a tiny amount of mass. This loss is not noticeable on human or even astronomical timescales. It unfolds over durations that exceed the age of the universe by many orders of magnitude. But it is continuous. It does not switch off. The black hole cannot prevent it without violating the principles of quantum physics. What makes Hawking radiation unsettling is not its strength, but its persistence. It represents a slow accounting process enforced by fundamental laws. No matter how massive or isolated the black hole is, the mechanism applies. There is no threshold below which it stops. The black hole appears stable because the timescale is immense, not because the process is absent. In this way, Hawking radiation introduces time back into the story of black holes. Objects once thought to be eternal become participants in gradual change, not through catastrophe, but through inevitability. And that brings the implication into focus. If this radiation exists and never fully ceases, how does it alter a black hole over time? Hawking radiation exists, but it does not act with urgency. Its effect on a black hole is extraordinarily weak. For objects as massive as known black holes, the rate of energy loss is so small that it is functionally invisible on any familiar timescale. The black hole does not shrink in a noticeable way. Its mass does not fluctuate. Its gravitational influence remains unchanged across millions and billions of years. From the perspective of stars, galaxies, and even cosmic evolution as we usually describe it, the black hole appears completely stable. This is why Hawking radiation has never been observed directly. The signal is not merely faint, it is overwhelmed by every other source of radiation in the universe. Cosmic background radiation, starlight, interstellar, dust emission. All of these drown it out entirely. Even in principle, isolating such a signal with present technology is impossible. The effect exists not as an observational phenomenon, but as a theoretical certainty. Its importance does not lie in what we can measure now, but in what must happen if the laws of physics hold indefinitely. The energy loss is continuous, but it unfolds at a pace that defies intuition. Each escaping particle removes an almost negligible fraction of the black hole's mass. The cumulative effect only becomes meaningful when considered over spans of time that far exceed the current age of the universe. This forces a shift in perspective. The death of a black hole is not something that happens within cosmic history as we normally define it. It does not belong to the era of stars, galaxies, or even dark energy-dominated expansion. It belongs to a future so distant that conventional milestones lose relevance. In that future, change is not marked by events, but by slow drift. The black hole does not collapse or explode. It does not cross a clear boundary from existence to non-existence. It simply diminishes, gradually, imperceptibly. Its mass decreases as energy leaks away into space. The process is so slow that for most of its lifetime, the black hole behaves as if nothing is happening at all. Stability is an approximation produced by timescale. What appears permanent is simply changing too slowly to notice. This reframes the meaning of decay. It is not synonymous with instability. It is a quiet accounting enforced by thermodynamics. The black hole loses energy because it must, not because it is disrupted. Its eventual disappearance is not a failure of structure, but the final consequence of universal laws applied without exception. To understand black hole death, one must abandon human scales of time entirely. The process stretches beyond comprehension, beyond narration, beyond any practical observation. And this brings the question into sharp focus. When we say that this evaporation takes a very long time, how long is very long? The lifetime of a black hole is not a fixed value. It is not assigned at birth, nor does it depend on its surroundings in a simple way. Instead, it is determined almost entirely by mass. The more massive the black hole, the longer it resists evaporation. This relationship is not linear. As mass increases, lifetime grows dramatically. A small increase in mass leads to an enormous increase in duration. When physicists translate the equations of Hawking radiation into time, the results are startling. Even a black hole with the mass of a star would persist for an unimaginably long span. A supermassive black hole would endure for durations that dwarf every familiar cosmic epoch. These are not figures measured in billions of years. They exceed the current age of the universe by factors so large that ordinary comparison breaks down. The numbers quickly leave the realm of intuitive meaning. Writing them down becomes an abstract exercise. They are correct, but they do not communicate experience. In this regime, time stops functioning as a narrative tool. There are no events to mark the passage, no stages that feel distinct. The black hole simply exists, slowly losing mass at a rate so small that it may as well be constant. For most of its lifetime, nothing about it changes in any noticeable way. From any reasonable observational standpoint, it appears eternal, yet mathematically, it is not. The equations insist that given enough time, evaporation will complete. This creates a tension between perception and calculation. Our senses and instincts are calibrated to short spans. Thousands of years feel long. Millions feel abstract. Billions already strain comprehension. The lifetimes predicted for black holes lie far beyond that. They belong to a future where stars are gone, galaxies are dark, and the universe itself has changed character. In such a context, calling this duration a lifetime feels misleading. It is not a life in any biological or even astronomical sense. It is a parameter describing how long a physical process takes to asymptotically reach completion. Time becomes a variable stripped of story. It is no longer something that happens. It is something that accumulates. This reframing matters because it reveals how limited our usual language is. When we say a black hole lives for a certain amount of time, we are borrowing concepts built for finite histories and applying them to processes that vastly exceed them. The scale forces humility. It reminds us that the universe operates comfortably in regimes where human intuition fails completely. The death of a black hole is not delayed because it is protected. It is delayed because the clock that governs it ticks at a rate we can barely conceive. And that leads to a necessary comparison. If these lifetimes are so large that they escape intuition, compared to what can they meaningfully be understood? To grasp the scale of black hole lifetimes, it helps to anchor them against the age of the universe itself. Current cosmological measurements place the universe at roughly 13.8 billion years old. This number already feels immense by human standards. It exceeds recorded history by many orders of magnitude and dwarfs every biological timescale. Yet, in the context of black hole evaporation, this age is barely a beginning. When physicists compare the predicted lifetimes of black holes to the current age of the universe, the disparity is extreme. The difference is not a matter of being a few times older or younger. It spans many orders of magnitude. Even the smallest astrophysical black holes are expected to survive far beyond the present cosmic era. Supermassive black holes extend this gap to an almost absurd degree. From this perspective, the universe we inhabit today is still in its infancy relative to black hole evolution. Stars are still forming. Galaxies are still interacting. Large-scale structure remains dynamic against the timeline of black hole decay. All of this occupies an early chapter. The black holes that exist today are not approaching death. They are not even meaningfully aging. Their mass loss is so slight that it has no practical effect on their structure or influence. For all observable purposes, they are unchanged from the moment they formed. This reframes how we think about cosmic history. What we usually call the lifetime of the universe is only the lifetime of its luminous phase. It is the era where stars shine, galaxies glow, and energy gradients remain steep. Black holes are built to outlast that entire chapter. They persist into eras where familiar structures vanish. In those future epochs, the universe becomes colder, darker, and more diffuse. Yet, black holes remain, continuing their slow thermodynamic evolution. In this sense, black holes act as witnesses to multiple cosmic phases. They are present during star formation, during galactic maturity, and long after both have faded. Their existence spans transitions that redefine what the universe looks like. Comparing their lifetimes to the current age of the universe reveals a profound asymmetry. Our present moment feels ancient only because our perspective is narrow. On thermodynamic timescales, it is fleeting. The universe has barely begun the processes that will eventually govern its final state. Black holes are not relics of the past. They are features of the deep future. Understanding this forces a shift in intuition. The question of black hole death is not about something that will happen soon. It is about processes that unfold after nearly everything else has ended. And that leads to a natural extension of the comparison. If black holes persist far beyond the current age of the universe, through what stages of cosmic evolution will they continue to exist? Not all black holes share the same fate at the same pace. While every black hole follows the same underlying thermodynamic rules, their timelines diverge sharply depending on mass. Smaller black holes evaporate faster. This is not an intuitive result, but it follows directly from the physics of Hawking radiation. The lower the mass, the higher the temperature of the black hole, and the stronger the radiation it emits. As a result, small black holes lose energy more rapidly than large ones. The relationship creates a hierarchy of disappearance. The least massive black holes are the first to fade. Hypothetical primordial black holes, if they exist at very small masses, would have completed their evaporation long ago. Even stellar mass black holes will vanish far earlier than supermassive ones. Yet, early, in this context, remains misleading. These deaths do not occur within any time frame familiar to human experience. They do not take place within the era of stars, planets, or life. They unfold in a future where current cosmic structures have already dissolved. The word faster only has meaning relative to something even slower. Compared to supermassive black holes, smaller ones evaporate quickly. Compared to any human or even galactic scale, the process is still unimaginably slow. This distinction matters. It prevents the mistake of imagining dramatic endings scattered throughout cosmic history. There will be no era where black holes suddenly vanish in large numbers. Their disappearance is staggered across extreme spans of time, one by one. According to mass, they quietly exhaust their energy. This ordering introduces structure into the deep future of the universe. It suggests that black hole death is not random. It follows a sequence dictated by fundamental physics. Smaller systems reach equilibrium sooner. Larger systems persist longer. This mirrors patterns seen elsewhere in thermodynamics, where size often determines longevity. The universe does not erase its structures all at once. It dismantles them gradually, beginning with the least massive and ending with the most extreme. In this way, black holes participate in a cosmic sorting process. Their deaths are not chaotic. They are organized by scale. This realization reframes the end of black holes not as a single finale, but as a long, drawn-out progression. The universe transitions through stages where certain black holes are gone while others remain. Over immense duration, the population thins, leaving only the most massive survivors. And even those are temporary. The picture that emerges is one of ordered fading rather than collapse. Understanding this order is crucial, because it hints at how the universe approaches its final thermodynamic state. If smaller black holes disappear first, what kind of cosmic order does that impose on the far future among all known structures in the universe? Supermassive black holes are built to last the longest. Their enormous mass suppresses Hawking radiation to an extreme degree. Energy leaks away so slowly that for vast stretches of time, the process is effectively frozen. While smaller black holes gradually disappear, these giants remain. They persist through eras when stars have exhausted their fuel and no new light is produced. Long after galaxies lose their shape and stellar remnants cool into darkness, supermassive black holes continue to exist as dominant structures. In this distant future, familiar sources of energy are gone. Nuclear fusion has ceased. Stellar evolution has ended. What remains is a universe defined by emptiness. Sparse particles and isolated gravitational wells. In that environment, the largest black holes stand out not by activity, but by endurance. They no longer feed. They no longer grow. They simply remain. Their presence marks the late stages of cosmic history. These objects become the last organized concentrations of mass. Everything else has dispersed or decayed into lower energy forms. Matter is thinly spread. Motion is minimal. Change is slow. Against this background, supermassive black holes function as anchors of structure. They shape the final architecture of the universe not through interaction, but through survival. Their eventual death lies so far ahead that it resists visualization. The timescales involved are not just longer than the age of the universe. They are longer than any era defined by stars, galaxies, or even black holes smaller than themselves. Language struggles here. Words like future and end lose clarity. The universe stretches into a state where time continues. But events do not. When these black holes finally evaporate, the universe will already be unrecognizable. The concept of a galaxy will no longer apply. The idea of light will have changed meaning. Only then does the slow thermodynamic accounting reach its final phase. The death of the largest black holes is not a climax. It is a conclusion written in silence. They fade not because something acts upon them, but because nothing can resist entropy forever. Their disappearance marks the closing of the last structured chapter of the cosmos. Understanding this places supermassive black holes in a unique role. They are not merely extreme objects within the universe. They are the final witnesses to its long unfolding. And that perspective invites a deeper question. When only the largest black holes remain, what does the universe itself look like? After the era of stars comes a very different chapter in cosmic history. When stellar formation ceases and nuclear fusion no longer lights the universe, the dominant structures that remain are black holes. This transition marks what can be described as a black hole-dominated era. It is not defined by brightness or activity, but by persistence. By this stage, most sources of free energy have been exhausted. Temperature differences that once powered complex processes have largely vanished. Without free energy, there are no engines left to drive dramatic change. No new stars form. No galaxies renew themselves. The universe settles into a quieter configuration. Black holes come to dominate not because they are energetic, but because everything else has faded. They become the most massive and organized structures left in an otherwise diffuse cosmos. Yet, even in this era, black holes are not static monuments. They continue to lose energy through Hawking radiation. The process remains extremely slow, but it never stops. Each black hole, regardless of size, is still drifting toward lower energy states. The universe at this stage is defined by scarcity. Matter is thinly spread. Interactions are rare. Most particles travel vast distances without encountering anything. Against this background, black holes represent the last reservoirs of concentrated mass and structure. Their dominance is a consequence of endurance, not renewal. Importantly, this era does not bring stasis. Evolution does not halt. It simply changes character. Instead of being driven by energetic events, it is governed by gradual thermodynamic relaxation. The universe continues to evolve because entropy continues to increase, even when energy is scarce. The direction of change remains fixed. Processes slow down, but they do not reverse. Black holes slowly evaporate. Radiation spreads into ever larger volumes. Temperature differences diminish further. The cosmos approaches uniformity not through violence, but through dilution. In this sense, the black hole era is a bridge between a structured universe and a nearly featureless one. It is a long passage where the last remnants of order persist while steadily weakening. Nothing new is built. Everything that exists is slowly dismantled. Yet the story does not end here. As long as energy continues to redistribute, however weakly, the universe remains dynamic. Change becomes subtle, but it does not disappear. And this brings the central question into focus. When usable energy grows ever rarer, what is it that allows the universe to keep evolving at all? Stars are the primary engines of energy in the universe as we know it. Their light, heat, and radiation drive nearly every complex process that shapes cosmic structure. Nuclear fusion inside stars maintains temperature gradients, powers chemistry, and sustains motion on large scales. As long as stars exist, the universe remains active and expressive. When stars finally exhaust their fuel, this engine shuts down. Nuclear reactions cease. No new light is generated. Existing photons continue to travel, but they grow increasingly diluted as space expands. The universe begins to darken in a literal sense. Without fusion, matter no longer has an internal source of energy. Planets cool. Stellar remnants fade. White dwarfs and neutron stars radiate away their remaining heat over immense timescales. Eventually, even these sources fall silent. Darkness becomes the dominant condition, not as a sudden transition, but as an accumulation of absonces. With the end of stars, the universe loses more than illumination. It loses its main driver of structure formation. Gravity alone remains. But without energy input, gravity cannot build complexity. It can only rearrange what already exists. Over time, interactions become rare. Systems settle into low-energy configurations. Motion slows. Collisions decrease. The cosmos enters a phase defined by inertia rather than creativity. Temperature drops toward uniformity. Differences that once powered change diminish. The universe becomes colder, not just in temperature, but in activity. Processes that once occurred naturally become statistically improbable. What remains are slow decays and rare interactions governed by chance. In this environment, light no longer marks time. There are no cycles of day or night. No stellar lifetimes to measure duration. Time continues, but without events that give it texture. The universe becomes a place where almost nothing happens. And what does happen unfolds over spans too long to feel sequential. This is not destruction in a dramatic sense. It is depletion. The gradual removal of energy gradients that once sustained form and motion. The universe does not collapse into chaos. It relaxes into stillness. In that stillness, the question of structure becomes critical. Without stars, without fusion, without fresh energy, only the most resilient configurations can maintain coherence. Everything else diffuses or decays, which raises a final uncertainty for this stage of cosmic history. If stars are gone and no new light is born, what structures, if any, can still hold their shape? As cosmic time stretches far beyond the era of stars, familiar celestial structures begin to dissolve. Galaxies lose coherence as gravitational bindings weaken and constituent matter disperses. Stellar remnants cool and fade until they become inert particles drifting through space. Over immense duration. Planets, asteroids, and smaller bodies are stripped of defining motion. What once appeared as organized systems gradually loses identity. In this long transition, black holes remain. They persist not because they are active, but because they are resilient. Among all known structures, they are the most resistant to decay. When galaxies no longer exist in any recognizable form, black holes still occupy space as concentrated wells of mass. The universe at this stage no longer resembles the cosmos we observe today. There are no spiral arms, no glowing cores, no large-scale motion driven by energy gradients. Interactions become exceedingly rare. Matter is sparse and widely separated. Without fresh energy input, nothing initiates large transformations. The universe settles into a quiet configuration defined by absence rather than presence. In this environment, black holes dominate simply by outlasting everything else. They do not shape the universe through dramatic events. They shape it by remaining when all other structures have dissolved. Their gravity still curves space-time. But there is little left to respond to it. Motion slows toward irrelevance. Change continues, but only in subtle ways governed by long-term thermodynamic processes. The cosmos approaches a state where nothing resembles structure in the traditional sense. Silence becomes the defining feature. This is not emptiness in a literal sense, but functional emptiness. Space still contains particles and radiation, yet nothing organizes them into complex systems. The black holes that remain appear almost timeless against this backdrop. They stand as the last recognizable entities in an otherwise featureless universe. From a human perspective, this state feels final. It suggests an end to history, an end to formation, an end to meaningful evolution. Yet physics resists such conclusions. Even this quiet universe is not frozen. Processes continue at scales too slow to notice. Energy still redistributes. Entropy still increases. The apparent permanence of black holes is again a matter of timescale, not exemption. The universe has reached a calm phase. But calm is not the same as permanence. And that realization forces the next question. If the universe eventually consists only of black holes, is even this state truly stable? Even in a universe where black holes are the last remaining structures, change does not cease. Hawking radiation continues without interruption. There is no mechanism that allows a black hole to preserve its mass indefinitely. As time stretches onward, energy keeps leaking into space in the form of faint radiation. The process remains slow, but it is relentless. Each quantum of radiation carries away a minute amount of mass over immense duration. These losses accumulate. The black hole grows lighter, not suddenly, but steadily. Its gravitational influence weakens as its mass declines. The well it carves into space-time becomes shallower. For most of this process, nothing dramatic happens. The universe barely notices the change. The black hole still appears dominant simply because nothing else remains. But mathematically, the trajectory is fixed. Given enough time, the mass approaches zero. In the final stages, the evaporation accelerates. As the black hole becomes smaller, its temperature increases and radiation becomes stronger. What was once imperceptible grows more significant, though still isolated in a universe nearly empty of matter. Eventually, the black hole completes its evaporation. There is no object left behind, no dense core, no remnant with hidden mass. The structure that once dominated cosmic history dissolves entirely into radiation. Gravity loses its last major anchor. With the disappearance of the final black holes, the universe enters a new condition. There are no longer regions of extreme curvature or concentrated mass. Space becomes smoother. What remains is an ocean of low-energy particles, and photons spread thinly across an ever-expanding volume. The energy is still present, but it is diffuse. It can no longer be gathered into structures. There are no engines left to concentrate it. The universe becomes dominated by uniformity. This outcome is not sudden. It is the end point of a process that has been unfolding since the first black holes formed. The disappearance of black holes does not mark a collapse or a catastrophe. It marks the completion of thermodynamic relaxation. Everything that could lose energy has done so. Everything that could decay has decayed. What remains is not emptiness, but a state where nothing meaningful can happen. Motion exists, but it does not lead to structure. Particles move, but rarely interact. Time continues, but without milestones. The universe reaches a condition where change is no longer visible, not because time has stopped, but because there is nothing left for time to act upon. This is the quiet conclusion implied by Hawking radiation. The most extreme objects do not escape the rules. They are simply the last to obey them. And that realization brings the final uncertainty into view. When black holes themselves have vanished and only diffuse radiation remains, what exactly is left of the universe after the final black holes have evaporated? The universe enters a state unlike any earlier epoch. There are no stars left to shine. No galaxies remain to organize matter into recognizable forms. Even black holes, once the most resilient structures, are gone. What disappears with them is not only mass concentration, but the very anchors that once shaped space-time. Without these anchors, gravity loses its ability to sculpt large-scale form. It still exists as a force, but there are no significant gradients left for it to act upon. The universe no longer contains focal points. Matter and radiation are spread thinly and almost uniformly. Distinctions that once defined objects begin to dissolve. In earlier eras, structure emerged from imbalance. Differences in density, temperature, and energy created motion and form. In this final condition, those differences are nearly erased. The universe trends toward uniformity, not by destruction, but by equilibration. Everything that could spread has spread. Everything that could relax has relaxed. What remains is a cosmos without landmarks. There are no centers, no edges, no regions of special significance. Space becomes homogeneous on scales that once supported immense variety, without stars. There is no light to outline form. Without galaxies, there is no rotation or clustering to give shape. Without black holes, there are no deep wells to gather matter. The familiar hierarchy of cosmic objects collapses, not into chaos, but into sameness. In this environment, the notion of structure becomes ambiguous. Objects are no longer defined by boundaries or persistence. Particles still exist, but they rarely interact. Radiation still moves, but it carries no usable energy gradients. Everything that remains is governed by statistical distribution rather than organized dynamics. The universe has not ended. It continues to expand. Time continues to pass. Physical laws still apply. Yet the character of reality has shifted. The cosmos no longer tells a story through formation and decay. It has settled into a condition where change is minimal and directionless. Uniformity dominates. Differences become vanishingly small. This is not emptiness in the sense of nothingness. It is fullness without structure. Energy fills space, but evenly. Matter persists, but without cohesion. The universe becomes a smooth field rather than a collection of things. In such a state, language begins to fail. Words like object, system, or body lose precision. They were built to describe a universe with contrast and hierarchy. Here, contrast has faded. Hierarchy has dissolved. What remains challenges the categories we use to understand existence. And this leads to a fundamental question. When structure itself disappears and uniformity prevails, does the concept of an object still hold any meaning at all? As the universe loses its last sources of structure, temperature itself begins to lose meaning in the way we once understood it. In earlier epochs, temperature differences powered everything. Hot stars radiated into cold space. Dense regions transferred energy to sparse ones. These gradients were the engines of change over immense spans of time. Those differences fade. The overall temperature of the universe drifts downward toward extremely low values. More importantly, variations in temperature diminish. Regions that were once distinct become indistinguishable. Energy continues to exist, but it is spread evenly, without gradients. Energy can no longer flow in useful ways. There is no direction for heat to move because everything is already nearly the same. This marks the approach to thermodynamic equilibrium. It is not a sudden transition. It is the final outcome of countless small redistributions accumulating over time. Radiation stretches as space expands. Particles exchange energy through rare interactions. Each process nudges the universe closer to uniformity. Eventually, the cosmos reaches a state where temperature differences are so small that no macroscopic process can exploit them. At this point, the concept of free energy effectively disappears. There is energy present, but none of it can be harnessed to produce work. No engines can run. No structures can form. No organized motion can be sustained. Thermodynamics has reached its conclusion. This condition is often described as heat death, not because everything is hot, but because thermal equilibrium has been achieved. The universe becomes cold, but uniformly so. Nothing is warmer or cooler in any meaningful sense. Change does not stop because time stops. It stops because there is no imbalance left to drive it. Physical laws still operate, but they produce no large-scale effects. Microscopic motion continues, but it averages out. The universe becomes dynamically inert. In this state, the arrow of time loses its visible expression. Entropy has reached its maximum. There is no further direction for increase that results in observable change. The future becomes indistinguishable from the present. Events do not cease in principle, but they cease to matter. The universe enters a condition where nothing new can emerge. This is not destruction. It is completion. The long process set in motion at the beginning has finished its course. All gradients have been erased. All potential differences have been spent. What remains is a universe in balance, quiet and uniform. And this brings the final uncertainty of thermodynamics into focus. When everything has reached equilibrium and no gradients remain, what can possibly still happen? In a universe that has reached thermodynamic balance, time does not disappear, but its role changes fundamentally. Time continues to exist as a parameter, but it no longer organizes reality in a meaningful way. Earlier in cosmic history, time was marked by sequence. Events followed one another. Structures formed, evolved, and decayed. There was a clear distinction between before and after. That distinction gave time narrative power. In the final state of equilibrium, this structure collapses, without significant processes. There are no milestones to separate moments. Nothing meaningful distinguishes one interval from the next. Change becomes statistically negligible. Motion continues at microscopic levels, but it does not accumulate into transformation. From any macroscopic perspective, the universe appears frozen, even though time has not stopped. This creates a subtle but profound shift. Time is no longer a driver. It becomes a background variable without consequence. The arrow of time. Once visible through increasing entropy and irreversible processes, fades from experience. Entropy has reached its maximum. There is no further direction for it to move in a way that produces difference. The future does not look different from the present. The present does not meaningfully differ from the past. All moments blur together into a uniform continuum. In such a condition, progression, los relevance, words like later or earlier no longer correspond to observable change. They remain mathematically valid, but physically empty. Time exists, but it does not do anything. It does not create novelty. It does not erase structure, because structure is already gone. It does not guide evolution, because evolution has completed its course. The universe enters a state where duration stretches endlessly without content. This challenges the way we usually think about endings. Death, in ordinary contexts, implies transition. It implies a before and an after. It marks the passage from one state to another. But in a universe without events, such transitions lose clarity. Nothing changes enough to justify a boundary. Nothing ends in a meaningful sense. Everything simply persists in sameness. The concept of time as a story collapses. There is no beginning of the end. No unfolding conclusion. There is only continuation without distinction. This raises a final conceptual tension. If time no longer hosts events and no longer differentiates states, does the idea of death still serve any purpose at all? In the final state of the universe, death loses all dramatic meaning. There is no explosion to mark the end. No sudden collapse. No final moment that stands out from what came before. The processes that lead here are slow, quiet, and continuous. Nothing announces itself. Nothing demands attention. The universe does not end with a sound or a flash, but with a gradual fading of difference. What we often imagine as an ending is shaped by human experience. Lives end abruptly. Stars explode. Structures fail visibly. But the universe does not follow emotional scripts. Its conclusions are governed by statistics and probability, not narrative. The ultimate fate of cosmic structure is not catastrophe, but exhaustion. Energy does not disappear. It becomes unusable. Motion does not stop. It becomes irrelevant. Change does not cease. It becomes imperceptible. In this sense, death is not an event. It is a condition, a state where nothing meaningful can happen. Not because of destruction, but because all gradients have been erased. The final moments of black holes reflect this perfectly. Their disappearance is not violent. It is not witnessed. It does not transform the universe in any noticeable way. Because by the time it occurs, there is nothing left to be transformed. The universe simply settles into stillness. Silence here is not emptiness, but uniformity. Everything that remains is spread evenly. No structure rises above the background. No process creates contrast. The cosmos reaches a state where the concept of an ending becomes unnecessary. There is no boundary between before and after that matters. There is only continuation without change. This challenges deeply held intuitions. We tend to associate meaning with climax, with turning points, with irreversible moments. But the universe does not require meaning to function. It moves toward equilibrium regardless of how that equilibrium feels to observers. The final state is not tragic. It is not peaceful. It is not hopeful. It is neutral, completely indifferent to interpretation. In that neutrality, emotion has no role. There is nothing left to lose, but also nothing left to gain. The long arc of cosmic evolution resolves not into a final act, but into quiet persistence. Everything that could happen has already happened. Everything that could change has already changed. What remains is duration without direction. This perspective reframes the entire journey. If the ultimate outcome of the universe is absolute stillness, then the value of earlier eras cannot lie in their permanence. It must lie in their contrast, their activity, their fleeting complexity, which brings the final question into focus. If the end of the universe is perfect silence, how should we understand life and time as we experience them today? As the universe drifts towards silence, there are rare moments when that silence is briefly broken, not by light, but by the trembling of space-time itself. As the universe drifts towards silence, there are rare moments when that silence is briefly broken, not by light, but by the trembling of space-time itself. Among the most powerful sources of such disturbances are pairs of black holes slowly moving toward one another. These systems do not form suddenly, and they do not begin as violent encounters. Two black holes become gravitationally bound through long cosmic histories, often as remnants of massive stars born together, or as a consequence of galaxies merging over immense timescales. At the beginning of this process, the distance between them is enormous. They may orbit one another across regions larger than entire solar systems, sometimes even larger than the visible extent of their original stellar environments. In this early phase, nothing appears dramatic. There is no flash, no explosion, no visible signal that hints at what will eventually occur. The interaction unfolds across spans of time that exceed anything familiar. Gravity works quietly, shaping the geometry of space-time around each black hole. Their individual curvatures overlap, creating a shared gravitational landscape. Within this landscape, the black holes enter a slow orbital motion, not rushing inward, but circling patiently. For long durations, the system appears almost unchanged. Orbits evolve so gradually that the motion seems timeless. Energy is not lost through friction or collision, because there is no material medium between them. Instead, energy leaks away through the emission of gravitational waves, subtle distortions of space-time that propagate outward. These waves are extraordinarily weak at large distances, but their cumulative effect is real. Over millions and then billions of years, the system loses energy. The orbit contracts. The black holes move closer together. Their orbital speed increases. Still, the process remains quiet and extended. This is not yet a collision. It is a preparation. The surrounding universe may continue as if nothing is happening. Stars live and die nearby. Gas clouds evolve. Galaxies drift apart. The approaching black holes do not announce themselves. Yet within the system, something fundamental is shifting. As the distance decreases, space-time between them becomes more strongly curved. Time near the pair begins to behave differently. The geometry grows more dynamic. The balance that once defined the system slowly changes character. This long approach is essential, because without it, nothing dramatic would ever follow. The rare moments when the universe breaks its silence are built upon ages of quiet evolution. And as the separation continues to shrink, the nature of the interaction itself begins to transform, raising the question of what exactly starts to change when distance is no longer vast, but finite. As the distance between two black holes continues to decrease, their motion enters a distinct regime, often described as a slow inward spiral. At this stage, the black holes no longer follow wide, almost static orbits. Instead, they trace tightening paths around a shared center of gravity. Each revolution brings them slightly closer than the one before. This motion is smooth and continuous, governed entirely by gravity and the geometry of space-time. There is still no contact, no collision, and no sudden release of energy. The defining feature of this phase is loss. With every orbit, the system gives up a small amount of energy. The black holes do not slow down because of friction or resistance. Space around them is nearly empty. The energy is lost through gravitational radiation. Ripples in space-time that propagate outward in all directions. These waves carry energy away from the system, even though they remain undetectable at great distances. Over long periods, this gradual leakage becomes decisive. The orbital radius shrinks. The orbital speed increases. The spiral tightens. This process can last for millions of years, especially for massive black holes that begin far apart. From the outside, nothing dramatic announces this transformation. There is no visible light, no burst of particles. The universe remains dark and quiet, yet the system is irreversibly evolving. Each orbit encodes information about mass, distance, and motion into space-time itself. The spiral inward is not chaotic. It follows precise mathematical rules. The rate at which energy is lost depends on how fast the black holes move and how strongly they distort space-time. As the separation decreases, the distortion grows stronger, and the radiation becomes more intense. Still, for most of this phase, the effect remains subtle. The black holes appear patient, almost hesitant. Their future merger is inevitable, but not imminent. This long duration matters. It is during this extended spiral that the system prepares the signal that will later be detected. The early stages imprint a slow rhythm into spacetime, a gradual increase in frequency and strength that reflects the tightening orbit. The universe is being gently shaken, not struck. From a physical perspective, this phase represents a transfer. Energy that once defined orbital motion is being converted into space-time vibrations. Nothing is destroyed. Nothing vanishes. The energy simply leaves the system in a form that spreads outward and never returns. The black holes lose the ability to maintain wide separation. Gravity pulls them inward. But it is the radiation of energy that allows the spiral to continue. Without this loss, the orbit would remain stable forever. The spiral in phase is therefore silent but decisive. It is the reason a collision can ever occur. And as the inward motion accelerates, a fundamental question comes into focus. If energy is steadily disappearing from the orbit, where exactly has that energy gone? After the long spiral inward, the system reaches a critical threshold. The distance between the two black holes becomes comparable to the size of their event horizons. At this point, the character of the interaction changes abruptly. The slow and patient evolution gives way to a brief and extreme phase known as the merger. This moment does not resemble a collision in any ordinary sense. There is no solid surface to crash into another. No matter slams together. No fragments are thrown outward. Black holes are not objects made of material that can collide. What approaches instead are two regions of space-time so intensely curved that their boundaries begin to overlap. As the event horizons draw close, the geometry of space-time becomes violently dynamic. The equations of general relativity no longer describe a gentle exchange of energy, but a rapid restructuring of curvature itself. The two horizons distort, stretch, and merge into a single enclosing boundary. For a fleeting instant, space-time behaves in a way that defies simple visualization. This is not motion through space. It is space itself, changing shape. The merger phase is extraordinarily short compared to the spiral that preceded it. What took millions or billions of years to prepare unfolds in a fraction of a second. During this brief interval, the system releases the most intense burst of gravitational waves it will ever produce. These waves encode the final masses, spins, and orientations of the original black holes. The universe is shaken not by impact, but by reconfiguration. Two separate curvatures become one. Two histories collapse into a single future. From the outside, nothing is seen. No light escapes. No debris signals the event. Yet space-time across vast distances responds. Distances stretch and compress as the gravitational wave passes. The merger is the loudest moment in gravitational terms. Even though it is completely silent to the eye, what emerges from this process is not chaos, but unity. A single black hole forms, larger and more massive than either of its predecessors. Its event horizon encloses what was once two separate regions. The violent dynamics subside almost immediately. The system has completed its transformation. The merger does not last. It is a transition, not a state. Its importance lies not in duration, but in consequence. In that instant, the universe performs a rare act of rewriting. The geometry of space-time rearranges itself into a simpler configuration. What was once a binary becomes a singular entity. Understanding this phase requires abandoning everyday intuition. There is no crash, no explosion, no material destruction. There is only geometry evolving at extreme speed. And this leads to the essential realization that defines the merger itself. If no material objects ever collide, then what is truly happening in this moment is the rapid and irreversible reorganization of space-time, which raises the deeper question of what is actually taking place when two black holes become one without any physical collision at all. After the merger completes, the newly formed black hole does not immediately settle into a calm, final state. The violent reconfiguration of space-time leaves it distorted. Its geometry is not yet the smooth, symmetric shape predicted for an isolated black hole. Instead, space-time around it continues to oscillate. This phase is known as the ring-down, a period where the black hole sheds its remaining irregularities. The process can be compared to a struck bell, not because the black hole makes sound, but because space-time itself vibrates and then gradually quiets. The oscillations are not random. They follow precise patterns determined by the fundamental properties of the black hole. Mass and spin dictate how space-time rings and how quickly those vibrations fade. Each oscillation carries energy away in the form of gravitational waves, allowing the black hole to relax into a stable configuration. Unlike the merger, which is brief and extreme, the ring-down unfolds as a smooth decay. The amplitude of the vibrations decreases over time. The frequency settles into characteristic modes. These modes are universal. Any black hole with the same mass and spin will ring in the same way. This universality is what makes the ring-down so important. It acts as a direct probe of black hole physics. There is no surrounding matter involved, no complex environment. What is observed is the behavior of space-time itself responding to extreme curvature. As the oscillations fade, the black hole approaches a state described by only a few parameters. All details of the chaotic merger are erased. The system forgets its past. This loss of information is not mysterious. It is a consequence of how gravity organizes itself. The ring-down marks the final step in that organization. For detectors far away, this phase appears as a clean signal, a rapidly damped waveform that carries a precise imprint of the black hole's properties. By analyzing these oscillations, physicists can infer the mass and spin of the final object with remarkable accuracy. The signal does not depend on assumptions about matter or light. It is geometry speaking directly. The universe briefly reveals how space-time behaves when pushed far from equilibrium and then allowed to relax. The ring down is therefore not an afterthought. It is a confirmation. It confirms that the object formed is indeed a black hole, as described by general relativity. It confirms that space-time settles into predictable forms, and it confirms that even the most violent events leave behind order. As the vibrations diminish and silence returns, the system completes its transformation. What remains is a single, stable black hole, indistinguishable from any other with the same fundamental parameters. The echoes fade, but they leave behind a record. Those fading oscillations encode information that traveled across the universe, waiting to be read, raising the essential question of what exactly those space-time vibrations tell us about the black hole that produced them. Gravitational waves are not objects traveling through space. They are ripples of space-time itself. When massive objects accelerate, they disturb the geometry around them, creating distortions that propagate outward. This effect is extraordinarily weak under ordinary conditions. Everyday motions, even planetary or stellar ones, produce gravitational waves so small they are effectively undetectable. To generate waves strong enough to matter, mass must move in extreme ways. It must accelerate violently and asymmetrically. Black hole mergers provide exactly these conditions. As two black holes spiral inward, their enormous masses move faster and faster through curved space-time. The acceleration becomes intense. The geometry responds by producing waves that carry energy away from the system. These waves do not consist of particles or radiation in the usual sense. They are changes in distance itself. Space stretches and compresses rhythmically as the wave passes. No light is emitted. No matter is ejected. The signal contains no photons and no material debris. What travels across the universe is pure geometry. Each wave encodes information about how space-time was distorted at the source. The masses involved, their motion, and their final configuration are written into the pattern of stretching and squeezing. This makes gravitational waves fundamentally different from all other astronomical messengers. Light tells us about energetic processes involving charged particles. Neutrinos reveal nuclear reactions. Gravitational waves reveal motion of mass itself, independent of composition. They do not care whether the source is luminous or dark. A black hole merger is therefore an ideal generator. Nothing blocks the signal. There is no absorption. The waves travel essentially unchanged from their origin to the observer. Over billions of years, they spread out and weaken, but they retain their form. By the time they reach Earth, their effect is tiny. Distances change by less than the width of a proton over kilometers, yet the pattern remains intact. Detecting such a signal requires a completely different approach to observation. One does not look for light. One measures distance itself. The universe briefly imprints its most violent motions into the fabric of space-time and sends that imprint outward. Understanding how these waves are generated clarifies what they are not. They are not explosions. They are not bursts of energy in the usual sense. They are the universe flexing and relaxing as massive objects rearrange space-time. This perspective reframes the challenge entirely. If gravitational waves carry no light and no matter, only geometry, then their discovery depends on our ability to sense minute changes in distance. raising the question of how such signals can possibly be detected at all. One of the most striking aspects of black hole mergers is their darkness. In most cases, these events produce no light at all. There are no flashes in visible wavelengths, no bursts of X-rays, and no electromagnetic afterglow to point telescopes toward the source. This is not because the event is weak, but because it involves almost no matter. When two black holes merge in isolation, there is nothing present to heat up, ionize, or radiate. Light is generated by charged particles accelerating and interacting. In a black hole merger, there are no such particles involved. The event horizon hides everything inside. And outside it, space-time alone is doing the work. As a result, the most violent rearrangements of gravity in the universe can occur in complete darkness. For traditional astronomy, this presents a profound challenge. Telescopes are designed to collect photons. They rely on light to locate objects, measure distances, and infer physical processes. When an event emits no light, it leaves no mark on the electromagnetic sky. From the perspective of conventional observation, nothing seems to happen. Entire cosmic catastrophes can unfold without a single photon betraying their existence. This limitation once defined the boundary of what could be known. Black hole mergers were predicted by theory, but they remained invisible. There was no way to confirm them directly using light. Yet this absence of electromagnetic signals is not a failure of nature. It is a clue. It tells us that light is not the only messenger the universe uses. When photons fall silent, space-time itself carries the information. Gravitational waves become the sole signal. They do not require matter. They do not interact with dust or gas. They pass freely through the universe, unaffected by obstacles that block light. In this way, darkness becomes an advantage. The lack of light forces a shift in method. Instead of looking outward with telescopes, we listen inward with instruments sensitive to distance. Astronomy expands beyond vision. It becomes geometry. The universe reveals its most hidden events not through brightness, but through motion encoded into space-time. This transition marks a fundamental change in how observation works. Knowledge no longer depends on illumination. It depends on measurement of subtle distortions. The silence of light does not mean absence of information. It means information has changed form. And that realization leads to the central pivot of modern gravitational astronomy. When light no longer helps us see, we are compelled to ask what it is that we now rely on instead. The collision of two black holes may sound apocalyptic, but in physical reality, it is not a cosmic disaster. There is no explosion in the conventional sense. No shockwave tears through surrounding space. No blast of energy sterilizes nearby regions. This is because the energy involved behaves very differently from what intuition suggests. During a black hole merger, energy is released almost entirely as gravitational waves. These waves do not heat matter, ignite radiation, or disrupt atomic structures. They stretch and compress space-time itself. And they do so with extreme subtlety at large distances. By the time gravitational waves reach Earth, their effect is extraordinarily small. Distances change by a fraction smaller than subatomic scales. Nothing shakes. Nothing breaks. Life continues unaffected. Even within the host galaxy of the merger, the influence is limited. Stars do not explode. Orbits remain stable. The event does not radiate outward as destruction. Instead, it radiates information. The merger does not damage the surrounding universe because space-time is remarkably elastic. It can flex, transmit the disturbance, and then return to its prior state without permanent harm. The energy carried by gravitational waves spreads out over immense volumes. As it propagates, it becomes diluted. What begins as an extreme event at the source becomes a faint whisper by the time it reaches distant regions. This is why such mergers pose no threat on human or planetary scales. Their danger exists only in extreme proximity. Only within distances comparable to the size of the merging system itself would the distortions be strong enough to cause damage. Such regions are vanishingly small compared to cosmic scales. The universe is vast, and these events are rare. They do not overlap. They do not cascade. There is no chain reaction. Each merger is isolated in space and time. Understanding this removes a common misconception. Violent does not mean destructive everywhere. Powerful does not mean catastrophic at a distance. The significance of black hole collisions lies not in what they destroy, but in what they reveal. They allow us to observe gravity operating at its most extreme. They provide a direct test of general relativity. They show how space-time behaves when pushed far from equilibrium. These events are laboratories, not threats. They reshape knowledge, not galaxies. The universe is not torn apart by them. It briefly speaks through them. And this distinction is crucial. Because if these collisions do not signal destruction, then their true importance must lie elsewhere. In the meaning they carry, rather than the damage they cause, gravitational waves do not travel through space-time in the way sound travels through air or waves move across water. They are space-time in motion. As a gravitational wave passes, distances themselves change. Space stretches in one direction while compressing in another, then reverses, oscillating as the wave moves on. Nothing material is pushed. No object is carried along. The effect acts directly on geometry. 2 points that were once a fixed distance apart become slightly closer or farther away, not because they moved, but because the space between them changed. This distortion is unimaginably small. Even the strongest gravitational waves reaching Earth alter distances by less than the width of a proton across kilometers of space. To human senses, such changes are meaningless. No ruler would notice. No structure would deform in any visible way. Yet the effect is real. Space-time itself behaves like an elastic medium, capable of vibrating when disturbed. This idea marks a profound shift in how reality is understood. Space is no longer a passive stage where events unfold. It is an active participant. It responds to motion, carries energy, and oscillates. The passing of a gravitational wave briefly turns the universe into a dynamic fabric. Length is no longer fixed. Geometry becomes time-dependent. These oscillations do not destroy structure because they are extraordinarily gentle at large distances. They pass through planets, stars, and even human bodies without resistance. Everything is stretched and compressed together, leaving no internal stress behind. The universe flexes as a whole. This is why gravitational waves can travel unimpeded across billions of light years. Nothing blocks them. Nothing absorbs them. They do not fade because of interaction, only because they spread out. Understanding this requires abandoning familiar analogies. There is no surface waving and no medium flowing. What oscillates is the metric that defines distance itself. Measuring such an effect demands precision beyond ordinary experience. It requires treating space as something that can be compared with itself at different moments. The challenge is not seeing motion. but detecting the absence of perfect rigidity. When space-time vibrates, it leaves behind no permanent trace, only a fleeting pattern of stretching and squeezing. Capturing that pattern is equivalent to measuring reality as it briefly departs from stillness. And this leads naturally to the central challenge. If the change is smaller than anything we can touch or see, how can it possibly be measured? To detect gravitational waves, astronomy required instruments unlike any that came before. Telescopes were no longer enough, because there was no light to collect. This need led to the creation of observatories such as LIGO and Virgo, facilities designed not to look outward, but to measure space itself. Their core technology is the laser interferometer, an instrument capable of comparing distances with extraordinary precision. Each observatory consists of long perpendicular arms, stretching for kilometers. A laser beam is split and sent down both arms, reflected back by mirrors, and then recombined. Under normal conditions, the distances are equal, and the light waves cancel in a predictable pattern. When a gravitational wave passes through Earth, space-time stretches in one direction and compresses in the other. The arms change length by an almost inconceivably small amount. This change alters the interference pattern of the returning light. Nothing touches the mirrors. Nothing pushes them directly. The measurement captures the change in space between them. The sensitivity required is extreme. These instruments can detect variations in distance smaller than a proton across kilometers. Achieving this demands isolation from seismic noise, thermal fluctuations, and even quantum effects. The observatories operate at the edge of what is physically measurable. In this sense, they function less like eyes and more like ears. They do not form images. They register vibrations. They listen to space-time as it oscillates. Importantly, these detectors do not need light from the source. They do not care whether black holes are in the sky. They respond only to the passing wave. This makes them fundamentally different from traditional observatories. Events that are completely dark become observable. Collisions, hidden from every telescope, leave a clear signature in these instruments. When multiple detectors register the same signal at slightly different times, the direction and distance of the source can be inferred. A new map of the universe emerges, one built from geometry rather than brightness. The first detections confirmed predictions made a century earlier, but they also opened a door to phenomena that had never been observed directly. With these tools, the universe reveals motions that were previously silent. The most extreme rearrangements of mass announce themselves not through light, but through tiny changes in length measured on Earth. This shift transforms what astronomy can access. When a new kind of instrument becomes available, entire classes of events move from theoretical possibility to observable reality, which leads naturally to the question of what becomes visible once we gain the ability to listen to the universe instead of only looking at it. In September 2015, something unprecedented occurred. Instruments on Earth registered a signal that did not arrive as light, particles, or radiation of any familiar kind. What was detected was a fleeting change in distance, a rhythmic stretching and squeezing of space itself. This marked the first direct observation of gravitational waves. It was not an image captured on a detector. It was not a point of light on a sky map. It was a time series, a pattern unfolding moment by moment, recorded as space-time vibrated and then fell quiet again. For the first time, the universe was not observed by looking at it, but by listening to it. Facilities such as LIGO registered the signal independently at different locations. confirming that it was not noise or local disturbance. The pattern matched with extraordinary precision the predictions for a black hole merger made decades earlier. Yet the experience of detection was fundamentally different from anything astronomy had known. There was no photograph to examine, no structure to visualize. Understanding the event required translating oscillations in distance into physical meaning. The signal rose in frequency and amplitude, then abruptly faded. This change in rhythm told a story of motion, acceleration, merger, and settling. Time itself became the primary observable. This shift had deep implications. Traditional astronomy builds knowledge from spatial information. Where something is, how bright it appears, what shape it takes. Gravitational wave astronomy begins instead with change. How quickly distances vary, how patterns evolve. The universe reveals itself not as a static picture, but as a sequence of events. Listening emphasizes process over appearance. It captures dynamics rather than form. With this new sense, phenomena that are invisible become accessible. Entire classes of events that produce no light suddenly enter observation. The cosmos expands not in size, but in expressiveness. Human perception extends beyond vision into geometry. This does not replace seeing. It complements it. Light and space-time together provide a richer account of reality. The first detection did more than confirm a theory. It demonstrated that the universe has a voice. That voice is subtle, encoded in minute distortions, but it carries information no image could ever provide. From that moment onward, astronomy was no longer limited to what shines. It could attend to what moves mass and reshapes geometry. This transformation forces a rethinking of observation itself. Seeing tells us where things are. Hearing tells us how they change. And with that realization, a deeper question emerges about how listening to the universe differs fundamentally from watching it unfold. When gravitational waves are described as sounds, it is important to understand what that description really means. These waves are not sound waves traveling through a medium. Space does not carry pressure variations the way air does. There is no vibration of particles that could be heard by an ear. Gravitational waves are changes in space-time itself, far removed from anything the human sensory system evolved to perceive. The sounds often associated with black hole mergers are therefore not natural phenomena. They are translations. Scientists take the measured signal, which is a time series of distance changes, and map it into the range of frequencies audible to humans. This process is called sonification. It does not create new information. It reshapes existing data into a form that intuition can grasp. The rising pitch corresponds to increasing frequency of space-time oscillations. The sudden cutoff marks the merger and ringdown. What we hear is not the universe making noise. It is the universe being interpreted. This distinction matters. Sound is a metaphor, not a physical property of the event. The purpose of sonification is cognitive, not descriptive. Human brains are exceptionally good at recognizing patterns in sound. Subtle changes in rhythm and tone are easier to notice when heard than when seen as graphs. By listening, researchers and the public alike can intuitively follow the evolution of a gravitational wave signal. Yet this usefulness carries risk. When representations become vivid, they can be mistaken for reality. The danger lies in forgetting that the sound is an overlay, not the phenomenon itself. The black hole merger did not roar. It did not ring audibly across space. What occurred was a precise mathematical variation in geometry. Sound is simply a bridge between abstraction and understanding. Used carefully, It deepens insight, used carelessly. It invites confusion. This balance reflects a broader challenge in science communication. Data often require transformation to become meaningful. Every transformation involves choice. Scaling, filtering, and mapping all emphasize some features and suppress others. The interpretation is guided by human limits. Recognizing this keeps the boundary clear. The sound is a tool. The wave is the reality. Maintaining that distinction allows us to use intuition without letting it mislead. And as gravitational astronomy relies increasingly on indirect signals and complex representations, the question becomes unavoidable. When data must be interpreted to be understood, where exactly does the line between insight and misunderstanding begin to blur? Gravitational waves introduce a fundamentally new kind of data into astronomy. Unlike light, this information does not pass through matter in a way that alters or obscures it. There is no dust to scatter it, no gas to absorb it, no plasma to distort it. The signal arrives almost exactly as it was emitted, carrying a direct imprint of the motion that produced it. This makes gravitational wave data uniquely clean. What is measured is not an indirect consequence of physical processes, but the processes themselves encoded into space-time. From these signals, properties that were once inferred only indirectly can now be measured with precision. The masses of black holes emerge clearly from the waveform. Their spins leave distinct signatures in how the signal evolves. Even the orientation of the system becomes accessible. This level of detail was previously unattainable for objects that emit no light. Gravitational waves bypass the need for electromagnetic interpretation entirely. They provide a direct channel to phenomena that were once hidden behind darkness. This new data stream expands the range of tests available to fundamental physics. Predictions of general relativity that were once purely theoretical can now be confronted with observation. Subtle effects that only appear in extreme gravitational fields become measurable. Each detection serves as a probe of gravity under conditions impossible to recreate on Earth. Importantly, this data is independent. It does not rely on the same assumptions used to interpret light. It does not depend on models of stellar atmospheres, radiation mechanisms, or plasma behavior. As a result, it offers a powerful cross-check. When gravitational wave measurements agree with electromagnetic observations, confidence increases. When they differ, new physics may be indicated. This independence is transformative. It allows long-standing assumptions to be tested rather than taken for granted. Concepts such as how black holes grow, how binaries form, and how gravity behaves at high energies must now satisfy two separate observational regimes. The universe is no longer telling a single story through light alone. It is providing parallel accounts through geometry. Integrating these perspectives reshapes understanding. It forces theory to become more robust. It narrows the space where speculation can hide. With each new detection, the framework of gravitational physics is refined. Old models are strengthened, revised, or discarded. This process is not about replacing what was known, but about deepening it. The arrival of gravitational wave data marks a transition from inference to measurement. And with that transition comes an unavoidable challenge. When entirely new forms of data enter science, the assumptions built in the era before them cannot remain untouched, raising the question of how those older ideas must now be re-examined. From the moment gravitational waves were first detected, they became one of the most stringent tests of general relativity ever performed. The theory, developed by Albert Einstein more than a century earlier, had predicted not only the existence of these waves, but their precise behavior, the shape of the waveform, its frequency, evolution, its amplitude, and its decay all followed mathematical expressions derived long before any detector existed. When real data arrived, it matched those predictions with remarkable accuracy. This agreement was not limited to gentle regimes. Black hole mergers probe gravity at its most extreme. Space-time is strongly curved. Velocities approach the speed of light. Accelerations are immense. These are precisely the conditions where deviations from theory might be expected to appear. Yet within current measurement precision, no large discrepancies have been found. The signals align with relativistic models across in spiral, merger, and ring down. Each phase reinforces confidence that the equations describe reality even under extraordinary stress. This success carries deep implications. It means that general relativity remains valid far beyond the environments where it was originally tested. It survives not only in weak gravitational fields like the solar system, but also in the violent rearrangements of spacetime produced by colliding black holes. However, this confirmation does not close the case. Agreement within uncertainty does not equal final proof. Every test has limits set by detector sensitivity and data volume. Small deviations could still exist below the threshold of detection. New physics might hide in subtle effects not yet measurable. The role of gravitational wave astronomy is therefore not to declare victory, but to expand the range of scrutiny. Each new detection pushes theory into regimes previously inaccessible. As instruments improve, precision increases. What is invisible today may become detectable tomorrow. This ongoing process keeps relativity under continuous examination. The theory has passed its hardest tests so far. But science does not stop testing a framework simply because it works. Instead, success sharpens the next question. If general relativity continues to hold under these extreme conditions, then the frontier must move further outward, towards situations even more extreme or more subtle, prompting us to ask where the next meaningful challenge to the theory should be sought. For most of its history, astronomy has depended almost entirely on light. Knowledge of the universe was built from photons arriving at detectors, carrying information about distant objects. What could not emit or reflect light remained largely inaccessible. Gravitational wave astronomy changes this foundation. It demonstrates that observation does not require illumination. Events can be studied even when no electromagnetic signal is present. This shift dramatically expands what counts as observable. Black hole mergers, once completely hidden, become accessible. Entire populations of dark systems enter scientific awareness. The universe no longer divides cleanly into visible and invisible realms. Instead, it reveals multiple channels through which information flows. Importantly, this new approach does not replace traditional methods. Telescopes remain essential. Light still provides unparalleled detail about composition, temperature, and structure. Gravitational waves add a complementary layer. They reveal motion, mass, and dynamics that light cannot. Together, these perspectives create a fuller picture. One shows appearance, the other shows process. The integration of both reshapes how cosmic events are understood. A galaxy collision, for example, can now be studied through starlight and through space-time vibrations. Each tells a different part of the story. This combined approach reduces ambiguity. It cross-checks interpretations. It exposes biases inherent in relying on a single messenger. As a result, the observable universe effectively grows larger, not in physical size, but in informational depth. Regions once silent become expressive. Phenomena once theoretical become measurable. Astronomy becomes less about where to look and more about how to listen and compare. This transition marks a maturation of the field. Observation becomes multidimensional. The universe is no longer a picture to be examined, but a system to be interrogated through diverse signals. With this broader toolkit, understanding shifts from partial glimpses to integrated views, and as methods multiply, the image of the cosmos itself changes, prompting reflection on how the arrival of observation without light alters the way the universe is perceived as a whole. The detection of gravitational waves marks the birth of a new branch of astronomy. For the first time, the universe is observed not only through what it emits, but through how it moves. This shift does not abandon traditional methods. Instead, it expands them. Gravitational wave astronomy emerges alongside electromagnetic astronomy, forming a combined approach that captures reality from multiple angles. Light reveals composition, temperature, and structure. Gravitational waves reveal mass, motion, and geometry. Together, they transform isolated observations into coherent narratives. A cosmic event is no longer a single signal. It becomes a multi-layered phenomenon, described by complementary messengers. This integration deepens understanding. It reduces ambiguity. It allows events to be cross-examined rather than inferred from a single source. As this new field develops, questions multiply. How many black hole mergers occur beyond current detection limits? What unknown classes of objects produce gravitational waves? How does gravity behave in regimes not yet explored? Each detection answers one question and raises several more. The universe becomes richer, not because it has changed, but because our ability to interrogate it has expanded. Importantly, this is only the beginning. Current detectors capture only the strongest signals. Future instruments will listen with greater sensitivity and across broader ranges. Frequencies now inaccessible will become audible. Subtler events will emerge from the background. Entire epochs of cosmic history may reveal themselves through space-time vibrations. What was once silent will acquire voice. This new astronomy does not promise easy conclusions. It promises complexity. It demands patience. It requires new ways of thinking about observation and evidence. But it also restores a sense of exploration. The cosmos is no longer a static image to be catalogued. It is a dynamic system to be experienced through multiple senses. Humanity has learned to look at the stars. Now it has learned to listen to the universe. And with that realization, the horizon of inquiry widens. If we have only just begun to hear the universe speak, how many stories remain unheard, waiting in the fabric of space-time itself? Learning to observe black holes without light has expanded our understanding. It also invites a quieter question: what, if anything, should we ever do with that knowledge? Throughout history, humanity has been defined by its search for energy. Each stage of civilization has been shaped by access to denser and more controllable sources. From fire to fossil fuels to nuclear reactions, This pattern creates a natural temptation. When confronted with the most extreme concentrations of energy known in the universe, the mind begins to wonder whether such power could ever be used. Black holes appear, at first glance, to represent the ultimate reservoir. Their mass density is unmatched. Their gravitational fields dwarf all familiar systems. In theoretical terms, they sit at the edge of what physics allows. Yet the idea of harvesting energy from a black hole does not arise from engineering ambition. It arises from thought experiments. No experiment has ever attempted such a thing. No technology exists that could approach it. The concept is born entirely within theoretical physics, where equations are allowed to ask questions that reality may never permit. These ideas are not proposals. They are probes. They test how physical laws behave at extremes. They explore what is allowed in principle, not what is achievable in practice. When physicists discuss extracting energy from black holes, they are not drawing blueprints. They are examining the boundaries of conservation laws, thermodynamics, and relativity. The question is framed carefully. Not how to build a machine, but whether the laws of nature even allow energy to be removed in a meaningful way. This distinction matters. Without it, speculation turns into illusion. The fascination with black holes as energy sources reflects a deeper human habit. We often look at power before considering purpose. The sheer scale of energy involved overwhelms intuition. Numbers grow so large that they detach from context. But physics does not care about desire. It cares about consistency. Any idea of extraction must obey strict constraints. Energy cannot be created. Entropy must increase. Causality must remain intact. Black holes, despite their mystery, are not loopholes in these rules. They are governed by them. In fact, they obey thermodynamic principles more rigorously than almost any other system we know. This realization reframes the discussion. The question is no longer whether black holes contain vast energy. That is obvious. The question becomes whether that energy is accessible in any physically meaningful sense. Theoretical work suggests limited mechanisms where energy could be transferred, but always at enormous cost and under conditions that verge on the unattainable. These ideas serve a conceptual role. They force physicists to confront the implications of their equations. They clarify what is forbidden and what is merely difficult. Importantly, they slow the conversation down. Before any solution is imagined, the problem itself must be understood. The act of asking precedes the act of doing. In this way, the idea of harvesting black hole energy is less about the future and more about humility. It reminds us that knowledge does not automatically imply action. Some understanding exists to define limits, not to overcome them. And so the discussion begins where it should. Not with plans or promises, but with a careful inquiry into foundations, leading inevitably to the deeper question of what physical principles such an idea would have to rest upon if it were ever more than a thought experiment. Among the earliest serious ideas about extracting energy from a black hole is a concept known as the Penrose process. It does not rely on fantasy technology or violations of physics. It emerges directly from the mathematics of rotating black holes. When a black hole spins, it drags space-time around with it. This effect becomes extreme near the event horizon, creating a region called the ergosphere. Inside this zone, space-time itself is forced to rotate. Nothing can remain stationary relative to the distant universe. Motion becomes compulsory. The key insight of the Penrose process is that within this region, energy can take on unusual properties. Under very specific conditions, a particle entering the ergosphere can split into two. One fragment falls into the black hole on a trajectory that carries negative energy relative to infinity. The other escapes outward with more energy than the original particle possessed. The extra energy is not created. It is taken from the black hole's rotation. In principle, this means that a spinning black hole can be slowed down by giving up some of its rotational energy. From a mathematical standpoint, the process is sound. It respects conservation laws. It does not break causality. It is allowed by general relativity. This is why it has endured as a legitimate idea within theoretical physics for decades. Yet legitimacy on paper does not imply feasibility in reality. The conditions required are extraordinarily precise. The particle trajectories must be tuned with extreme accuracy. The interaction must occur deep within a region where tidal forces are immense. Any practical apparatus would have to survive gravitational gradients capable of shredding ordinary matter. Even more critically, the efficiency of the process is limited. Only a fraction of the black hole's rotational energy can be extracted before the black hole becomes non-rotating. The remaining mass remains inaccessible. Scaling this up to something resembling an energy source reveals deeper obstacles. The environment near a rotating black hole is violently unstable. Radiation, plasma, and magnetic fields dominate. Maintaining controlled interactions in such a setting is beyond any foreseeable technology. The process also requires delivering matter into precisely defined orbits and recovering the escaping fragments without catastrophic loss. Each step introduces engineering challenges, orders of magnitude beyond current capabilities. As a result, the Penrose process occupies a narrow space in scientific thought. It demonstrates that black holes are not absolute energy sinks. They possess extractable properties under idealized conditions. But it also illustrates how permissibility in theory does not translate into practicality. The gap between what equations allow and what reality tolerates becomes starkly visible. The value of the Penrose process is therefore not as a blueprint for future power generation. Its value lies in what it teaches about rotating spacetime, energy definitions, and the subtle ways gravity reshapes classical intuition. It clarifies that even in the most extreme environments, physics remains internally consistent. At the same time, it reminds us that consistency does not imply accessibility. The universe may permit certain exchanges, but at costs so high that they remain effectively unreachable. This realization reframes the original curiosity. If a process can exist cleanly in mathematics, yet be blocked by every practical constraint of the physical world, then the true barrier is not whether extraction is allowed in principle, but why the structure of reality places such overwhelming obstacles in the way when theory alone suggests possibility. When the idea of extracting energy from black holes is discussed, one number often dominates attention: theoretical efficiency. On paper, the efficiency of certain black hole-related processes appears extraordinary. In idealized calculations, the fraction of mass energy that could be converted into usable energy can exceed that of nuclear fusion by a wide margin. Fusion, which powers stars, converts less than 1% of mass into energy. By contrast, rotating black holes contain far larger, accessible energy reservoirs in principle. This comparison is seductive. It creates the impression that black holes represent a vastly superior energy source waiting to be tapped. Yet theoretical efficiency exists in a carefully constructed world. It assumes perfect conditions, precise control, and ideal trajectories. It assumes that losses can be minimized and that interactions occur exactly as equations prescribe. Reality is not obliged to cooperate. In any physical system, efficiency is eroded by friction, instability, and uncertainty. The more extreme the environment, the harsher these effects become. Near a black hole, nothing is gentle. Tidal forces vary violently over short distances. Radiation fields are intense. Plasma flows are turbulent. Any deviation from the idealized path compounds rapidly. A process that is efficient in theory becomes wasteful in practice. Even small imperfections magnify into catastrophic losses. This gap between theoretical maximum and practical outcome is not unique to black holes. It appears in all energy technologies. Engines never reach Carnot efficiency. Reactors never achieve perfect conversion. But with black holes, the scale of the gap becomes overwhelming. The same factors that grant high theoretical efficiency also make control nearly impossible. The conditions required to approach the maximum are precisely those that eliminate margin for error. There is no stable operating range. There is only success under perfection or failure through destruction. Furthermore, efficiency alone does not define usefulness. An energy source must be accessible, controllable, and repeatable. It must deliver energy at rates and locations compatible with infrastructure. Black hole processes fail these criteria immediately. Even if a single extraction were possible, repeating it safely and consistently would remain beyond reach. Transporting energy away from such an environment introduces additional losses. The energy must be captured, converted, and transmitted without destabilizing the system that produced it. Each step erodes the theoretical advantage. What remains is a sobering realization. High efficiency does not automatically translate into viable technology. In many cases, the most efficient processes are precisely those that are least usable. Nature allows them, but only at scales and conditions that resist intervention. This reframes the excitement around theoretical numbers. Efficiency becomes a property of equations, not of engineering. It marks what is allowed, not what is achievable. The distance between possibility and implementation becomes the central issue. Black holes highlight this distance more clearly than almost any other system. They remind us that physics permits far more than civilization can harness. Understanding this distinction is essential. Without it, speculation drifts into fantasy. With it, the discussion regains discipline. The question is no longer how impressive the efficiency appears, but whether efficiency alone is ever sufficient to transform an idea into technology, or whether the true barrier lies in the unforgiving gap between what mathematics permits and what reality allows to be built. The idea of a Dyson sphere was originally conceived for stars. It imagines a civilization surrounding a star with structures to capture a significant fraction of its emitted energy. When this concept is extended to black holes, the picture changes dramatically. A black hole itself emits almost no light. There is nothing to surround at the event horizon that could be harvested directly. Any realistic proposal, therefore, shifts focus away from the black hole itself and toward its environment. The energy of interest comes from accretion disks and relativistic jets. As matter falls toward a black hole, it heats to extreme temperatures, releasing vast amounts of radiation before crossing the horizon. In some systems, powerful jets carry energy outward along the rotational axis. These regions, not the event horizon, are where usable energy exists. A hypothetical Dyson-like structure around a black hole would therefore not be a sphere at all. It would be a complex arrangement positioned to intercept radiation and particle flows from the disk or jets. Such a structure would need to withstand intense heat, radiation, and gravitational gradients. Stability would require precision far beyond ordinary engineering. Orbits would have to be maintained with extraordinary accuracy to avoid decay or destruction. The environment near an active black hole is chaotic. Magnetic fields fluctuate. Plasma flows are turbulent. High-energy particles bombard any surface continuously. Designing materials that could survive for meaningful durations under such conditions exceeds all known capabilities. Even at a conceptual level, the scale of construction is staggering. The mass required to build a collector large enough to capture a useful fraction of the energy would itself rival planetary or stellar masses. Coordinating such a structure without triggering instabilities in the surrounding system introduces further complications. Moreover, black holes are not steady energy sources in the way stars are. Accretion rates vary. Jets can turn on and off. Energy output fluctuates across timescales. A collector designed for peak output might sit idle for long periods. In contrast, stars provide a relatively stable and predictable flow of energy over billions of years. This comparison matters. When evaluating energy sources, reliability is as important as magnitude. Black holes may offer extreme power under certain conditions, but they lack consistency. The very processes that make them energetic also make them volatile. The Dyson sphere concept highlights this difference. Around a star, it represents an extrapolation of known engineering challenges. Around a black hole, it represents a leap into environments fundamentally hostile to structure. The thought experiment is valuable not because it points toward construction, but because it sharpens perspective. It forces a comparison between theoretical abundance and practical usability. In doing so, it reframes the question of superiority. A source can be more energetic, yet less useful. Power without control is not advantage. As the idea unfolds, it becomes clear that whether a black hole is a better energy source than a star depends not on raw output, but on the balance between accessibility, stability, and survivability, which leads naturally to the question of whether black holes truly offer an advantage over stars when considered as potential sources of usable energy. When black holes are discussed as potential energy sources, the comparison with stars becomes unavoidable. Stars are the original power plants of the universe. They shine steadily for billions of years, converting mass into energy through nuclear fusion in a predictable and well-understood way. Their behavior is comparatively gentle. Distances are manageable. Radiation levels, while intense, fall within ranges that can be mitigated. From an engineering perspective, stars are approachable. Their energy arrives freely, spreads outward, and requires no intervention to be released. One only needs to intercept it. Black holes, by contrast, are fundamentally indirect. They do not generate energy on their own. Any usable output comes from matter falling toward them or from extreme relativistic processes tied to rotation. This energy is episodic rather than continuous. It depends on supply, alignment, and instability. Accessing it requires operating in regions where gravity is violent and margins for error vanish. In practical terms, stars offer reliability. Their luminosity changes slowly. Their output can be forecast over astronomical timescales. A civilization planning long-term energy use would value such consistency. Black hole systems offer no such guarantee. Accretion can fluctuate. Jets can shut down. The same black hole can alternate between quiescence and outburst. Designing infrastructure around such variability introduces layers of complexity that dwarf any theoretical efficiency advantage. There is also the question of proximity. Stars are common. They populate galaxies by the hundreds of billions. Many are close enough that energy interception is at least conceivable. Black holes are rarer and often distant. The most energetic examples reside in galactic centers far removed from habitable regions. Transporting energy across such distances adds further losses and risks. From every practical angle, stars appear superior. They are simpler, safer, and more generous. And yet, the fascination with black holes persists. This persistence reveals something important. The appeal is not rooted in utility. It is rooted in extremity. Black holes represent the limits of physical law. They compress gravity, energy, and space-time into regimes that challenge intuition. Thinking about them as energy sources is less about solving an energy problem and more about probing the boundaries of what physics allows. Stars already satisfy most conceivable needs. They offer more energy than any civilization could plausibly require. The turn toward black holes therefore signals a different motivation. It reflects a desire to test mastery rather than to meet demand. It asks not what is sufficient, but what is maximal. This shift in perspective is revealing. It shows how technological imagination can drift away from necessity toward abstraction. When resources are abundant, curiosity turns toward extremes. In that sense, black holes function as conceptual mirrors. They expose the difference between power and usefulness. They force a reckoning with the fact that greater intensity does not imply greater suitability. By comparing stars and black holes, the hierarchy becomes clear. Stability often outweighs magnitude. Accessibility matters more than concentration. The universe already provides generous energy sources. Choosing to look beyond them raises a deeper question about intention. If stars already offer everything needed, then the continued contemplation of black holes is not driven by scarcity, but by the uniquely human impulse to explore the most extreme possibilities simply because they exist. Which leads naturally to the question of why humanity keeps turning its attention to black holes at all when far simpler sources are already at hand. When discussions turn toward civilizations capable of exploiting extreme energy sources, the Kardashev scale inevitably enters the conversation. Proposed by Nikolai Kardashev. This scale does not measure intelligence, culture, or wisdom. It measures energy consumption. It ranks civilizations according to how much power they can access and control. A Type I civilization uses energy comparable to that available on its home planet. A Type II civilization harnesses the full output of its star. A Type III civilization commands the energy of an entire galaxy. Within this framework, black holes often appear as symbols of the highest tiers. Their immense energy densities suggest a civilization that has moved far beyond stellar dependence. Yet the scale itself is deliberately narrow. It equates advancement with throughput. More energy implies a higher rank. This simplicity is both its strength and its limitation. It provides a clear quantitative measure, but it ignores qualitative dimensions. A civilization may consume vast energy inefficiently. Another may achieve stability with far less. The scale does not distinguish between mastery and excess. It does not ask how energy is used, only how much flows through the system. This becomes critical when black holes enter the picture. To even contemplate using them as energy sources implies operating at a level far beyond stellar engineering. It suggests a civilization capable of manipulating extreme gravity, controlling relativistic environments, and managing risks that dwarf planetary scales. But does this necessarily imply greater intelligence or wisdom? The scale assumes that energy access correlates with capability. History offers mixed evidence. On Earth, increases in energy use have enabled complexity, but they have also amplified vulnerability. Greater power magnifies both creation and destruction. The Kardashev framework captures growth, but not balance. It measures expansion, not restraint. Black holes, when placed within this scale, function as conceptual endpoints. They represent the idea of ultimate extraction. Yet this framing can mislead. It risks treating the universe as a reservoir waiting to be drained. It prioritizes domination over understanding. The fascination with black holes as markers of advanced civilization reveals an underlying assumption that progress means consuming ever more. But physical possibility does not imply desirability. A civilization could choose efficiency, longevity, or minimal impact over maximal extraction. Such choices would lower its position on the scale without diminishing its sophistication. In this sense, the Kardashev scale reflects a particular vision of advancement rooted in industrial expansion. It is useful for categorizing hypothetical capabilities, but insufficient for judging maturity. When black holes are invoked as energy sources, the conversation shifts from what can be done to what should be done. The scale does not answer that. It remains silent on purpose. It tells us how much power a civilization commands, not whether it understands the consequences of commanding it. As humanity contemplates its future, this distinction matters. Energy is a tool, not a goal. Measuring civilization solely by consumption risks mistaking intensity for progress. Black holes tempt the imagination because they sit at the extreme end of the scale. But extremes test more than capacity. They test judgment. And that brings the discussion back to its core tension. If the accumulation of energy defines rank but not wisdom, then increasing power alone cannot be equated with advancement, forcing us to confront whether possessing more energy truly makes a civilization more advanced, or merely more capable of acting on its impulses. Beyond questions of feasibility lies a more serious concern: physical risk. Near a black hole, stability is not the default state. Orbits that appear mathematically allowed can become dynamically unstable under small perturbations. Gravitational interactions couple with radiation pressure, magnetic fields, and relativistic effects in ways that resist full modeling. A configuration that seems controlled can drift into chaos without warning. Unlike familiar engineering environments, there is no benign failure region. Systems do not gently degrade. They cross thresholds. Once crossed, recovery is impossible. Energy extraction concepts amplify this danger. Any attempt to tap rotational or accretion energy introduces feedback. Removing energy changes the system that supplies it. Altering spin affects space-time geometry. Modifying accretion flows reshapes magnetic fields and radiation output. These changes can trigger cascades. Feedback loops may grow instead of damping. The system can respond in ways that models fail to anticipate. This is not hypothetical caution. Nonlinear systems routinely exhibit emergent behavior that escapes prediction even when equations are known. Near a black hole, nonlinearity is extreme. Crucially, there is no safe way to experiment. One cannot begin with a small-scale test. There is no laboratory analog. No miniature version exists where failure is acceptable. Any real attempt would operate at full consequence from the first moment. Data would be collected only if the system survives. If it does not, the experiment ends permanently. This reality changes the ethics of exploration. Science often advances through controlled risk. Experiments fail. Lessons are learned. Here, failure means irreversible loss, material, energy, and potentially entire regions of space could be destabilized. Even distant observers might be affected by uncontrolled emissions or gravitational disturbances. The absence of reversibility removes a key safety valve that modern science relies upon. It forces a reassessment of acceptable risk. In environments where errors cannot be undone, the standard approach of learning by doing becomes untenable. This does not merely slow progress. It challenges the assumption that every question must be tested physically. Some knowledge may need to remain theoretical because the act of testing carries unacceptable cost. Black holes represent the sharpest expression of this dilemma. They are systems where nature enforces finality. There are no second chances near an event horizon. This fact reframes ambition once again. The barrier is not just danger, but irreversibility. When outcomes cannot be rolled back, caution becomes a necessity rather than a choice. And so the central question emerges with greater weight. If there is no safe way to test, no gradual path forward, and no margin for correction, should the desire to explore override the responsibility to avoid irreversible harm, beyond physical danger lies a quieter but deeper risk: ethical risk. Any technology capable of accessing extreme energy inevitably raises questions of control. Who decides how it is used? Who benefits? Who bears the consequences if something goes wrong? History shows that powerful technologies rarely remain neutral. They amplify existing structures of authority. They concentrate influence. The greater the energy involved, the greater the asymmetry that follows. A source as extreme as a black hole would not merely supply power, it would redefine power. Control over such a system would grant disproportionate leverage. Economic dominance would follow. Political imbalance would harden. Decisions made by a few could affect regions far beyond their immediate reach. The scale of consequence grows faster than the scale of accountability. Purpose becomes another ethical fault line. Energy can sustain civilizations, but it can also enable coercion, surveillance, and destruction. The same infrastructure that supports stability can be repurposed for control. When the energy source is unprecedented in magnitude, the potential misuse scales accordingly. Intentions may begin as benign, but incentives evolve. Once dependence forms, restraint weakens. The question shifts from whether the technology can be abused to how quickly abuse becomes normalized. There is also the issue of exclusion. Access to extreme energy would not be evenly distributed. Entire populations, or even entire civilizations, could be left outside its benefits while remaining exposed to its risks. If other intelligent life exists, the ethical horizon widens further. Manipulating cosmic-scale energy sources could alter environments shared across vast distances. Actions taken by one civilization might impose irreversible conditions on others without consent or awareness. This introduces a moral responsibility that extends beyond planetary or even stellar boundaries. Technology at this level ceases to be local. It becomes cosmological in implication. Importantly, technology itself does not choose. It executes. Values are supplied by those who wield it. Assuming neutrality is a mistake, every design embeds priorities. Every deployment reflects judgment. The greater the power, the more unforgiving those judgments become. Small ethical failures at low energy scales produce limited harm. At extreme scales, the same failures propagate catastrophically. This imbalance forces reflection. Wisdom does not scale automatically with capability. Intelligence does not guarantee restraint. Collective understanding often lags behind technical achievement. When tools grow faster than shared ethics, instability follows. Black hole energy represents the ultimate version of this problem. It is not simply a question of engineering feasibility. It is a test of moral readiness. Whether a civilization can handle such power responsibly depends less on physics than on governance, culture, and humility. The ethical risk lies not in malevolence alone, but in overconfidence. Believing that capability implies justification is the first failure. Recognizing limits is harder than overcoming them, and so the discussion turns inward. When power grows beyond the scale of collective wisdom, something fundamental is threatened. It may not be survival alone, but trust, balance, and the shared framework that allows civilizations to coexist, leading inevitably to the question of what truly stands at risk when strength outpaces the ability to use it wisely. History repeatedly shows that technology often advances faster than understanding. Tools are built, deployed, and normalized long before their full consequences are grasped. Early successes create confidence. Immediate benefits overshadow distant risks. Only later do the deeper costs emerge. This pattern is not accidental. Human societies are driven by short-term incentives. Urgency favors action over reflection. Once a capability exists, pressure builds to use it. Restraint appears abstract. Consequences feel hypothetical. In many cases, the harm is delayed, diffuse, and difficult to trace back to a single decision. Black holes represent an extreme version of this familiar danger. They are among the least understood objects in physics. While their broad behavior is described by theory, many details remain unresolved. The interaction between gravity, quantum effects, and extreme energy densities is not fully unified. We do not yet possess a complete theory that describes black holes in all regimes. Intervening in such systems would mean acting inside a domain where understanding is explicitly incomplete. That incompleteness matters. Control depends on prediction. Prediction depends on comprehension. When understanding is partial, control becomes an illusion. A system may appear stable under known models while harboring unknown modes of failure. History offers many examples of this mismatch. Technologies introduced with confidence later revealed side effects that were invisible at the time of deployment. Environmental damage, systemic risk, and long-term instability often surfaced only after scale made reversal impossible. In each case, early intervention was justified by necessity or optimism. In hindsight, the cost of patience would have been far lower than the cost of correction. With black holes, the stakes rise dramatically. These are not systems where failure produces localized harm. They operate at scales where errors propagate outward. A misjudged interaction could alter gravitational dynamics, radiation output, or energetic balance in ways that cannot be contained. There is no buffer zone. There is no gradual ramp-up. Intervention would occur at full intensity from the start. This removes the safety net that allowed earlier technologies to be refined through experience. It also magnifies the ethical burden. Acting without sufficient understanding is not merely risky. It is irresponsible when the consequences extend beyond the ability to respond. Knowledge gaps are not neutral. They represent unknown risks. Proceeding in spite of them transfers uncertainty into reality. In most technological histories, Society learns by absorbing damage. In the context of black holes, absorbing damage may not be possible. The margin for learning through error disappears. This forces a reversal of the usual logic. Instead of acting until problems appear, restraint becomes the rational choice until understanding is deep enough to justify intervention. This is difficult for a species accustomed to exploration through trial. It demands a different relationship with curiosity, one that values delay as a form of intelligence rather than weakness. Black holes challenge not only physics, but temperament. They test whether humanity can recognize when not to act. The temptation to use what is powerful before it is fully understood is deeply ingrained. Yet history suggests that the most severe consequences arise precisely from this impulse. When comprehension lags behind capability, systems behave in ways no one intended. The damage often arrives quietly, accumulates invisibly, and only becomes undeniable when reversal is impossible. In that light, the prospect of intervening in black hole systems raises a sobering reflection. Humanity has paid for premature action many times before, but never in environments where mistakes could not be undone at any scale. Which leads naturally to the question of what prices have already been paid in the past when knowledge was mistaken for control. Technological history carries a repeating pattern. Breakthroughs arrive with promise, speed, and confidence. Consequences arrive later, slower, and often uninvited. The delay between invention and full impact creates a dangerous illusion of control. Early stages appear manageable. Benefits are visible. Risks remain abstract. Only with time do secondary effects accumulate and reveal themselves. Nuclear energy offers a clear example. Initially celebrated as a near-limitless power source, it transformed warfare and energy production alike. The physics worked exactly as predicted. What proved harder to manage were political incentives, waste, persistence, and the long tail of environmental and ethical cost. The technology was not flawed. The context of its use was. Industrial chemistry follows a similar arc. Synthetic compounds revolutionized agriculture, medicine, and manufacturing. Yet many chemicals introduced as solutions later revealed toxicity, persistence, and ecological disruption. The damage unfolded gradually. Cause and effect separated across decades. Correction lagged behind deployment. Biotechnology adds another layer. Tools that allow manipulation of life promise extraordinary benefits. But they also carry risks that propagate invisibly. Genetic changes do not respect borders. Biological systems amplify small interventions. Oversight often reacts after diffusion, not before. In all these cases, the pattern holds. Understanding grows after implementation. Regulation follows damage. Society learns by absorbing cost. This model, while imperfect, relies on one crucial assumption: that errors are survivable, that harm, while serious, can be mitigated, that systems allow retreat, adaptation, and repair. Black holes violate this assumption completely. They offer no buffer between action and consequence. There is no slow diffusion of impact, no long adjustment period. Any intervention would unfold at full scale immediately. There is no room for feedback-based correction. A mistake would not produce lessons. It would terminate the experiment. This is what makes analogies to past technologies only partially useful. Those histories teach caution, but they also highlight a difference. Past errors occurred in systems that allowed recovery. Black holes operate in regimes where recovery does not exist. The absence of reversibility changes the ethical calculus entirely. It raises the bar for justification beyond precedent. Learning through failure is not an option. Progress through iteration is impossible. This forces a more demanding definition of responsibility. It requires foresight rather than reaction. It demands that understanding precede action, not follow it. The temptation to proceed anyway is familiar. Each generation believes it will manage risk better than the last. Yet the structure of delay remains unchanged. Consequences always trail capability. In the case of black holes, the trail disappears. Cause and consequence collapse into the same moment. That compression removes the safety margin that has historically allowed technological ambition to survive its own mistakes. The lesson from history is therefore not that humanity should never innovate, but that innovation without reversibility carries a different moral weight. When there is no chance to correct course, the threshold for action must be higher. This distinction marks the boundary between progress and recklessness. Progress expands understanding while preserving the ability to respond. Recklessness commits power before comprehension. And in environments where errors cannot be undone, the difference between the two becomes not philosophical, but existential, forcing us to confront what truly separates advancement, guided by wisdom, from ambition, driven by momentum alone. As technological imagination stretches toward the most extreme possibilities, a quieter principle becomes increasingly important. Understanding must come before use. Throughout the history of science, the most durable advances have emerged when theory matured before application. When understanding leads, technology tends to be measured, adaptable, and resilient. When application races ahead, uncertainty hardens into risk. Black holes force this principle into sharp relief. They are not merely powerful objects. They are boundary conditions of physics itself. Many of their properties are known only through indirect inference. Others remain unresolved at the deepest theoretical levels. Acting within such systems without a complete framework is not exploration. It is improvisation under irreversible conditions. Science, at its best, maps limits before attempting to cross them. It identifies where models break down, where assumptions fail, and where unknowns dominate. This mapping is not a delay to progress. It is progress. Understanding constraints refines ambition. It transforms raw possibility into informed choice. Not every physically allowed action is a rational one. The ability to do something does not impose an obligation to do it. Black holes illustrate this distinction with unusual clarity. They exist as natural experiments already running at cosmic scale. They radiate, merge, evolve, and decay without intervention. By observing them, science gains insight into gravity, quantum effects, and the structure of space-time itself. This knowledge is valuable independent of use. In fact, its value may be greatest precisely because it is not instrumentalized. Restraint becomes a form of intelligence here. Choosing not to intervene preserves the integrity of the system being studied. It allows understanding to deepen without distortion. It acknowledges that some domains yield more by observation than by manipulation. This runs counter to a common technological instinct that equates engagement with action. Yet maturity often expresses itself through selective inaction. Knowing when to stop is as important as knowing how to proceed. Slowness in this context is not weakness. It is calibration. It aligns capability with comprehension. It prevents power from outrunning meaning. In the case of black holes, patience is not passive. It is active attention. It is the decision to listen to what the universe reveals without attempting to bend it to immediate purpose. This perspective reframes value itself. Black holes do not need to be exploited to matter. Their significance lies in what they teach about limits, about entropy, about time, and about the architecture of reality. They serve as reference points for theory, as tests for ideas, and as reminders that the universe contains processes far beyond practical use. In that sense, they enrich understanding without demanding control. As humanity considers its future, this lesson grows more relevant. Power will continue to increase. Opportunities to intervene will multiply. The question will not always be what can be done, but what should remain untouched. Wisdom may lie less in expanding reach than in choosing boundaries. Black holes stand as silent instructors in this regard. They suggest that the highest form of advancement may be knowing when knowledge itself is the destination, which leads naturally to the question of what value black holes hold if they are never exploited, and whether understanding alone can be a sufficient and meaningful outcome throughout the series. Black holes have appeared as objects of immense power, yet at this stage, their role shifts. They become less a test of strength and more a test of restraint. The challenge they pose is not whether a civilization can manipulate extreme forces, but whether it can choose not to. Intelligence is often measured by problem solving, by the ability to bend nature toward goals. Maturity introduces a different metric: the capacity to recognize when intervention reduces understanding rather than expands it. Black holes sit precisely at this boundary. They are systems where observation yields profound insight, while interference risks irreversible distortion. To study them without attempting to exploit them requires discipline. It demands separating curiosity from possession. Understanding without ownership is counterintuitive in a technological culture accustomed to extraction. Yet this separation may mark a higher level of cognitive development. Observation without intervention preserves complexity. It allows phenomena to unfold according to their own dynamics. In such cases, knowledge accumulates without collapsing the system under study. This approach reflects confidence rather than limitation. It signals that comprehension is valued over control. Choosing not to act is often mistaken for hesitation. In reality, it can be the result of deeper awareness. Knowing the consequences of action can lead to deliberate inaction. Black holes force this distinction into clarity. Their environments punish impatience. Their scale exposes the cost of arrogance. A civilization that approaches them with humility acknowledges that not all power needs to be exercised. This reframes what progress means. Advancement is no longer defined by how much can be taken, but by how much can be understood without harm. The ability to observe without altering becomes a mark of sophistication. It suggests a civilization capable of long-term thinking, capable of valuing stability over dominance. In this sense, black holes function as mirrors. They reflect the values of those who study them. Exploitation would reveal insecurity and urgency. Restraint reveals confidence and foresight. The choice is not imposed by physics. It is imposed by character. A mature scientific culture recognizes that some systems offer their greatest lessons when left intact. It understands that curiosity does not always require intervention. The most demanding challenge is not overcoming nature, but aligning ambition with responsibility. Black holes do not demand conquest. They demand judgment. They test whether intelligence has grown beyond impulse. As this realization settles, the question shifts from capability to definition. A civilization may possess immense knowledge and still fail this test if it cannot restrain itself. Conversely, A civilization that chooses understanding over exploitation demonstrates a different kind of advancement. This leads naturally to the deeper question of how maturity itself should be defined. Is it measured by power accumulated, or by the wisdom to know when power should remain unused? As the discussion reaches its most reflective point, one conclusion emerges with clarity. Humility is not a moral accessory. It is a survival condition. The universe operates independently of human intention. Its laws do not adjust to ambition, optimism, or error. Gravity does not negotiate. Thermodynamics does not forgive. Systems evolve according to principles that remain indifferent to who observes them or why. In such an environment, mistakes are not corrected by second chances. They are absorbed into outcome. This reality places a hard constraint on technological aspiration. Survival over long timescales requires alignment with natural limits rather than attempts to override them. Humility functions as a stabilizing strategy. It encourages careful observation before intervention. It prioritizes understanding over dominance. It recognizes that complexity increases faster than control. Civilizations that mistake capability for entitlement expose themselves to irreversible risk. History suggests that collapse often follows not from weakness, but from overreach. The inability to recognize boundaries has ended more projects than lack of ingenuity ever did. In the cosmic context, this lesson intensifies. The universe does not center human goals. It does not reward boldness for its own sake. It responds only to consistency with its laws. A humble approach accepts this asymmetry. It acknowledges that knowledge grows through patience. That longevity depends on restraint. That not every accessible domain must be entered. Knowing which doors to leave closed becomes a form of intelligence. This does not diminish science. It refines it. Science, guided by humility, seeks coherence rather than conquest. It asks how systems work before asking how they can be used. It values prediction, verification, and limits. It treats ignorance as a signal to slow down, not as an obstacle to push through. In this frame, humility is not passivity. It is active calibration. It aligns ambition with reality. It prevents curiosity from mutating into compulsion. A civilization that internalizes this principle increases its chance of persistence. It reduces self-imposed hazards. It learns to coexist with forces it cannot dominate. Black holes represent the ultimate reminder of this condition. They do not respond to intention. They expose error instantly. They embody regimes where miscalculation has final consequences. Approaching them with humility is not optional. It is mandatory for survival. This recognition reframes the purpose of scientific inquiry. The goal shifts from extraction to understanding, from expansion to integration, from opening every door to choosing wisely which ones should remain closed. When humility becomes foundational, science evolves into a practice of listening rather than intrusion. If humility is the prerequisite for survival, then what? Ultimately, should science aim for, if not the relentless exercise of power, but the cultivation of understanding that allows a civilization to endure within the universe it inhabits? At the end of this journey, 1. Truth stands quietly behind every discovery. The universe does not depend on being understood. It existed long before observation. It will continue long after curiosity fades. Galaxies formed. Stars ignited. Black holes merged. And space-time evolved without regard for whether any mind was present to witness it. Understanding is not a requirement imposed by the cosmos. It is an activity chosen by those within it. This distinction matters. It reframes knowledge not as entitlement, but as privilege. The universe does not owe explanation. It does not wait for readiness. Black holes do not pause their evolution until theory catches up. They form, radiate, merge, and decay according to laws that operate regardless of comprehension. Science, therefore, is not an act of conquest. It is an act of approach. It does not grant ownership over what is studied. It offers alignment with how things already are. When this is forgotten, inquiry hardens into domination. Questions become tools. Understanding becomes leverage. The universe resists this posture, not through opposition, but through indifference. Errors are not corrected. Misjudgments are not softened. Consequences unfold as they must. In this light, science reveals its deeper character. It is not about forcing clarity onto reality. It is about earning partial insight through patience, endurance, rigor, and restraint. Each answer opens further uncertainty. Each model carries assumptions that may later fail. This is not weakness. It is the structure of learning in a universe that exceeds any single perspective. Black holes exemplify this structure. They are among the most studied objects in modern physics. Yet they remain partially opaque. The more deeply they are examined, the more they expose the limits of current understanding. They do not yield mastery. They offer lessons. Chief among them is humility. The recognition that comprehension is always provisional. That observation does not imply control. That proximity to truth does not remove mystery. Science, at its most mature, accepts this condition. It advances without expecting finality. It values coherence over closure. It understands that the goal is not to finish the map, but to improve navigation. In this sense, the act of trying to understand the universe becomes meaningful precisely because it is not required. It is an expression of curiosity rather than necessity, of care rather than entitlement, of participation rather than dominance. Black holes will continue their paths regardless of what is known about them. The universe will unfold according to its own logic. The only variable is how a thinking species chooses to engage with that unfolding, whether with impatience or patience, with extraction or observation, with arrogance or humility. The final question, therefore, does not belong to the universe. It belongs to us. If the universe does not need to be understood, why do we keep trying to understand it anyway?